The Project Gutenberg ebook of Form and Function, a contribution to the history of animal morphology. This ebook is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. Title: Form and Function, a contribution to the history of animal morphology. Author: E. S. Russell. Release date: January 23, 2007. Ebook number 20426. Language: English. Credits: produced by Suzanne Liebarger, Turgut Dinser, and the online distributed proofreading team at http://www.pgdp.net. This file was produced from images generously made available by the Internet Archive/Canadian Libraries. Start of the Project Gutenberg ebook. Form and Function, a contribution to the history of animal morphology. Form and Function, a contribution to the history of animal morphology by E. S. Russell, M.A., Bachelors of Science, F.Z.S. Illustrated. London: John Murray, Albemarle Street, W. 1916. All rights reserved. Transcriber's note: obvious printer errors have been corrected, all other inconsistencies in spelling and punctuation are as in the original. Preface: this book is not intended to be a full or detailed history of animal morphology. A complete account is given neither of morphological discoveries nor of morphological theories. My aim has been rather to call attention to the existence of diverse typical attitudes to the problems of form, and to trace the interplay of the theories that have arisen out of them. The main currents of morphological thought are to my mind three: the functional or synthetic, the formal or transcendental, and the materialistic or disintegrative. The first is associated with the great names of Aristotle, Cuvier, and von Baer, and leads easily to the more open vitalism of Lamarck and Samuel Butler. The typical representative of the second attitude is Geoffroy Saint-Hilaire, and this habit of thought has greatly influenced the development of evolutionary morphology. The main battleground of these two opposing tendencies is the problem of the relation of function to form. Is function the mechanical result of form, or is form merely the manifestation of function or activity? What is the essence of life organization or activity? The materialistic attitude is not distinctively biological, but is common to practically all fields of thought. It dates back to the Greek atomists, and the triumph of mechanical science in the 19th century has induced many to accept materialism as the only possible scientific method. In biology, it is more akin to the formal than to the functional attitude. In the course of this book, I have not hidden my own sympathy with the functional attitude. It appears to me probable that more insight will be gained into the real nature of life and organization by concentrating on the active response of the animal, as manifested both in behavior and in morphogenesis, particularly in the post-embryonic stages, than by giving attention exclusively to the historical aspect of structure, as is the custom of pure morphology. I believe we shall only make progress in this direction if we frankly adopt the simple everyday conception of living things which many of us have had drilled out of us, that they are active, purposeful agents, not mere complicated aggregations of protein and other substances. Such an attitude is probably quite as sound philosophically as the opposing one, but I have not in this place attempted any justification of it. I have touched very lightly upon the controversy between vitalism and materialism, which has been revived with the early years of the present century. It hardly lends itself as yet to historical treatment, and I could hardly hope to maintain with regard to it that objective attitude which should characterize the historian. The main result I hope to have achieved with this book is the demonstration, tentative and incomplete as it is, of the essential continuity of animal morphology from the days of Aristotle down to our own time. It is unfortunately true that modern biology, perhaps in consequence of the great advances it has made in certain directions, has to a considerable extent lost its historical consciousness, and if this book helps in any degree to counteract this tendency so far as animal morphology is concerned, it will have served its purpose. I owe a debt of gratitude to my friends Dr. James F. Gemmell and Professor J. Arthur Thomson for much kindly encouragement and helpful criticism. The credit for the illustrations is due to my wife, Mrs. Jehanne A. Russell. One is from nature, the others are drawn from the original figures. ESR Chelsea, 1916. Contents Chap Page I. The Beginnings of Comparative Anatomy 1-2. Comparative Anatomy before Cuvier 17-3. Cuvier 31-4. Goethe 45 v. Etienne Geoffroy Saint-Hilaire 52-6. The Followers of Etienne Geoffroy Saint-Hilaire 79-7. The German Transcendentalists 89-8. Transcendental Anatomy in England Richard Owen 102-9. Carl Ernst von Baer 113x. The Embryological Criterion 133-11. The Cell Theory 169-12. The Close of the Pre-Evolutionary Period 190-13. The Relation of Lamarck and Darwin to Morphology 213-14. Ernst Haeckel and Carl Gegenbohr 246-15. Early Theories on the Origin of Vertebrates 268-16. The Germ Layers and Evolution 288-17. The Organism as an Historical Being 302-18. The Beginnings of Causal Morphology 314-19. Samuel Butler and the Memory Theories of Heredity 335xx. The Classical Tradition in Modern Morphology 345 Index 365 Illustrations Fig. Page 1. Hyoid Arch of the Conger. Original. 58-2. Vertebra of a pleuronectid. Geoffroy. 61-3. Abdominal segment of the lobster. Geoffroy. 63-4. Ideal typical vertebra. Owen. 102-5. Natural typical vertebra. Owen. 103-6. The archetype of the vertebrate skeleton. Owen. 105-7. Ideal transverse section of a vertebrate embryo. Von Baer. 119-8. Gill slits of the pig embryo. Rathke. 134-9. Meckel's cartilage and ear-ossicles in embryo of pig. Reichert. 145-10. Cranial vertebrae and visceral arches in embryo of pig. Reichert. 148-11. Embryonic cranium of the adder. Rathke. 152-12. Transverse section of chick embryo. Rimac. 211-13. Development of the Ascidion larva, Kowalewski. 272-14. Transverse section of the worm Nyes. Semper. 280-15. The 5 primary stages of ontogeny. Haeckel. 292 Form and Function Chapter I. The Beginnings of Comparative Anatomy. The first name of which the history of anatomy keeps record is that of Alcmaeon, a contemporary of Pythagoras, 6th century BC. His interests appear to have been rather physiological than anatomical. He traced the chief nerves of sense to the brain, which he considered to be the seat of the soul, and he made some good guesses at the mechanism of the organs of special sense. He showed that, contrary to the received opinion, the seminal fluid did not originate in the spinal cord. 2 comparisons are recorded of his, one that puberty is the equivalent of the flowering time in plants, the other that milk is the equivalent of white of egg. One both show his bias towards looking at the functional side of living things. The latter comparison reappears in Aristotle. A century later, Diogenes of Apollonia gave a description of the venous system. He too placed the seat of sensation in the brain. He assumed a vital air in all living things, being in this influenced by Anaximenes, whose primitive matter was infinite air. In following out this thought, he tried to prove that both fishes and oysters have the power of breathing. To a more strictly morphological note is struck by a curious saying of Empedocles, 4th century BC, that hair and foliage and the thick plumage of birds are one. 3. In the collected writings of Hippocrates and his school, the Corpus Hippocraticum, of which no part is later than the end of the 5th century, there are recorded many anatomical facts. The author of the treatise on the muscles knew, for instance, that the spinal marrow is different from ordinary marrow and has membranes continuous with those of the brain. Embryos of 7 days have all the parts of the body plainly visible. Work on comparative embryology is contained in the treatise on the development of the child. For the author of the treatise on the joints, which Littra calls the great surgical monument of antiquity, is to be credited with the first systematic attempt at comparative anatomy, for he compared the human skeleton with that of other vertebrates. Aristotle, 384 to 322 BC. 5. May fairly be said to be the founder of comparative anatomy, not because he was specially interested in problems of pure morphology, but because he described the structure of many animals and classified them in a scientific way. We shall discuss here the morphological ideas which occur in his writings upon animals in the Historia Animalium, the De Partibus Animalium, and the De Generatione Animalium. The Historia Animalium is a most comprehensive work, in some ways the finest textbook of zoology ever written. Certainly few modern textbooks take such a broad and sane view of living creatures. Aristotle never forgets that form and structure are but one of the many properties of living things. He takes quite as much interest in their behavior, their ecology, distribution, comparative physiology. He takes a special interest in the comparative physiology of reproduction. The Historia Animalium contains a description of the form and structure of man and of as many animals as Aristotle was acquainted with, and he was acquainted with an astonishingly large number. The later De Partibus Animalium is a treatise on the causes of the form and structure of animals. Owing to the importance which Aristotle ascribed to the final cause, this work became really a treatise on the functions of the parts, a discussion of the problems of the relation of form to function, and the adaptedness of structure. Aristotle was quite well aware that each of the big groups of animals was built upon one plan of structure, which showed endless variations in excess and defect in the different members of the group. But he did not realize that this fact of community of plan constituted a problem in itself. His interest was turned towards the functional side of living things. Form was for him a secondary result of function. Yet he was not unaware of facts of form for which he could not quite find a place in his theory of organic form, facts of form which were not, at first sight at least, facts of function. Thus he was aware of certain facts of correlation, which could not be explained offhand as due to correlation of the functions of the parts. He knew, for instance, that all animals without front teeth in the upper jaw have cotyledons, while most that have front teeth on both jaws and no horns have no cotyledons. De General, 2:7. Speaking generally, however, we find in Aristotle no purely morphological concepts. What then does morphology owe to Aristotle? It owes to him, first, a great mass of facts about the structure of animals, second, the first scientific classification of animals, third, a clear enunciation of the fact of community of plan within each of the big groups, fourth, an attempt to explain certain instances of the correlation of parts, fifth, a pregnant distinction between homogeneous and heterogeneous parts, Sixth, a generalization on the succession of forms in development, and seventh, the first enunciation of the idea of the échelle d'êtres. 1. What surprises the modern reader of the Historia Animalium perhaps more than anything else is the extent and variety of Aristotle's knowledge of animals. He describes more than 500 kinds. 7. Not only does he know the ordinary beasts, birds, and fishes with which everyone is acquainted, but he knows a great deal about cuttlefish, snails, and oysters, about crabs, crawfish, palinurus, lobsters, shrimps, and hermit crabs, about sea urchins and starfish, sea anemones, and sponges, about ascidians, which seem to have puzzled him not a little. He has noticed even fish lice and intestinal worms, both flat and round. Of the smaller land animals, he knows a great many insects and their larvae. The extent of his anatomical knowledge is equally surprising, and much of it is clearly the result of personal observation. No one can read his account of the internal anatomy of the chameleon, Histori Anim, 2, or his description of the structure of cuttlefish, Histori Anim, 4, or that touch in the description of the hermit crab, Histori Anim, 4. Two large eyes, not turned on one side like those of crabs, but straightforward without being convinced that Aristotle is speaking of what he has seen. Naturally he could not make much of the anatomy of small insects and snails, and, to tell the truth, he does not seem to have cared greatly about the minutiae of structure. He was too much of a Greek and an aristocrat to care about laborious detail. Not only did he lay a foundation for comparative anatomy, but he made a real start with comparative embryology. Medical men before him had known many facts about human development. Aristotle seems to have been the first to study in any detail the development of the chick. He describes this as it appears to the naked eye, the position of the embryo on the yolk, the palpitating spot at the third day, the formation of the body and of the large sightless eyes, the veins on the yolk, the embryonic membranes, of which he distinguished two. 2. Aristotle had various systems of classifying animals. They could be classified, he thought, according to their structure, their manner of reproduction, their manner of life, their mode of locomotion, their food, and so on. Thus you might, in addition to structural classifications, divide animals into gregarious, solitary, and social, or land animals into troglodytes, surface dwellers, and burrowers, Histori Anim, I. He knew that dichotomous classifications were of little use for animals, de partibus, I3, and he explicitly and in so many words accepted the principle of all natural classification, that affinities must be judged by comparing not one but the sum total of characters. As everyone knows, he was the first to distinguish the big groups of animals, many of which were already distinguished roughly by the common usages of speech. Among his sanguini he did little more than define with greater exactitude the limits of the groups established by the popular classification. Among the exsanguineous animals, however, corresponding to our invertebrates, he established a much more definite classification than the popular, which is apt to call them indiscriminately shellfish, insects, or creeping things. He went beyond the superficialities of popular classification, too, in clearly separating cetacea from fishes. He had some notion of species and genera in our sense. He distinguished many species of cuttlefish, octopus, polypus, of which there were many kinds, Ylodon, moschites, which he knew to have only one row of suckers while octopus has two, Argonauta, Nautilus, Sepia, and apparently Liligomedia, equals his Toothes, and L. vulgaris, or Forbesii, which seems to be his Tuthos. He had a grasp of the principles which should be followed in judging of the natural affinities of species. For example, he knew that the cuckoo resembles a hawk. But, he says, the hawk has crooked talons, which the cuckoo has not, nor does it resemble the hawk in the form of its head, but in these respects is more like the pigeon than the hawk, which it resembles in nothing but its color. The markings, however, upon the hawk are like lines, while the cuckoo is spotted. History Annum, Cresswell's Trans, p. 147, London, 1862. The groups he distinguished were man, viviparous quadrupeds, oviparous quadrupeds, birds, fishes, cetacea, cephalopoda, malacostraca, equals higher crustacea, insecta, equals annulose animals, testacea, equals mollusks, echinoderms, ascidians. A class of acalephae, including sea anemones and sponges, was grouped with the testacea. The first 5 groups were classed together as sanguineous, the others as exsanguineous, from the presence or absence of red blood. Besides these classes there are, he says, many other creatures in the sea which it is not possible to arrange in any class from their scarcity. Cresswell, Loccit, p. 90. 3. Aristotle's greatest service to morphology is his clear recognition of the unity of plan holding throughout each of the great groups. He recognizes this most clearly in the case of man and the viviparous quadrupeds, with whose structure he was best acquainted. In the Historia Animalium he takes man as a standard, and describes his external and internal parts in detail, then considers viviparous quadrupeds and compares them with man. Whatever parts a man has before, a quadruped has beneath, those that are behind in man form the quadruped's back. Cresswell, Loccit, p. 26. Apes, monkeys, and cynocephali combine the characteristics of man and quadrupeds. He notices that all viviparous quadrupeds have hair. Oviparous quadrupeds resemble the viviparous, but they lack some organs, such as ears with an external pinna, mammae, hair. Oviparous bipeds, or birds, also have many parts like the animals described above. He does not, however, seem to realize that a bird's wings are the equivalent of a mammal's arms or forelegs. Fishes are much more divergent, they possess no neck, nor limbs, nor testicles, meaning a solid ovoid body such as the testis in mammals, nor mammae. Instead of hair they have scales. Speaking generally, the sanguinea differ from man and from one another in their parts, which may be present or absent, or exhibit differences in excess and defect, or in form. Unity of plan extends to all the principal systems of organs. All sanguineous animals have either a bony or a spinous column. The remainder of the bones exist in some animals, but not in others, for if they have the limbs they have the bones belonging to them. Cresswell, Loccit, p. 60. Viviparous animals with blood and feet do not differ much in their bones, but rather by analogy, in hardness, softness, and size. Cresswell, Loccit, p. 59. The venous system, too, is built upon the same general plan throughout the sanguinea. In all sanguineous animals, the nature and origin of the principal veins are the same, but the multitude of smaller veins is not alike in all, for neither are the parts of the same nature, nor do all possess the same parts. Cresswell, Loccit, p. 56. It will be noticed in the first and last of these 3 quotations that Aristotle recognizes the fact of correlation between systems of organs between limbs and bones, and between blood vessels and the parts to which they go. Sanguineous animals all possess certain organs: heart, liver, spleen, kidneys, and so on. Other organs occur in most of the classes: the esophagus and the lungs. The position which these parts occupy is the same in all animals. Sc. sanguinea, Cresswell, Loccit, p. 39. Unity of plan is observable not only in the sanguinea, but also within each of the other large groups. Aristotle recognizes that all his cuttlefish are alike in structure. Among his Malacostraca he compares point by point the external parts of the Carabus, Palinurus, and the Astacus, Homerus, and he compares also the general internal anatomy of the various genera he distinguishes. As regards Testacea, he writes, the nature of their internal structure is similar in all, especially in the turbinate animals, for they differ in size and in the relations of excess. The univalves and bivalves do not exhibit many differences. Cresswell, LOCCIT, p. 83. There is an interesting remark about the creature called Carcinium, hermit crab, that it resembles both the Malacostraca and the Testacea, for this in its nature is similar to the animals that are like carabi, and it is born naked. Cresswell, LOCCIT, p. 85. In the last phrase we may perhaps read the first recognition of the embryological criterion. With the recognition of unity of plan within each group necessarily goes the recognition of what later morphology calls the homology of parts. The parts of a horse can be compared one by one with the parts of another viviparous quadruped. In all the animals belonging to the same class the parts are the same, only they differ in excess or defect. These remarks are placed in the forefront of the Historia Animalium. Generally speaking, parts which bear the same name are for Aristotle homologous throughout the class. But he goes further and notes the essential resemblance underlying the differences of certain parts. He classes together nails and claws, the spines of the hedgehog, and hair, as being homologous structures. He says that teeth are allied to bones, whereas horns are more nearly allied to skin. Histori Anim, 3. This is an astonishingly happy guess, considering that all he had to go upon was the observation that in black animals the horns are black but the teeth white. One cannot but admire the way in which Aristotle fixes upon apparently trivial and commonplace facts, and draws from them far-reaching consequences. He often goes wrong, it is true, but he always errs in the grand manner. While Aristotle certainly recognized the existence of homologies, and even had a feeling for them, he did not clearly distinguish homology from analogy. He comes pretty near the distinction in the following passage. After explaining that in animals belonging to the same class the parts are the same, differing only in excess or defect, he says, but some animals agree with each other in their parts neither in form nor in excess and defect, but have only an analogous likeness, such as a bone bears to a spine, a nail to a hoof, a hand to a crab's claw, the scale of a fish to the feather of a bird, for that which is a feather in the bird is a scale in the fish. Cresswell, LOCCIT, p. 2. One of these comparisons is, however, a homology not an analogy, and the last phrase throws a little doubt upon the whole question, for it is not made clear whether it is position or function that determines what are equivalent organs. In the De Partibus Animalium there occurs the following passage: groups that only differ in degree, and in the more or less of an identical element that they possess, are aggregated under a single class. Groups whose attributes are not identical but analogous are separated. For instance, bird differs from bird by gradation, or by excess and defect. Some birds have long feathers, others short ones, but all are feathered. Bird and fish are more remote and only agree in having analogous organs, for what in the bird is feather, in the fish is scale. Such analogies can scarcely, however, serve universally as indications for the formation of groups, for almost all animals present analogies in their corresponding parts. 8. It is thus similarity in form and structure which determines the formation of the main groups. Within each group the parts differ only in degree, in largeness or smallness, softness and hardness, smoothness or roughness, and the like. LOCCIT, I, 4, 644b. These passages show that Aristotle had some conception of homology as distinct from analogy. He did not, however, develop the idea. What Aristotle sought in the variety of animal structure, and what he found, were not homologies, but rather communities of function, parts with the same attributes. His interest was all in organs, in functioning parts, not in the mere spatial relationship of parts. This comes out clearly in his treatise on the parts of animals, which is subsequent to, and the complement of, his History of Animals. The latter is a description of the variety of animal form, the former is a treatise on the functions of the parts. He describes the plan of the De Partibus Animalium as follows: we have, then, first to describe the common functions, common, that is, to the whole animal kingdom, or to certain large groups, or to members of a species. In other words, we have to describe the attributes common to all animals, or to assemblages, like the class of birds, of closely allied groups differentiated by gradation, or to groups like man not differentiated into subordinate groups. In the first case the common attributes may be called analogous, in the second generic, in the third specific, I. 5, 645b, trans. Ogle. The alimentary canal is a good example of a part which is analogous throughout the animal kingdom, for all animals possess in common those parts by which they take in food, and into which they receive it. Cresswell, Loccit, p. 6. The De Partibus Animalium becomes in form a comparative organography, but the emphasis is always on function and community of function. Thus he treats of bone, fish spine, and cartilage together, De Partibus, 2, 9, 655a, because they have the same function, though he says elsewhere that they are only analogous structures, 2, 8, 653b. In the same connection he describes also the supporting tissues of invertebrates, the hard exoskeleton of crustacea and insects, the shell of testacea, the bone of sepia, 2, 8, 654a. Aristotle took much more interest in analogies, in organs of similar function, than in homologies. He did recognize the existence of homologies, but rather malgré lui, because the facts forced it upon him. His only excursion into the realm of transcendental anatomy is his comparison of a cephalopod to a doubled-up vertebrate whose legs have become adherent to its head, whose alimentary canal has doubled upon itself in such a way as to bring the anus near the mouth, De Partibus, 4, 9, 684b. It is clear, however, that Aristotle did not seek to establish by this comparison any true homologies of parts, but merely analogies, thus avoiding the error into which Marinx and Lorenzit fell more than 2,000 years later in their paper communicated to the Académie des Sciences, which formed the starting point of the famous controversy between Cuvier and Geoffroy Saint-Hilaire, see chap v. below. Moreover, Aristotle did not so much compare a cephalopod with a doubled-up vertebrate as contrasts cephalopods, and also testacea, with all other animals. Other animals have their organs in a straight line, cephalopods and testacea alone show this peculiar doubling up of the body. 4. Aristotle was much struck with certain facts of correlation, of the interdependence of two organs which are not apparently in functional dependence on one another. Such correlation may be positive or negative, the presence of one organ may either entail the presence of the other, or it may entail its absence. Aristotle has various ways of explaining facts of correlation. He observed that no animal has both tusks and horns, but this fact could easily be explained on the principle that nature never makes anything superfluous or in vain. If an animal is protected by the possession of tusks it does not require horns, and vice versa. The correlation of a multiple stomach with deficient development of the teeth, as in ruminants, is accounted for by saying that the animal needs its complex stomach to make up for the shortcomings of its teeth. De Partibus, 3, 14, 674b. Other examples of correlation were not susceptible of this explanation in terms of final causes. He lays stress on the fact, in the main true, of the inverse development of horns and front teeth in the upper jaw, exemplified in ruminants. He explains the fact in this way. Teeth and horns are formed from earthy matter in the body, and there is not enough to form both teeth and horns, so nature by subtracting from the teeth adds to the horns, the nutriment which in most animals goes to the former being here spent on the augmentation of the latter. De partibus, 3, 2, 664a, trans. Ogle. A similar kind of explanation is offered of the fact that Selachia have cartilage instead of bone. In these Selachia nature has used all the earthy matter on the skin, i.e., on the placoid scales, and she is unable to allot to many different parts one and the same superfluity of material. De partibus, 2, 9, 655a, trans. Ogle. Speaking generally, nature invariably gives to one part what she subtracts from another. Loccit, 2, 14, 658a. This thought reappears again in the 19th century in Geoffroy Saint Hilaire's Loi de Balancement and also in Goethe's writings on morphology. For Aristotle it meant that nature was limited by the nature of her means, that finality was limited by necessity. Thus in the larger animals there is an excess of earthy matter, as a necessary result of the material nature of the animal. This excess is turned by nature to good account, but there is not enough to serve both for teeth and for horns. Loccit, 3, 2, 663b. But there are other instances of correlation which seem to have taxed even Aristotle's ingenuity beyond its powers. Thus he knew that all animals, meaning viviparous quadrupeds, with no front teeth in the upper jaw have cotyledons on their fetal membranes, and that most animals which have front teeth in both jaws and no horns have no cotyledons. De Generatione, 2, 7. He offers no explanation of this, but accepts it as a fact. We may conveniently refer here to one or two other ideas of Aristotle regarding the causes of form. He makes the profound remark that the possible range of form of an organ is limited to some extent by its existing differentiation. Thus he explains the absence of external, projecting, ears in birds and reptiles by the fact that their skin is hard and does not easily take on the form of an external ear. De partibus, 2, 12. The fact of the inverse correlation is certain, the explanation is, though very vague, probably correct. In one passage of the De Partibus Aristotle clearly enunciates the principle of the division of labor, afterwards emphasized by H. Milne Edwards. In some insects, he says, the proboscis combines the functions of a tongue and a sting, in others the tongue and the sting are quite separate. Now it is better, he goes on, that one and the same instrument shall not be made to serve several dissimilar ends, but that there shall be one organ to serve as a weapon, which can then be very sharp, and a distinct one to serve as a tongue, which can then be of spongy texture and fit to absorb nutriment. Whenever, therefore, nature is able to provide two separate instruments for two separate uses, without the one hampering the other, she does so, instead of acting like a coppersmith who for cheapness makes a spit and lamp holder in 1, 4, 6, 683a. 5. The first sentence of the Historia Animalium formulates, with that simplicity and directness which is so characteristic of Aristotle, the distinction between homogeneous and heterogeneous parts, in the mass the distinction between tissues and organs. Some parts of animals are simple, and these can be divided into like parts, as flesh into pieces of flesh. Others are compound, and cannot be divided into like parts, as the hand cannot be divided into hands, nor the face into faces. All the compound parts also are made up of simple parts, the hand, for example, of flesh and sinew and bone. Cresswell, Loccit, p. 1. In the De Partibus Animalium he broadens the conception by adding another form of composition. Now there are, he says, 3 degrees of composition, and of these the first in order, as all will allow, is composition out of what some call the elements, such as earth, air, water, fire. The second degree of composition is that by which the homogeneous parts of animals, such as bone, flesh, and the like, are constituted out of the primary substances. The third and last stage is the composition which forms the heterogeneous parts, such as face, hand, and the rest. 2. 1. 646a, trans. Ogle. In the Historia Animalium the homogeneous parts are divided into, 1. The soft and moist, or fluid, such as blood, serum, flesh, fat, suet, marrow, semen, gall, milk, phlegm, faces and urine, and, 2. The hard and dry, or solid, such as sinew, vein, hair, bone, cartilage, nail, and horn. It would appear from this enumeration that Aristotle's distinction of simple and complex parts does not altogether coincide with our distinction of tissues and organs. We should not call vein a tissue, nor do we include under this heading non-living secretions. But in the De Partibus Animalium Aristotle, while still holding to the distinction set forth above, is alive to the fact that his simple parts include several different sorts of substances. He distinguishes among the homogeneous parts 3 sets. The first of these comprises the tissues out of which the heterogeneous parts are constructed, example flesh and bone. The second set form the nutriment of the parts, and are invariably fluid, while the third set are the residue of the second and constitute the residual excretions of the body. 2. 647b. He sees clearly the difficulty of calling vein or blood vessel a simple part, for while a blood vessel and a part of it are both blood vessel, as we should say vascular tissue, yet a part of a blood vessel is not a blood vessel. There is form suprad to homogeneity of structure. 2. 647b. Similarly for the heart and the other viscera. The heart, like the other viscera, is one of the homogeneous parts, for, if cut up, its pieces are homogeneous in substance with each other. But it is at the same time heterogeneous in virtue of its definite configuration. 2. 1. 647a, trans. Ogle. Aristotle, therefore, came very near our conception of tissue. He was of course not a histologist. He describes not the structure of tissues, which he could not know, but rather their distribution within the organism. His section on the homogeneous parts of sanguine, Historia Animalium, 3, second half, is largely a comparative topographical anatomy. In it, for instance, he describes the venous and skeletal systems. This distinction which Aristotle drew plays an important part in all his writings on animals, particularly in his theory of development. It was a distinction of immense value, and is full of meaning even at the present day. No one has ever given a better definition of organ than is implied in Aristotle's description of the heterogeneous parts. The capacity of action resides in the compound parts. Cresswell, LOCCIT, p. 7. The heterogeneous parts were distinguished by the faculty of doing something. They were the active or executive parts. The homogeneous parts were distinguished mainly by physical characters, degeneratione, I. 18, but certain of them had other than purely physical properties. They were the organs of touch, De Partibus, 2, 1, 647a. 6. In a passage in the Degeneratione, 2, 3, Aristotle says that the embryo is an animal before it is a particular animal, that the general characters appear before the special. This is a foreshadowing of the essential point in von Bayer's law, see chap 9 below. He considers also that tissues arise before organs. The homogeneous parts are anterior genetically to the heterogeneous parts and posterior to the elementary material, de partibus, 2, 1, 646b. 7. We meet in Aristotle an idea which later acquired considerable vogue, that of the échelle d'êtres, or scale of beings, that organisms, or even all objects organic or inorganic, can be arranged in a single ascending series. The idea is a common one. Its first literary expression is found perhaps in primitive creation myths, in which inorganic things are created before organic, and plants before animals. It may be recognized also in Anaximander's theory that land animals arose from aquatic animals, more clearly still in Anaxagoras' theory that life took its origin on this globe from vegetable germs which fell to earth with the rain. Anaxagoras considered animals higher in the scale than plants, for while the latter participated in pleasure, when they grew, and pain, when they lost their leaves, animals had in addition nous. In Empedocles' theory of evolution, the vegetable world preceded the animal. Plato, in the Timaeus, describes the whole organic world as being formed by degradation from man, who is created first. Man sinks first into woman, then into brute form, traversing all the stages from the higher to the lower animals, and becoming finally a plant. This is a reversal of the more usual notion, but the idea of gradation is equally present. Aristotle seems not to have believed in any transformation of species, but he saw that nature passes gradually from inanimate to animate things without a clear dividing line. The race of plants succeeds immediately that of inanimate objects, Cresswell, LOCCIT, p. 94. Within the organic realm the passage from plants to animals is gradual. Some creatures, for example, the sea anemones and sponges, might belong to either class. Aristotle recognized also a natural series among the groups of animals, a series of increasing complexity of structure. He begins his study of structure with man, who is the most intricate, and then takes up in turn viviparous and oviparous quadrupeds, then birds, then fishes. After the sanguini he considers the exsanguini, and of the latter first the most highly organized, the cephalopods, and last the simplest, the lower members of his class of the testacea. In treating of generation, in Histori Animalium, v. he reverses this order. In the De Generatione, Book 2, 1, there is given another serial arrangement of animals, this time in relation to their manner of reproduction. There is a gradation, he says, of the following kind: 1. Internally viviparous sanguini producing a perfect animal. 2. Externally viviparous sanguini. 3. Oviparous sanguini producing a perfect egg. 4. Animals producing an imperfect egg, one which increases in size after being laid. 5. Insects, producing a scolex, or grub. In Aristotle's view the gradation of organic forms is the consequence, not the cause, of the gradation observable in their activities. Plants have no work to do beside nutrition, growth, and reproduction, they possess only the nutritive soul. Animals possess in addition sensation and the sensitive or perceptive soul. Their manner of life differs in their having pleasure in sexual intercourse, in their mode of parturition and rearing their young. Histori Anim, 8, trans. Cresswell, p. 195. Man alone has the rational soul in addition to the two lower kinds. As it is put in the De Partibus, 2, 10, 656a, trans. Ogle, plants, again, inasmuch as they are without locomotion, present no great variety in their heterogeneous parts. 4. Where the functions are but few, few also are the organs required to effect them. Animals, however, that not only live but feel, present a greater multiformity of parts, and this diversity is greater in some animals than in others, being most varied in those to whose share has fallen not mere life but life of high degree. Now such an animal is man. With the great exception of Aristotle, the philosophers of Greece and Rome made little contribution to morphological theory. Passing mention may be made of the atomists Leucippus, Democritus, and their great disciple Lucretius, who in his magnificent poem De Natura Rerum gave impassioned expression to the materialistic conception of the universe. But the full effect of materialism upon morphology does not become apparent till the rise of physiology in the 17th and 18th centuries, and reaches its culmination in the 19th century. The evolutionary ideas of Lucretius exercised no immediate influence upon the development of morphology. 1 E. Zeller, Greek Philosophy, ENG Trans, I, 522 FN, London 1881. Other particulars as to Alcmaeon in T. Gompertz, Greek Thinkers, ENG Trans, I, London, 1901. 2 Zeller, LOCCIT, I, p. 297. 3 Gompertz, LOCCIT, I, p. 244. 4 R. Burckhardt, Biologie u Humanismus, p. 85, Jena, 1907. 5 See the interesting account of Aristotle's biological work in Professor Darcy W. Thompson's Herbert Spencer Lecture, 1913, and his translation of the Historia Animalium in the Oxford series. 6 On Aristotle's Forerunners, C. R. Burckhardt, Das Koisktersystem, in Vorstufe des Zoologischen Systematik de Aristoteles. Verh. Naderf. Guess. Basel, XX, 1904. 7 T. E. Lones, Aristotle's Researches in Natural Science, pages 82-3, London, 1912. 8 De Partibus Animalium, I, 4, 644 A Trans. W. Ogle, Oxford, 1911. Chapter 2 Comparative Anatomy Before Cuvier. For 2000 years after Aristotle little advance was made upon his comparative anatomy. Knowledge of the human body was increased not long after his death by Herophilus and Erasistratus, but not even Galen more than 4 centuries later made any essential additions to Aristotle's anatomy. During the Middle Ages, particularly after the introduction to Europe in the 13th century of the Arab texts and commentaries, Aristotle dominated men's thoughts of nature. The commentary of Albertus Magnus, based upon that of Avicenna, did much to impose Aristotle upon the learned world. Albertus seems to have contented himself with following closely in the footsteps of his master. There are noted, however, by Bonnier certain improvements made by Albertus on Aristotle's view of the seriation of living things. He is the first, writes Bonnier, to take the correct view that fungi are lower plants allied to the most lowly organized animals. From this point there start, for Albertus Magnus, 2 series of living creatures, and he regards the plant series as culminating in the trees which have well-developed flowers. 9 Aristotle's influence is predominant also in the work of Edward Wotton, 1492-1555, who in his book De Differentiis Animalium adopted a classification similar to that proposed by Aristotle. He too laid stress upon the gradation shown from the lower to the higher forms. In the 16th century, 2 groups of men helped to lay foundations for a future science of comparative anatomy: the great Italian anatomists Vesalius, Philoppius, and Fabricius, and the first systematists, though their systems were little more than catalogues, Rondeletius, Aldrovandus, and Gessner. The anatomists, however, took little interest in problems of pure morphology. The anatomy of the human body was for them simply the necessary preliminary of the discovery of the functions of the parts. They were quite as much physiologists as anatomists. One of them, Fabricius, made observations on the development of the chick, 1615. Harvey, who was a pupil of Fabricius, likewise published an account of the embryology of the chick. 10 In his philosophy and habit of thought, Harvey was a follower of Aristotle. It is worth noting that in his Exercitations Anatomicae de Motu Cordis, 1628, there is a passage which dimly foreshadows the law of recapitulation in development, which later had so much vogue. 11 A stimulating contribution to comparative anatomy was made by Belin 12, who published in 1555 a Histoire de la nature des oiseaux, in which he showed opposite one another a skeleton of a bird and of a mammal, giving the same names to homologous bones. The anatomy of animals other than man was indeed not altogether neglected at this time. Coiter, 1535–1600, studied the anatomy of vertebrates, discovering among other things the fibrous structure of the brain. Carlo Ruini of Bologna wrote in 1598 a book on the anatomy of the horse. 13 Somewhat later Severino, professor at Naples, dissected many animals and came to the conclusion that they were built upon the same plan as man. 14 Willis, of Oxford and London, in his Cerebri Anatome, 1659, recognized the necessity for comparative study of the structure of the brain. He found out that the brain of man is very like that of other mammals, the brain of birds, on the contrary, like that of fishes. 15 He described the anatomy of the oyster and the crayfish. He had, however, not much feeling for morphology. The foundation of the Jardin de Plantes at Paris in 1626 and the subsequent addition to it of a museum of natural history and a menagerie gave a great impulse to the study of comparative anatomy by supplying a rich material for dissection. Advantage was taken of these facilities, particularly by Claude Perrault and Duvernay. 16 In a volume entitled De la mécanique des animaux, Perrault recognizes clearly the idea of unity of type, and even pushes it too far, seeking to prove that in plants there exists an arterial system and veins provided with valves. 17 The beginning of the 17th century saw the invention of the microscope, which was to have such an enormous influence upon the development of biological studies. It did not come into scientific use until well on in the middle of the century. Just before it came into use, Francis Glisson, 1597–1677, an Englishman, gave in the introduction to his treatise on the liver an account of the notions then current on the structure of organic bodies. He classifies the parts as similar and organic, the former determined by their material, the latter by the form which they assume. The similar parts are divided into the sanguineous or rich in blood and the spermatic. Both sets are further subdivided according to their physical characters. 18 The latter, for instance, into the hard, soft, and tensile tissues. The classification resembles greatly that propounded by Aristotle, though it is notably inferior in the details of its working out. For Aristotle, as for all anatomists before the days of the microscope, the tissues were not much more than inorganic substances, differing from one another in texture, in hardness, and other physical properties. They possessed indeed properties, such as contractility, which were not inorganic, but as far as their visible structure was concerned there was little to raise them above the inorganic level. The application of the microscope changed all that, for it revealed in the tissues an organic structure as complex in its grade as the gross and visible structure of the whole organism. Of the four men who first made adequate use of the new aid, Malpighi, Hooke, Leeuwenhoek, and Swammerdam, the first named contributed the most to make current the new conceptions of organic structure. He studied in some detail the development of the chick. He described the minute structure of the lungs, 1661, demonstrating for the first time, by his discovery of the capillaries, the connection of the arteries with the veins. In his work, De Viscerum Structura, 1666, he describes the histology of the spleen, the kidney, the liver, and the cortex of the brain, establishing among other things the fact that the liver was really a conglomerate gland, and discovering the Malpighian bodies in the kidney. This work was done on a broad comparative basis. Since in the higher, more perfect, red-blooded animals, the simplicity of their structure is wont to be involved by many obscurities, it is necessary that we should approach the subject by the observation of the lower, imperfect animals. 19 So he wrote in the De Viscerum Structura, and accordingly he studied the liver first in the snail, then in fishes, reptiles, mammals, and finally man. In the introduction to his Anatome Plantarum, 1675, in which he laid the foundations of plant histology, he vindicates the comparative method in the following words: In the enthusiasm of youth I applied myself to anatomy, and although I was interested in particular problems, yet I dared to pry into them in the higher animals. But since these matters enveloped in peculiar mystery still lie in obscurity, they require the comparison of simpler conditions, and so the investigation of insects 20 at once attracted me. Finally, since this also has its own difficulties, I applied my mind to the study of plants, intending after prolonged occupation with this domain, to retrace my steps by way of the vegetable kingdom, and get back to my former studies. But perhaps not even this will be sufficient, since the simpler world of minerals and the elements should have been taken first. In this case, however, the undertaking becomes enormous and far beyond my powers. 21 There is something fine in this life of broad outlines, devoted wholeheartedly to an idea, to a plan of research, which required a lifetime to carry out. An important histological discovery dating from this time is that of the finer structure of muscle, made by Stenson, or Steno, in 1664. He described the structure of muscle fibers, resolving them into their constituent fibrils. To the microscope we owe not only histology but the comparative anatomy of the lower animals. Throughout the 17th and 18th centuries the discovery of structure in the lower animals went on continuously, as may be read in any history of zoology 22. We content ourselves here with mentioning only some representative names. In the 17th century Leeuwenhoek, applying the microscope almost at random, discovered fact after fact, his most famous discovery being that of the spermatic animal culls. Swammerdam studied the metamorphoses of insects and made wonderfully minute dissections of all sorts of animals, snails, and insects particularly. He described also the development of the frog. It is curious to see what a grip his conception of metamorphosis had upon him when he homologises the stages of the frog's development with the egg, the worm, and the nymph of insects. Book of Nature, p. 104, ENG trans. 1785. He even speaks of the human embryo as being at a certain stage a manvermicle. In the 18th century, Reaumur and Bonnet continued the minute study of insects, laying more stress, however, on their habits and physiology than upon their anatomy. Lyonnais made a most laborious investigation of the anatomy of the willow caterpillar, 1762. John Hunter, 1728–93, dissected all kinds of animals, from holothurians to whales. His interest was, however, that of the physiologist, and he was not specially interested in problems of form. It is interesting to note a formulation in somewhat confused language of the recapitulation theory. The passage occurs in his description of the drawings he made to illustrate the development of the chick. It is quoted in full by Owen, J. Hunter, Observations on Certain Parts of the Animal Economy, with notes by Richard Owen. London, 1837. Preface, PXXVI. We give here the last and clearest sentence. If we were to take a series of animals from the more imperfect to the perfect, we should probably find an imperfect animal corresponding with some stage of the most perfect. The tendency of the time was not towards morphology, but rather to general natural history and to systematics, the latter under the powerful influence of Linnaeus, 1707 to 1778. The former tendency is well represented by Réaumur, 1683 to 1757, with his observations on insects, the digestion of birds, the regeneration of the crayfish's legs, and 100 other matters. To this tendency belong also Tremblay's famous experiments on Hydra, 1744, and Rosel von Rosenhoff's Insektenbelustigung, 1746 to 1761. Bonnet, 1720 to 1793, deserves special mention here, since in his Traité d'Insectologie, 1745, and more fully in his Contemplation de la Nature, 1764, he gives the most complete expression to the idea of the échelle des êtres. This idea seems to have taken complete possession of his imagination. He extends it to the universe. Every world has its own scale of beings, and all the scales when joined together form but one, which then contains all the possible orders of perfection. At the end of the preface to his Traité d'Insectologie, Ouvres, I, 1779, he gives a long table, headed Idée d'une échelle des êtres naturels, and rather resembling a ladder, on the rungs of which the following names appear: man, shell, fish, stones, orangutan, tube worms, figured stones, ape, clothes worms, crystals, quadrupeds, insects, salts, flying squirrel, gall insects, vitrioles, bat, tenia, ostrich, polyps, metals, sea nettles, birds, sensitive plant, half metals, aquatic birds, amphibious birds, plants, sulfurs, flying fish, lichens, bitumens, molds, fish, fungi, agarics, earths, creeping fish, truffles, pure earth, eels, corals, and coralloids, water serpents, lithophytes, water, asbestos, serpents, talc, gypsums, air, slugs, selenite, slates, snails, fire, more subtle matter. The nature of the transitional forms which he inserts between his principal classes show very clearly his entire lack of morphological insight. The transitions are functional. The positions assigned to clothes moths and corals are very curious. The whole scheme, so fantastic in its details, was largely influenced by Leibniz's continuity philosophy, and is in no way an improvement on the older and saner Aristotelian scheme. Robinet, in the 5th volume of his book De la Nature, 1761-6, foreshadows the somewhat similar views of the German transcendentalists. All beings, he writes, have been conceived and formed on one single plan, of which they are the endlessly graduated variations. This prototype is the human form, the metamorphoses of which are to be considered as so many steps towards the most excellent form of being. 23. The idea of a gradation of beings appears also in Buffon, 1707-1788, but here it takes more definitely its true character as a functional gradation. 24. Since everything in nature shades into everything else, he says, it is possible to establish a scale for judging of the degrees of the intrinsic qualities of every animal. 25. He is quite well aware that the groups of invertebrates are different in structural plan from the vertebrates. The animal kingdom includes various animated beings, whose organization is very different from our own and from that of the animals whose body is similarly constructed to ours. 26. He limits himself to a consideration of the vertebrates, deeming that the economy of an oyster ought not to form part of his subject matter. He has a clear perception of the unity of plan which reigns throughout the vertebrate series 27. What is new in Buffon is his interpretation of the unity of plan. For the first time we find clearly expressed the thought that unity of plan is to be explained by community of origin. Buffon's utterances on this point are, as is well known, somewhat vacillating. The famous passage, however, which occurs in his account of the ass shows pretty clearly that Buffon saw no theoretical objection to the descent of all the varied species of animals from one single form. Once admit, he argues, that within the bounds of a single family one species may originate from the type species by degeneration, then one might reasonably suppose that from a single being nature could in time produce all the other organized beings. 28 Elsewhere, example in the Discours de la Degeneration de Animaux 29, Buffon expresses himself with more caution. He finds that it is possible to reduce the 200 species of quadrupeds which he has described to quite a small number of families from which it is not impossible that all the rest are derived. 30 Within each of the families the species branch off from a parent or type species. This we may note is a great advance on the linear arrangement implied in the idea of an échelle d'Edris. 31 It is a mistake to suppose that Buffon was par excellence a maker of hypotheses. On the contrary, he saw things very sanely and with a very open mind. He expressly mentions the great difficulties which one encounters in supposing that one species may arise from another by degeneration. How does it happen that two individuals degenerate just in the right direction and to the right stage so as to be capable of breeding together? How is it that one does not find intermediate links between species? One is reminded of the objections, not altogether without validity, which were made to the Darwinian theory in its early days. I cannot agree with those who think that Buffon was an out-and-out evolutionist, who concealed his opinions for fear of the Church. No doubt he did trim his sails the palpably insincere mais non, ils certain, par la révélation, que tous les animaux ont également participé à la grâce de la création. 32 Following hard upon the too bold hypothesis of the origin of all species from a single one, is proof of it. But he was too sane and matter-of-fact a thinker to go much beyond his facts, and his evolution doctrine remained always tentative. One thing, however, he was sure of, that evolution would give a rational foundation to the classification which, almost in spite of himself, he recognized in nature. If, and only if, the species of one family originated from a single type species, could families be founded rationally, avec raison. Buffon was, curiously enough, rather unwilling to recognize any systematic unit higher than the species. Strictly speaking, there are only individuals in nature, but there are also groups of individuals which resemble one another from generation to generation and are able to breed together. These are species. Buffon adheres to the genetic definition of species, and the species is a much more definite unit than the genus, the order, the class, which are not divisions imposed by us upon nature. Species are definitely discontinuous. 33 And this is the only discontinuity which nature shows us. Buffon put his views into practice in his Histoire naturelle, where he describes species after species, never uniting them into larger groups. We have seen, however, how the facts forced upon him the conception of the family. Buffon was no morphologist. He left to Daubenton what one might call the dirty work of his book, the dissection and minute description of the animals treated. But Buffon was a man of genius, and accordingly his ideas on morphology are fresh and illuminating. Few naturalists have been so free from the prejudices and traditions of their trade. He makes in the Discours sur la nature des animaux 34 a distinction, which Bichat and Cuvier later developed with much profit, between the animal and the vegetative part of animals. 35 The vegetative or organic functions go on continuously, even in sleep, and are performed by the internal organs, of which the heart is the central one. The active waking life of the animal, that part of its life which distinguishes it from the plant, involves the external parts, the sense organs and the extremities. An animal is, as it were, made up of a complex of organs performing the vegetative functions, assimilation, growth, and reproduction, surrounded by an envelope formed by the limbs, the sense organs, the nerves, and the brain, which is the center of this envelope. 36 animals may differ from one another enormously in the external parts, particularly in the appendicular skeleton, without showing any great difference in the plan and arrangement of their internal organs. Quadrupeds, cetacea, birds, amphibians, and fish are as unlike as possible in external form and in the shape of their limbs, but they all resemble one another in their internal organs. Let the internal organs change, however, the external parts will change infinitely more, and you will get another animal, an animal of a totally different nature. Thus an insect has a most singular internal economy, and, in consequence, you find it is in every point different from any vertebrate animal. In this contrast, on the whole justified, between the importance of variations in the vegetative and variations in the animal parts, one may see without doing violence to Buffon's thought, an indication of the difference between homology and analogy. It is usually in the external parts, in the organs by which the animal adapts itself to its environment, that one meets with the greatest number of analogical resemblances. This contrast of vegetative and animal parts and their relative importance for the discovery of affinities was at any rate a considerable step towards an analysis of the concept of unity of plan. To Xavier Bichat, 1771–1802, belongs the credit of working out in detail the distinction drawn by Aristotle and Buffon between the animal and the vegetative functions. Bichat was not a comparative anatomist, his interest lay in human anatomy, normal and pathological. So his views are drawn chiefly from the consideration of human structure. He classifies functions into those relating to the individual and those relating to the species. The functions pertaining to the individual may be divided into those of the animal and those of the organic life. 37 I call animal life that order of functions which connects us with surrounding bodies, signifying thereby that this order belongs only to animals, Peele's Xiath. Its organs are the afferent and efferent nerves, the brain, the sense organs, and the voluntary muscles. The brain is its central organ. Digestion, circulation, respiration, exhalation, absorption, secretion, nutrition, calorification, or production of animal heat, compose organic life, whose principal and central organ is the heart, Peele's 6. The contrast of the animal and the organic life runs through all Bichat's work. It receives classical expression in his Recherches physiologiques sur la vie et la mort, 1800. The plant and the animal stand for two different modes of living. The plant lives within itself, and has with the external world only relations of nutrition. The animal adds to this organic life a life of active relation with surrounding things. 3rd ed. 1805, p. 2. One might almost say that the plant is the framework, the foundation of the animal, and that to form the animal it sufficed to cover this foundation with a system of organs fitted to establish relations with the world outside. It follows that the functions of the animal form two quite distinct classes. One class consists in a continual succession of assimilation and excretion. Through these functions the animal incessantly transforms into its own substance the molecules of surrounding bodies, later to reject these molecules when they have become heterogeneous to it. Through this first class of functions the animal exists only within itself. Through the other class it exists outside. It is an inhabitant of the world, and not, like the plant, of the place which saw its birth. The animal feels and perceives its surroundings, reflects its sensations, moves of its own will under their influence, and, as a rule, can communicate by its voice its desires and its fears, its pleasures, or its pains. I call organic life the sum of the functions of the former class, for all organized creatures, plants, or animals, possess them to a more or less marked degree, and organized structure is the sole condition necessary to their exercise. The combined functions of the second class form the animal life, so named because it is the exclusive attribute of the animal kingdom, pages 2 to 3. In both lives there is a double movement, in the animal life from the periphery to the center and from the center to the periphery, in the organic life also from the exterior to the interior and back again, but here a movement of composition and decomposition. As the brain mediates between sensation and motion, so the vascular system is the go-between of the organs of assimilation and the organs of dissimilation. The most essential structural difference between the organs of animal life and the organs of organic life is, in man and the higher animals at least, the symmetry of the one set and the irregularity of the other. Compare the symmetry of the nerves and muscles of the animal life with the asymmetrical disposition of the visceral muscles and the sympathetic nerves, which belong to the organic life. Noteworthy differences exist between the two lives with respect to the influence of habit. Everything in the animal life is under the dominion of habit. Habit dulls sensation, habit strengthens the judgment. In the organic life, on the contrary, habit exercises no influence. The difference comes out clearly in the development of the individual. The organs of the organic life attain their full perfection independently of use, the organs of the animal life require an education, and without education they do not reach perfection. LOCCIT, p. 127. Bichat was the founder of what was known for a time as general anatomy, the study of the constituent tissues of the body in health and disease. His classification of tissues was macroscopical and physiological. He relied upon texture and function in distinguishing them rather than upon microscopical structure. The tissues he distinguished are as follows: 38.1. The cellular membrane. 12. Fibrocartilage. 2 nerves of animal life. 13 muscles of organic life. 3 nerves of organic life. 14 muscles of animal life. 4 arteries. 15 mucous membrane. 5 veins. 16 serous membrane. 6 exhalants. 17 synovial membrane. 7 absorbents and glands. 18 the glands. 8 bones. 19 the dermis. 9 medulla. 20 epidermis. 10 cartilage. 21 cutis. 11 fibrous tissue. The cellular membrane seems to mean undifferentiated connective tissue. Exhalants are imperceptible tubes arising from the capillaries and secreting fat, serum, marrow, etc. The absorbents and glands are the lymphatics and the lymphatic glands. In Bichat's eyes, this resolution of the organism into tissues had a deeper significance than any separation into organs, for to each tissue must be attributed a vie propre, an individual and peculiar life. When we study a function, we must consider the complicated organ which performs it in a general way, but if we would be instructed in the properties and life of that organ, we must absolutely resolve it into its constituent parts. 39. The tissues have, too, a great importance for pathology, for diseases are often diseases of tissues rather than of organs. 49. Le Monde Végétal, p. 41, Paris, 1907. 10 Exercitations de Generatione Animalium, 1651. For an account of Harvey's work on generation and development, cm. Radl's Masterly Geschichte der biologischen Theorie n. I, pages 31-8, Leipzig, 1905. 11. The passage runs: Sic natura perfecta et divina nihil faciens frustra, nec quipium animali cor attidit, ubi non erat opus, nec prius quam esset ejus usus, Facet, sed istum gradibus in format ioni cujuscumque animalis, transcens per omnium animalium constitutions, ut edidicam, ovum, vermem, fetum, perfectionem in singulis acquirit. 12 C. I. Geoffroy Saint Hilaire, Essays de Zoologie Générale, p. 71, Paris, 1841. 13 M. Foster, Lectures on the History of Physiology, Cambridge, p. 53, 1901. 14 Zootomia Democratia, Nuremberg, 1645, Antiperipecius, SCU de Respiratione Piscium, Amsterdam, 1661. 15 Radl, LOCCIT, I, p. 50. 16 Perrault et Duvernay, Memoires pour servir à l'histoire des animaux, Paris, 1699. 17 Fusai, Nature et Sciences Naturelles, Paris, p. 76, and 18 Foster, LOCCIT, p. 85. 19 Transaction by Foster, LOCCIT, p. 113. 20 He made a careful study of the silkworm. 21 Itanem, ferventi actatus calori, anatomica aggressus, licet circa peculiaria fuorum solicitus, in perfectioribus tamen hec rumori sum agius. Verum, cum hec properis tenebris obscura jacent, simplicium analogismo agent, ind insectorum indago illico ericit, qui cum et ipsa suis habi difficultates ad plantarum perquisitionem animum post remo agici, ut diu hoc lustrato mundo gressu retroacto vegetantis naturi gradu, ad prima studia iter mei apparirem. Sed nec forte hoc ipsum sufficiat cum simplicior mineralium elementarum mundus praeire debit. At in immensum excrescit opus, et mis viribus omino impar, opera omnia, I, p. 1, London, 1686. 22 See particularly E. Radl, LOCCIT. 1 Thiel. J. V. Karras, Geschichte Zoologie, München, 1872. 23 For a good historical account of the gradation theories see Thienmann's paper in the Zoologische Annalen, Würzburg, 3, pages 185 to 274, 1910, from which the quotation from Robinet is taken. 24 Histoire naturelle, I, p. 13, 2, p. 9, 4, p. 101, and 14, pages 28 to 9, 1749 and later. 25 No translation can render the beauty of the original cum tout se fate etk tout est par nuance dans la nature. 4, p. 101. 26 History nat. 4, p. 5. 27 See particularly his comparison of the skeleton of the horse with that of man. History nat. 4, p. 381, also p. 13. 28 LOCCIT, p. 382. 29 Tome 14, pages 311 to 374. 30 Tome 14, p. 358. 31 See also Oizo, Tome I, pages 394, 395. Pallas in 1766 adopted for the whole animal kingdom this branching arrangement. 32 But this cannot be, for it is certain by revelation that all animals have equally participated in the grace of creation. 33 4, p. 385. 34 4, pages 3 to 110. 35 It has been revived in our own days by Bergson, Matière et Memoire, p. 57. 36 4, pages 7 to 15. 37 Anatomie Générale, Paris, 1801, ENG trans. 1824 38 Anatomie Générale, ENG trans, I, P. Lee. 39 Anatomie Générale, ENG trans, I, P. Lee. 40 LOCCIT, I, Section 7. Chapter 3 Cuvier was perhaps the greatest of comparative anatomists. His work is, in the best sense of the word, classical. Like all his predecessors, like Aristotle, like the Italian anatomists, Cuvier studied structure and function together, even gave function the primacy. Some functions, he says 41 are common to all organized bodies: origin by generation, growth by nutrition, and by death. There are also secondary functions. Of these the most important, in animals at least, are the faculties of feeling and moving. These two faculties are necessarily bound up together. If nature has given animals sensation, she must also have given them the power of movement, the power to flee from what is harmful and draw near to what is good. These two faculties determine all the others. A creature that feels and moves requires a stomach to carry food in. Food requires instruments to divide it, liquids to digest it. Plants, which do not feel and do not move, have no need of a stomach, but have roots instead. Thus the animal functions of feeling and moving determine the character of the organs of the second order, the organs of digestion. These in their turn are prior to the organs of circulation, which are a means to the end of distributing the nutrient fluid or blood to all parts of the body. These organs of the third order are not only dependent on those of the second order, but are also not even necessary, for many animals are without them. Only animals with a circulatory system can have definite breathing organs, lungs or gills. Plants, and animals without a circulation, breathe by their whole surface. There is accordingly a rational order of functions, and therefore of the systems of organs which perform them. The most important are the animal functions, with their great organ system, the neuromuscular mechanism. Then come the digestive functions, and after them, and in a sense accessory to them, the functions and organs of circulation and respiration. The last three may be grouped as the vital functions. The animal functions not only determine the character of the vital functions, but influence also the primary faculty of generation, for animals' power of movement has rendered their mode of fecundation more simple, has therefore had an effect on their organs of generation. This division into animal and vital functions recalls Buffon's and Bichat's distinction of the animal and the vegetative lives. Cuvier apparently took this idea from Buffon, for he says that a plant is an animal that sleeps 42, but the idea is as old as Aristotle, who discusses the sleep of embryos and of plants in the last book of the De Generatione Animalium. The distinction between animal and vegetative life is, of course, based for Aristotle in the difference between the psi upsilon chi iota sigma theta eta tau iota kappa and the psi upsilon chi theta rho pi tau iota kappa. Cuvier, like Aristotle, Buffon, and Bichat, makes the heart the center of the vegetative organs. It is important to note that Cuvier puts function before structure, and infers from function what the organ will be. Plants, he writes, having few faculties, have a very simple organization. 43 It is only after having discussed and classified functions that Cuvier goes on to examine organs. First, his views on the composition of the animal body. Aristotle distinguished 3 degrees of composition: the elements, the homogeneous parts, and the heterogeneous parts or organs. Cuvier does the same. Some small advance has been made in the 2000 years interval, due in the first place to the progress of chemistry, and in the second to the invention of the microscope. To the first circumstance Cuvier owes his knowledge that the inorganic substances forming the first degree of composition are principally C, N, H, O, and P, combined to form albumin, fibrin, and the like, which are in their turn combined to form the solids and fluids of the body. To the latter circumstance Cuvier owes the statement that the finest fragments into which mechanical division can resolve the organism are little flakes and filaments, which, joined up loosely together, form a cellulosity. The discovery of the true cellular nature of animal tissues did not come till much later, till some years after Cuvier's death in 1832. Knowledge of histological detail was, however, considerable by the beginning of the 19th century. Cuvier knew, for example, that each muscle fiber has its own nerve fiber. But he gives no elaborate account of the homogeneous parts, no detailed histology. On the other hand, his treatment of the heterogeneous parts or organs is detailed and masterly. 44 The main systems of organs are, in order of importance, the nervous and muscular, the digestive, the circulatory, and the respiratory. Each organ or system of organs may have many forms. If any form of any organ could exist in combination with any form of all the others, there would be an enormous number of combinations theoretically possible. But these combinations do not all exist in nature, for organs are not merely assembled, rapprochés, but act upon one another, and act all together for a common end. Accordingly, only the combinations that fulfill these conditions exist in nature. Cuvier thus dismisses the question of a science of possible organic forms and considers only the forms or combinations actually existing. This question of the possibility of a theoretical morphology of living things, after the fashion of the morphology of crystals with their 16 possible types, was raised in later years by K. G. Karras, Braun, and Haeckel. Organisms, then, are harmonious combinations of organs, and the harmony is primarily a harmony of functions. Every function depends upon every other, and all are necessary. The harmony of organs and their mutual dependence are the results of the interdependence of function. This thought, the recognition of the functional unity of the organism, is the fundamental one at the base of all Cuvier's work. Before him men had recognized more or less clearly the harmony of structure and function, and had based much of their work upon this unanalyzed assumption. Cuvier was the first naturalist to raise this thought to the level of a principle peculiar to natural history. It is on this mutual dependence of the functions and the assistance which they lend one to another that are founded the laws that determine the relations of their organs. These laws are as inevitable as the laws of metaphysics and mathematics, for it is evident that a proper harmony between organs that act one upon another is a necessary condition of the existence of the being to which they belong. 45 This rational principle, peculiar to natural history, Cuvier calls the principle of the conditions of existence, for the following reasons: since nothing can exist that does not fulfill the conditions which render its existence possible, the different parts of each being must be coordinated in such a way as to render possible the existence of the being as a whole, not only in itself, but also in its relations with other beings, and the analysis of these conditions often leads to general laws which are as certain as those which are derived from calculation or from experiment. 46 By conditions of existence he means something quite different from what is now commonly understood. The idea of the external conditions of existence, the environment, enters very little into his thought. He is intent on the adaptations of function and organ within the living creature, a point of view rather neglected nowadays, but essential for the understanding of living things. The very condition of existence of a living thing, and part of the essential definition of it, is that its parts work together for the good of the whole. The principle of the adaptedness of parts may be used as an explanatory principle, enabling the naturalist to trace out in detail the interdependence of functions and their organs. When you have discovered how one organ is adapted to another and to the whole, you have gone a certain way towards understanding it. That is using teleology as a regulative principle, in Kant's sense of the word. Cuvier was indeed a teleologist after the fashion of Kant, and there can be no doubt that he was influenced, at least in the exposition of his ideas, by Kant's critic der Urteilskraft, which appeared 10 years before the publication of the Lektions die Anatomie compare. Teleology in Kant's sense is and will always be a necessary postulate of biology. It does not supply an explanation of organic forms and activities, but without it one cannot even begin to understand living things. Adaptedness is the most general fact of life, and innumerable lesser facts can be grouped as particular cases of it, can be, so far, understood. Cuvier's famous principle of correlation, the cornerstone of his work, is simply the practical application to the facts of structure of the principle of functional adaptedness. By the principle of correlation, from one part of an animal, given sufficient knowledge of the structure of its like, you can in a general way construct the whole. This must necessarily be so, for all the organs of an animal form a single system, the parts of which hang together, and act and react upon one another, and no modifications can appear in one part without bringing about corresponding modifications in all the rest. 47. The logical basis of the principle is sound. The functions of the parts are all intimately bound up with one another, and one function cannot vary without bringing in its train corresponding modifications in the others. Structure and function are bound up together, every modification of a function entails therefore the modification of an organ. Hence from the shape of one organ you can infer the shape of the other organs if you have sufficiently extensive empirical knowledge of functions, and of the relation of structure to function in each kind of organ. Given an alimentary canal capable of digesting only flesh, and possessing therefore a certain form, you know that the other functions must be adapted to this particular function of the alimentary canal. The animal must have keen sight, fine smell, speed, agility, and strength in paws and jaws. These particular functions must have correspondingly modified organs, well-developed eyes and ears, claws and teeth. Further, you know from experience that such and such definitely modified organs are invariably found with the carnivorous habit, carnassial teeth, for example, and reduced clavicles. From a carnivorous alimentary canal, then, you can infer with certainty that the animal possessed carnassial teeth and the other structural peculiarities of carnivorous animals, example the peculiar coronoid process of the mandible. From the carnassial tooth you can infer the reduced clavicle, and so on. In a word, the form of the tooth implies the form of the condyle, that of the shoulder blade that of the claws, just as the equation of a curve implies all its properties. 48. Similarly, the great respiratory power of birds is correlated with their great muscular strength, and renders necessary great digestive powers. Hence the correlated structure of lungs, muscles, and their attachments, and alimentary canal, in birds. Not only do systems of organs, by being adjusted to special modifications of function, influence one another, but so also do parts of the same organ. This is noticeably the case with the skeleton, where hardly a facet can vary without the others varying proportionately, so that from one bone you can up to a certain point deduce all the rest. We deduce the necessity, the constancy, of these coexistences of organs from the observed reciprocal influence of their functions. That being established, we can argue from observed constancy of relation between two organs an action of one upon the other, and so be led to a discovery of their functions. But even if we do not discover the functional interdependencies of the parts, we can use the established fact of the constant coexistence of two parts as proof of a functional correlation between them. Correlation is either a rational or an empirical principle, according as we know or do not know the interdependence of function of which it is the expression. Even when we apply the rational principle of correlation, it would be useless in our hands if we had not extensive empirical knowledge. When we use an empirical rule of correlation, we depend entirely upon observation. There are a great many cases, Writes Cuvier 49, where our theoretical knowledge of the relations of forms would not suffice, if it were not filled out by observation, that is to say, there are many cases of correlation not yet explicable in terms of function. From a hoof you can deduce the main characters of herbivores, with a certain amount of assistance from your empirical knowledge of herbivores, but could you from a cloven hoof deduce that the animal is a ruminant, unless you had observed the constancy of relation, not directly explicable in terms of function, between cloven hoofs and chewing the cud? Or could you deduce from the existence of frontal horns that the animal ruminates? Nevertheless, since these relations are constant, they must necessarily have a sufficient cause, but as we are ignorant of this cause, observation must supplement theory. Observation establishes empirical laws which become almost as certain as the rational laws, when they are based upon a sufficient number of observations. But that there exist all the same hidden reasons for all these relations is partly revealed by observation itself, independently of general philosophy. 50. That is to say, even correlations for which no explanation in terms of function can be supplied are probably in reality functional correlations. This may, in some cases, be inferred from the graded correspondence of two sets of organs. For example, ungulates which do not ruminate, and have not a cloven hoof, have a more perfect dentition and more bones in the foot than the true cloven-hoofed ruminants. There is a correlation between the state of development of the teeth and of the foot. This correlation is a graded one, for camels, which have a more perfect dentition than other ruminants, have also a bone more in their tarsus. It seems probable, therefore, that there is some reason, that is, some explanation in terms of function, for this case of correlation. Nevertheless, the fact remains that many correlations are not explicable in terms of function, and the substitution of correlation as an empirical principle for correlation as a rational principle marks for Cuvier a step away from his functional comparative anatomy towards a pure morphology. It is significant that in later times the term correlation has come to be applied more especially to the purely empirical constancies of relation, and has lost most of its functional significance. But the correlation of the parts of an organism is no mere mathematical concept, to be expressed by a coefficient, but something deeper and more vital. Cuvier interpreted the functional dependence of the parts in terms of what we now call the general metabolism. He had a clear vision of the constant movement of molecules in the living tissue, combining and recombining, of the organism taking in and intercalating molecules from outside from the food and rejecting molecules in the excretions, a ceaseless tourbillon vital. This general movement, universal in every part, is so unmistakably the very essence of life that parts separated from a living body straightway die. 51. The organization of the body, the arrangement of its solids and liquids, is adapted to further the tourbillon vital. Each part contributes to this general movement its own particular action and is affected by it in particular ways, with the result that, in every being, life is a unity which results from the mutual action and reaction of all its parts. 52. Cuvier, however, did not resolve life into metabolism, nor reduce vital happenings to the chemical level. The form of organized bodies is more essential than the matter of which they are composed, for the matter changes ceaselessly while the form remains unchanged. It is in form that we must seek the differences between species, and not in the combinations of matter, which are almost the same in all 53. The differences are to be sought at the level of the second and third degrees of composition. The existence of differences of form introduces a new problem, the problem of diversity. There are only a few possible combinations of the principal organs, but as you get down to less important parts the possible scope of variation is greatly increased, and most of the possible variations do exist. Nature seems prodigal of form which needs not to be useful in order to exist. It needs only to be possible, i.e., of such a character that it does not destroy the harmony of the whole. 54. We seize here the relation of the principle of the adaptedness of parts to the problem of the variety of form. The former is in a sense a regulative and conservative principle which lays down limits beyond which variation may not stray. In itself it is not a fountain of change, there must be another cause of change. This thought is of great importance for theories of descent. Cuvier has no theory to account for the variety of form, he contents himself with a classification. There are two main ways of classifying forms. You may classify according to single organs or according to the totality of organs. By the first method you can have as many classifications as you have organs, and the classifications will not necessarily coincide. Thus you can divide animals according to their organs of digestion into two classes, those in which the alimentary canal is a sac with one opening, zoophytes, and those in which the canal has two openings. 55. A curious forestalment, in the rough, of the modern division of metazoa into coelentra and chylometa. It is only by taking single organs that you can arrange animals into long series, and you will have as many series as you take organs. Only in this way can you form any Echeldaedras or graded series, and you can get even this kind of gradation only within each of the big groups formed on a common plan of structure. You can never grade, for example, from invertebrates to vertebrates through intermediate forms. 56, which is perfectly true, in spite of Amphioxus and Balanoglossus. In the Regni animal, Cuvier restricts the application of the idea of the echelle within even narrower limits, refusing to admit its validity within the bounds of the vertebrate phylum, or even within the vertebrate classes. This seems, however, to refer to a seriation of whole organisms and not of organs, so that the possibility of a seriation of organs within a class is not denied. Cuvier was, above all, a positive spirit, and he looked askance at all speculation which went beyond the facts. The pretended scale of beings, he wrote, is only an erroneous application to the totality of creation of partial observations, which have validity only when confined to the sphere within which they were made. 57. This remark, which is after all only just, perfectly expresses Cuvier's attitude to the transcendental theories, and was probably a protest against the sweeping generalizations of his colleague, Étienne Geoffroy Saint-Hilaire. A true classification should be based upon the comparison of all organs, but all organs are not of equal value for classification, nor are all the variations of each organ equally important. In estimating the value of variations, more stress should be laid on function than on form, for only those variations are important which affect the mode of functioning. These are the principles on which Cuvier bases the classification of animals given in the Lecons, Article V, Division de animaux d'après l'ensemble de leur organisation. The scheme of classification actually given in the Lecons recalls curiously that of Aristotle, for there is the same broad division into vertebrates, with red blood, and invertebrates, almost all with white blood. 9 classes altogether are distinguished: mammals, birds, reptiles, fishes, mollusks, crustacea, insects, worms, zoophytes, including echinoderms and coelenterate. A maturer theory and practice of classification is given in the Regni animal of 17 years later. Here the principle of the subordination of characters, which seems to have been first explicitly stated by the younger de Jussreau in his Genera Plantarum, 1789-58, is more clearly recognized. The properties or peculiarities of structure which have the greatest number of relations of incompatibility and coexistence, and therefore influence the whole in the greatest degree, are the important or dominating characters, to which the others must be subordinated in classification. These dominant characters are also the most constant. 59. In deciding which characters are the most important, Cuvier makes use of his fundamental classification of functions and organs into two main sets. The heart and the organs of circulation are a kind of center for the vegetative functions, as the brain and the spinal cord are for the animal functions. 60. These two organ systems vary in harmony, and their characters must form the basis for the delimitation of the great groups. Judged by this standard, there are four principal types of form 61, of which all the others are but modifications. These four types are vertebrates, mollusks, articulates, and radiates. The first three have bilateral, the last has radial symmetry. Vertebrates and mollusks have blood vessels, but articulates show a functional transition from the blood vessel to the tracheal system. Radiates approach the homogeneity of plants, they appear to lack a distinct nervous system and sense organs, and the lowest of them show only a homogeneous pulp which is mobile and sensitive. All four classes are principally distinguished from one another by the broad structural relations of their neuromuscular system, of the organs of the animal functions. Vertebrates have a spinal cord and brain, an internal skeleton built on a definite plan, with an axis and appendages. In mollusks the muscles are attached to the skin and the shell, and the nervous system consists of separate masses. Articulates have a hard external skeleton and jointed limbs, and their nervous system consists of two long ventral cords. Radiates have ill-defined nervous and muscular systems, and in their lowest forms possess the animal functions without the animal organs. This well-rounded classification of animal forms is in a sense the crown of Cuvier's work, for the principle of the subordination of characters, in the interpretation which he gives to it, is a direct application of his principle of functional correlation. Each of the great groups is built upon one plan. The idea of the unity of plan has become for Cuvier a commonplace of his thought, and it is tacitly recognized in all his anatomical work. But he never takes it as a hard and fast principle which must at all costs be imposed upon the facts. Cuvier has become known as the greatest champion of the fixity of species, but it is not often recognized that his attitude to this problem is at least as scientific as that of the evolutionists of his own and later times. No doubt he became dogmatic in his rejection of evolution theory, but he was on sure ground in maintaining that the evolutionists of his day went beyond their facts. He considered that certain forms, species, have reproduced themselves from the origin of things without exceeding the limits of variation. His definition of a species was, the individuals descended from one another or from common parents, together with those that resemble them as much as they resemble one another. 62. These forms are neither produced nor do they change of themselves. Life presupposes their existence, for it cannot arise save in organizations ready prepared for it. 63. He based his rejection of all theories of descent upon the absence of definite evidence for evolution. If species have gradually changed, he argued, one ought to find traces of these gradual modifications. 64. Paleontology does not furnish such traces. Again, the limits of variation, even under domestication, are narrow, and the most extreme variation does not fundamentally alter the specific type. Thus the dog has varied perhaps most of all, in size, in shape, in color. But throughout all these variations the relations of the bones remain the same, and the form of the teeth never changes to an appreciable extent. At most there are some individuals in which an additional false molar develops on one side or the other. 65. This second objection is the objection of the morphologist. It would be an interesting study to compare Cuvier's views on variation with those of Darwin, who was essentially a systematist. Cuvier's first objection was of course determined to some extent by the imperfection of the paleontological knowledge of his time. But even at the present day the objection has a certain force, for although we have definite evidence of many serial transformations of one species into another along a single line, for example, Neumeyer's Paludina series, yet at any one geological level the species, the lines of descent, are all distinct from one another. 66. Cuvier recognized very clearly that there is a succession of forms in time, and that on the whole the most primitive forms are the earliest to appear. Mammals are later than reptiles, and fishes appear earlier than either. As Dieperid puts it, Cuvier not only demonstrated the presence in the sedimentary strata of a series of terrestrial faunas superimposed and distinct, but he was the first to express, and that very clearly, the idea of the gradual increase in complexity of these faunas from the oldest to the most recent, p10. He did not believe that the fauna of one epoch was transformed into the fauna of the next. He explained the disappearance of the one by the hypothesis of sudden catastrophes, and the appearance of the next by the hypothesis of immigration. He nowhere advanced the hypothesis of successive new creations. For the rest, when I maintain that the stony layers contain the bones of several genera and the earthy layers those of several species which no longer exist, I do not mean that a new creation has been necessary to produce the existing species. I merely say that they did not exist in the same localities and must have come thither from elsewhere. 67 It was left to d'Orbigny to teach the doctrine of successive creations, of which he distinguished 27, Cours élémentaire de paléontologie stratigraphique, 1849. Cuvier, however, can hardly have believed that all species were present at the beginning, since he does admit a progression of forms. Probably he had no theory on the subject, for theories without facts had little interest for him. At any rate, it is a mistake to think that Cuvier was a supporter of the theological doctrine of special creation. His philosophy of nature was mechanistic, and he dedicated his Recherches sur les ossements fossiles to his friend Laplace. He admitted the idea of evolution at least so far as to conceive of a development of man from a savage to a civilized state. 68 He refused to accept the extravagant evolutionary theory of de Maillet and the somewhat confused theory of Lamarck, whom he joins with de Maillet, 69 just as he rejected the transcendental theories of Geoffroy Saint-Hilaire, because they seemed to him not based upon facts. 41 Leçons d'anatomie comparée, Tome I, pages 10 ETSCQ, 1800. 42 Leçons d'anatomie comparée, I, p. 18. 43 LOCCIT, I, p. 13. 44 Leçons d'anatomie comparée, Tome I, articles 3-4, 1800. 45 Leçons d'anatomie comparée, I, p. 47. 46 Le Regni Animal, I, p. 6, 1817. 47 Histoire de progrès des sciences naturelles depuis 1789, I, p. 310, 1826. 48 Recherches sur les ossements fossiles, I, p. 60, 1812. 49 Ossements fossiles, I, p. 60. 50 LOCCIT, I, p. 63. 51 Leçons d'anatomie comparée, I, p. 6. 52 Le Regni Animal, I, p. 16. 53 Histoire Prague. Sci Nat, I, p. 187, 1826. 54 Leçons, I, p. 58. 55 LOCCIT, I, article 3. 56 LOCCIT, I, p. 60. 57 Regni Animal, I, pxx. 58 Cuvier, Histoire Prague. Sci Nat, I, p. 288, 1826. 59 Regni Animal, I, p. 10. 60 Regni Animal, p. 55. 61 First propounded by Cuvier in 1812, NMUSD Hist. Nat, 19. 62 Regni Animal, I, p. 19. 63 LOCCIT, p. 20. 64 Recherches sur les ossements fossiles, I, p. 74, 1812. 65 LOCCIT, p. 79. 66 CC Deperit, Les Transformations du Monde Animal, Paris, 1907, and G. Steinmann, Die Geologischen Grundlagen Abstammungslehre, Leipzig, 1908. 67 Recherches, I, p. 81. 68 Regni Animal, I, p. 91. 69 Ossements Fossils, I, p. 26. Chapter 4 Goethe Science, in so far as it rises above the mere accumulation of facts, is a product of the mind's creative activity. Scientific theories are not so much formulae extracted from experience as intuitions imposed upon experience. So it was that Goethe, who was little more than a dilettante 70, seized upon the essential principles of a morphology some years before that morphology was accepted by the workers. Goethe is important in the history of morphological method because he was the first to bring to clear consciousness and to express in definite terms the idea on which comparative anatomy before him was based, the idea of the unity of plan. We have seen that this idea was familiar to Aristotle and that it was recognized implicitly by all who after him studied structure comparatively. In Goethe's time the idea had become ripe for expression. It was used as a guiding principle in Goethe's youth, particularly by Wieck d'Azyr and by Camper. The former, 1748 to 1794, who discovered 71 in the same year as Goethe, 1784, the intermaxillary bone in man, pointed out the homology in structure between the forelimb and the hind limb, and interpreted certain rudimentary bones, the intermaxillaris and rudimentary clavicles, in the light of the theory that vertebrates are built upon one single plan of structure. Nature seems to operate always according to an original and general plan, from which she departs with regret and whose traces we come across everywhere. Wieck d'Azyr, quoted by Flourens, MEM. Academics I, XXIII, p. 30. Peter Camper, 1722 to 1789, we are told by Goethe himself in his Osteology, was convinced of the unity of plan holding throughout vertebrates. He compared in particular the brain of fishes with the brain of man. The idea of the unity of plan had not yet become limited and defined as a strictly scientific theory, it was an idea common to philosophy, to ordinary thought, and to anatomical science. We find it expressed by Herder, who perhaps got it from Kant, in his Ideen zur Philosophie der Geschichte der Menschheit, 1784, and it is possible that Goethe became impressed with the importance of the idea through his conversations with Herder. Be that as it may, it is certain that Goethe sought for the intermaxillaris in man only because he was firmly convinced that the skeleton in all the higher animals was built upon one common plan and that accordingly bones such as the intermaxillaris, found well developed in some animals, must also be found in man. The idea was not drawn from the facts, but the facts were interpreted and even sought for in the light of the idea. I eagerly worked upon a general osteological scheme, and had accordingly to assume that all the separate parts of the structure, in detail as in the whole, must be discoverable in all animals, because on this supposition is built the already long begun science of comparative anatomy. 72 The principle comes to clear expression in his Erste Entwurf einer allgemeinen Einleitung in die vergleichende Anatomie, 1795. 73 He writes, on this account an attempt is here made to arrive at an anatomical type, a general picture in which the forms of all animals are contained in potentia, and by means of which we can describe each animal in an invariable order. 74 His aim is to discover a general scheme of the constant in organic parts, a scheme into which all animals will fit equally well, and no animal better than the rest. When we remember that the type to which anatomists before him had, consciously or unconsciously, referred all other structure was man himself, we see that in seeking after an abstract generalist type Goethe was reaching out to a new conception. The fact that only the structure of man and the higher animals was at all well known in his time led Goethe to think that his general types would hold for the lower animals as well, though it was to be arrived at primarily from a study of the higher animals. All he could assert of the entire animal kingdom was that all animals agreed in having a head, a middle part, and an end part, with their characteristic organs, and that accordingly they might, in this respect at least, be reduced to one common typus. Goethe's knowledge of the lower animals was not extensive. Though Goethe did not work out a criterion of the homology of parts with any great clearness, he had an inkling of the principle later developed by E. Geoffroy Saint-Hilaire, and called by him the principle of connections. According to this principle, the homology of a part is determined by its position relative to other parts. Goethe expresses it thus: on the other hand, the most constant factor is the position in which the bone is invariably found, and the function to which it is adapted in the organic edifice. 75. But from this sentence it is not clear that Goethe understood the principle as one of form independent of function, for he seems to consider that the homology of an organ is partly determined by the function which it performs for the whole. He wavers between the purely formal or morphological interpretation of the principle of connections and the functional. We find him in the additions to the Entwurf, 1796, saying we must take into consideration not merely the spatial relations of the parts, but also their living reciprocal influence, their dependence upon and action on one another. 76. But in seeking for the intermaxillary bone in man he was guided by its position relative to the maxillaries. It must be the bone between the anterior ends of the maxillaries, a bone whose limits are indicated in the adult only by surface grooves. As a matter of fact, Goethe's morphological views are neither very clearly expressed nor very consistent. This comes out in his treatment of the relation between structure and function. Sometimes he takes the view that structure determines function. The parts of the animal, he writes, their reciprocal forms, their relations, their particular properties determine the life and habits of the creature. 77. We are not to explain, he says, the tusks of the babirusa by their possible use, but we must ask how it comes to have tusks. In the same way we must not suppose that a bull has horns in order to gore, but we must investigate the process by which it comes to have horns to gore with. This is the rigorous morphological view. On the other hand, he admits elsewhere that function may influence form. Apparently he did not work out his ideas on this point to logical clearness, and Radl 78 is probably correct in saying that the following quotation with its double assertion represents most nearly Goethe's position. Also bestimmt die Gestalt die Lebensweise des Thieres, und die Weise zu leben, sie wird auf alle Gestalten machtig Zurück. 79. His best piece of purely morphological work was his theory of the metamorphosis of plants. Stripped of its vaguer elements, and of the crude attempt to explain differences in the character of plant organs by differences in the degree of refinement of the sap supplied to them, the theory is that stem leaves, sepals, petals, and stamens are all identical members or appendages. These appendages differ from one another only in shape and in degree of expansion, stem leaves being expanded, sepals contracted, petals expanded, and so on alternately. It is equally correct to call a stamen a contracted petal, and a petal an expanded stamen, for no one of the organs is the type of the others, but all equally are varieties of a single abstract plant appendage. What Goethe considered he had proved for the appendages of plants he extended to all living things. Every living thing is a complex of living independent beings, which der Idee, der Anlage nach, are the same, but in appearance may be the same or similar, different, or unlike. 80. Not only is there a primordial animal and a primordial plant, schematic forms to which all separate species are referable, but the parts of each are themselves units, which der idee nach, are identical inter se. This fantasy can hardly be taken seriously as a scientific theory. It seems, however, to have been what guided Goethe in his discovery of the vertebral nature of the skull. Just as the forelimb can be homologous with the hind limb, so, reasoning by analogy, the skull should be capable of being homologous with the vertebrae. To what ludicrous extremes this doctrine of the repetition of parts within the organism was pushed we shall see when we consider the theories of the German transcendentalists of the early 19th century. Though Goethe's morphological views were lacking in definiteness, he hit upon one or two ideas which proved useful. Thus he enunciated the law of balance long before Etienne Geoffroy Saint-Hilaire, the law that to no part can anything be added, without something being taken away from another part, and vice versa. 81 He saw, too, what a help to the interpretation of adult structure the study of the embryo would be, for many bones which are fused in the adult are separate in the embryo. 82 This also was a point to which the later transcendentalists gave considerable attention. So far we have spoken of Goethe as if he were merely the prophet of formal morphology. We have pointed out how he brought to clear expression the morphological principle implicit in the idea of unity of type, and how he seized upon some important guiding ideas, such as the principle of connections. But Goethe was not a formalist, and he was very far from the static conception of life which is at the base of pure morphology. His interest was not in Gestalt or fixed form, Bildung, or form change. He saw that Gestalt was but a momentary phase of Bildung, and could be considered apart and in itself only by an abstraction fatal to all understanding of the living thing. Mephistopheles scoffs at the scholars who would explain a living creature by anatomizing it. Dan hat die viel insaner Hand, felt leider. Nur das Geistige Band. 83 Goethe kept clear of this mistake. He knew that the artist comes nearer to the truth than the analyst. In the fragment entitled Bildung und Bildung organischer Naturen, 1807, introductory to a reprint of his paper on the metamorphosis of plants, we get an exposition of his general views on living things. He points out there how we try to understand things by separating them into their parts. We can, it is true, resolve the organism into its structural elements, but we cannot recompose it or endow it with life by joining up the parts. Hence we require some other means of understanding it. In all ages, even among scientific men, there can be discerned a yearning to apprehend the living form as such, to grasp the connection of their external visible parts, to interpret them as indications of the inner activity, and so, in a certain measure, to master the whole conceptually. This science, which should discover the inner meaning of organic Bildung, is called morphology. 84 In morphology we should not speak of Gestalt or fixed form, or if we do we should understand by it only a momentary phase of Bildung. Form is of interest not in itself but only as the manifestation of the inner activity of the living being. Over development, he says elsewhere, there presides a formative force, a Bild and Kraft or Bildungstrieb, which works out the idea of the organism. Living things, in his view of them, strive to manifest an idea. They are nature's works of art, and so, incidentally, they require an artist to interpret them. This profound conception of the nature of life is applied not only to the growing changing individual but also to the whole changing world of organisms. They are all manifestations of a living shaping power which molds them. This shaping power, immanent in all life, is conceived to work according to a general plan, and so we get an explanation of the fact that living things seem simply varieties of one common type. If we once recognize, says Goethe, that the creative spirit brings into being and shapes the evolution of the more perfect organic creatures according to a general scheme, is it altogether impossible to represent this original plan, if not to the senses at least to the mind. 85 Such an interpretation of the unity of plan reaches perhaps beyond the bounds of science. 70 C. Kohlbrugge, Historie Crit. Studien über Goethe als Naturforscher, Zollannalen. V. 1913, pages 83 to 231. 71 Or rediscovered, according to Kohlbrugge. 72 Cotta ed., Volume 9, p. 448. 73 First draft of a general introduction to comparative anatomy. 74 Cotta ed., 9, p. 463. 75 Cotta ed., p. 478. 76 LOCCIT, p. 491. 77 Entwerf, Cotta ed., 9, p. 465. 78 Geschichte biologischen Theorie N, I, p. 266. 79 So the form determines the manner of life of the animal, and the manner of life in its turn reacts powerfully upon all forms. 80 Bildung und Bildung organischer Naturen, 1807. 81 Cotta ed., 9, p. 466. 82 LOCCIT, pages 474 to 5. 83 Then he has all the parts within his hand, excepting only, sad to say, the living bond. 84 Goethe was the inventor of the word. 85 Cotta ed., 9, p. 490. Chapter V. Etienne Geoffroy Saint-Hilaire Geoffroy made an experiment, unsuccessful but instructive. He tried to found a science of pure morphology, he failed. His failure showed, once and for all, that a pure morphology of organic forms is impracticable. Already, in 1796, in one of his earliest memoirs 86 Geoffroy was guided by the idea that nature has formed all living things upon one plan. Organs which seem anomalous are merely modifications of the normal. The trunk of an elephant is formed by the excessively prolonged nostrils, the horn of a rhinoceros is simply a mass of adhering hairs. In general, however varied their form, all organs are simply variations of a common scheme. Nature employs no new organs. Organs which are rudimentary, such as the clavicles in the ostrich and the nictitating membrane in man, bear witness to the unity of plan. In this Geoffroy goes no further than his predecessors. They too had recognized homologies of organs, they too had interpreted rudimentary organs as vestiges of an original plan. In a series of papers published in 1807, Geoffroy took a further step, and sought to establish homologies which were not obvious homologies, too, not so much of organs as of parts. These memoirs, published in the Annales du Muséum d'Histoire Naturelle, volumes 9 and X, 1807, dealt with the homology between the bones of the pectoral fin and girdle in fish and the bones of the arm and shoulder girdle in higher vertebrates, with the homologies of the bones of the sternum, and with the determination of the pieces of the skull, particularly in the crocodile. All Geoffroy's morphological doctrine is found in them, but for the full expression of his views we must take his chief work, the Philosophie Anatomique, particularly the first volume, 1818. This volume contains, beside the important Discours Préliminaire and Introduction which we shall presently consider in detail, 5 memoirs, which deal with the various bones connected with the respiratory organs in fishes, the bones of the operculum, of the hyoid, of the bronchial arches, of the pectoral girdle, and seek to discover their homologies with corresponding bones in air-breathing vertebrates. Can the organization of vertebrate animals be referred to one uniform type? This is the question with which the Philosophie Anatomique opens, the question to which the whole book is an answer. But is it not generally acknowledged by naturalists that vertebrates are built upon one uniform plan, that, for instance, the forelimb may be modified for running, climbing, swimming, or flying, yet the arrangement of the bones remain the same. How else could there be a natural method of classification? 87 But the homologies so drawn repose upon a vague and confused feeling for likenesses, they are not based upon an explicit principle. What general principle can be applied? Now it is evident that the sole general principle one can apply is given by the position, the relations, and the dependencies of the parts, that is to say, by what I name and include under the term of connections. For instance, the part known as the hand in man and generally as the forefoot in other vertebrates, is the fourth part in order in the anterior member, and its homologue can always be recognized by this fact of its connections, pxxvi. The principle of connections serves as a guide in tracing an organ through all its functional transformations, for an organ can be deteriorated, atrophied, annihilated, but not transposed, pxxx. It is this principle which enables one to follow out in detail the further fundamental conception that in every vertebrate there are found the same organic materials, or units of construction. This conception, which Geoffroy calls the theory de analogues, pxxxii, is clearly one part of the old idea of the unity of type. It teaches the unity of composition of organic beings, while the Principe de Connections adds the unity of plan. Both conceptions are logically implicit in the vague notion of unity of type. Geoffroy disengaged them, and pushed each to its logical extreme. Most of the ordinary homologies of structure in air-breathing vertebrates have already been seized, he continues, for they are more or less obvious, and many intermediate states exist, p. 30. But ordinary methods of comparison fail when the attempt is made to homologize the structure of fishes with that of air-breathing vertebrates, for the homologies are anything but obvious and no intermediate organs are found. Most air-breathing vertebrates have a larynx, a trachea, and bronchi, which are absent in fish, and fish have many parts which seem to be absent in higher vertebrates. But apply the theory of analogues. It teaches that there can be no organ peculiar to fish and not found in other vertebrates. Apply the principle of connections, it will show which organs are homologous in the two types, pxxxv. Comparative anatomists, with few exceptions, had hitherto taken man as the type, and referred all structure to his. Geoffroy's principles led him to give preference to no one animal in particular, but to seize upon each part in the species in which it reaches the maximum of its development, p. 30. He is thus led to refer all structures to a generalist abstract type. In this abstract type each organ exists at the maximum of its development, each organ shows all its potentialities realized. In a way, therefore, this type, this abstraction, gives the scheme of the possible transformations of each organ. It is true Geoffroy does not refer to this archetype in so many words, but it must always have been vaguely present in his mind. He has this idea in his head when he says in one of his later works, there is, philosophically speaking, only a single animal. 88 The single animal is simply the generalist type. Having laid down his two principles, Geoffroy goes on to apply them to the difficult case of the comparison of the skeleton of fish with the skeleton of the higher vertebrates. My present task is to demonstrate that there is no part of the bony framework of fishes that cannot find its analogue in the other vertebrate animals. 89 It seems at first sight that many bones are peculiar to fish, formed expressly for performing the functions which fish do not share with higher animals. These are the bones connected with respiration, the operculum, the branchiostegal rays, the bronchial arches, and others. That the peculiar bones should be connected with the respiratory functions is only natural, for the contrast between fish and higher vertebrates is essentially a contrast between water-breathing and air-breathing animals. Considering first the general form of the skeleton in fish, we are met at once with a difficulty. there is no obvious homologue in fishes of the neck, the trunk, and the abdomen of higher animals. What apparently corresponds to the trunk is in fishes crowded close up under the head. But, after all, it is not of the essence of the vertebrate type to have the trunk and the abdomen attached at definite and invariable distances along the vertebral column. That is a notion surviving from the anatomy which made man its type. The trunk differs in position according to the class, in quadrupeds, birds, and fishes, p9. Now, says Geoffroy, allow me this one hypothesis, that the trunk with its organs can, as it were, move bodily along the vertebral column, so as to be found in one class near the front end of the vertebral column, in another about the middle, and in a third near the end. Then I can show you in detail that the constituent parts of this trunk are found in all classes to be invariably in the same positions relatively to one another, p10. It is important to note this hypothesis of a metastasis which Geoffroy makes, for it is the key to the understanding of many of the far-fetched homologies which he tries to establish. It is, of course, clear that this hypothesis is in formal contradiction with his principal hypothesis of the invariability of connections, and that he, so to speak, gets a hold on his fish to apply his principle of connections only by admitting at the very outset an exception to his primary principle. A further application of the hypothesis of metastasis will be noticed below in connection with the determination of the sternum of fishes. We note here an interpretation of the first metastasis in terms of functional adaptation. The constant and violent action of the tail, if it does not go so far as actually to displace and move forward the internal organs, at least fits in well with an arrangement in which the organs are so disposed, p99. The first memoir deals with the homologies of the opercular bones. Geoffroy considers that the external opening of the ear corresponds to the external opening of the gill chamber, which lies between the operculum and the pectoral girdle. The ear communicates with the buccal cavity by the eustachian tube, so does the bronchial chamber by means of the gill slits. The auditory chamber of higher vertebrates is, therefore, the homologue of the bronchial chamber in fish. The opercular bones in fish and the ossicles of the ear in other vertebrates stand in close relation to this chamber, therefore the opercular bones are the homologues of the ossicles of the ear, the interoperculum corresponding to the malleus, the suboperculum to the lenticular, the minute lower part of the suboperculum to the incus, the operculum to the stapes, and the preoperculum to the tympanic ring. In making these particular determinations, Geoffroy professes to be led by his principle of connections. The preoperculum has, he says, the same connections with neighboring bones as the tympanic bone in other vertebrates, and the other pieces of the gill cover are homologous with particular ear ossicles according to the order in which they stand to one another. The second memoir in the book deals with the sternum, and affords a very good example of Geoffroy's method of dealing with the facts of structure. We shall omit here any detailed reference to the other three memoirs, which deal with the hyoid, with the bronchial arches and the structures which correspond in air-breathing vertebrates, and with the bones of the shoulder girdle. In the memoir on the sternum, Geoffroy's first care is to arrive at a definition of what a sternum is. He defines it partly by its functions, partly by its connections, as the system of bones which covers and protects the thorax, and gives attachment to certain groups of muscles. The most highly developed sternum, according to this definition, is the plastron of the tortoise, whose structure it dominates, p103. It is important, therefore, to determine of how many bones the plastron is composed, since the full number of elementary parts of which an organ is composed is best seen when the organ is at the maximum of its development. There are 9 bones in the plastron of the tortoise. The conclusion to be drawn from this is that every sternum, provided that it is not inhibited in its development by some obstacle, is composed of 9 elementary parts, p105. These 9 bones are in Geoffroy's nomenclature: the episternals, the hyosternals, the hyposternals, the xiphisternals, which are all paired bones, and the entosternal, which is unpaired. The arrangement of them is in the tortoise. The articulations in the tortoise are indicated by the connecting lines. Geoffroy tries to show that the sternum in other animals is composed of these 9 bones, or at least of a certain number of them, always in the same invariable relative positions. Thus in birds the sternum consists of 5 pieces, of a huge keeled entosternal, and of 2 annexes on either side, which are the ho and hyposternals. These are separate only in young birds. Occasionally, especially in young birds, rudiments of episternals and xiphisternals also occur. The minuteness of the episternals and the xiphisternals Fig. 1 hyoid arch of the conger, original, may be attributed to the gigantic size of the entosternal, in accordance with the Lloyd balancement. In the other air-breathing vertebrates the 9 sternal elements can, according to Geoffroy, be discovered without great difficulty. But when we come to the determination of the sternum in fishes, difficulties abound, which Geoffroy solves in the following way. He points out that between the clavicles, clythra, and the hyoid bone, basohyal, in fishes there is a long median bone, urohyal, which is attached in front by 2 strong tendons to the horns of the hyoid and is free behind, see Fig. 1. Guan, 1720, had seen in this bone the homologue of the sternum. Geoffroy adopts this view, but considers that this bone alone cannot represent the whole sternum. He finds the representatives of other bones of the sternum in the large bones, epihyal and ceratohyal, or the 2 pieces of the ceratohyal, which are comprised in the hyoid arch. But he is immediately met by the difficulty that this complex of bones is situated in front of the pectoral girdle, whereas the sternum in higher vertebrates lies behind the pectoral girdle. He reflects, however, that the gills of fish, situated in front of the clavicles, are merely the lungs under another name. The gills have become shifted forward by a metastasis similar to that which brought the whole thoracic organs far forward in fish. This being so, their supporting elements, the sternum and the ribs, must have moved with them, and are hence to be found in front of the pectoral girdle. Geoffroy's next step is to point out that the only possible homologues of sternal ribs are the branchiostegal rays, which arise from the large bones of the hyoid arch. If these are sternal ribs, the bones to which they are attached must be the ho and hyposternals or annexes, the bones from which in birds the ribs take their origin. The unpaired sternal bone, urohyal, cannot be homologous with the entosternal, for it has no connections with the annexes. He decides that it must represent the episternals, for in some young birds there is a 2-headed episternal to which 2 strong tendons are attached, just in the same way as the unpaired piece in fish is bound to the bones of the hyoid by 2 tendons. Thus it is not the sternum as a whole that has shifted in front of the clavicles and covered with its side pieces the gills placed there, it is a piece exclusively piscine, in the sense that it is only in the class of fishes that it reaches the maximum of its development, p. 83. To sum up, the sternum in all 4 vertebrate classes is composed of the same elements, arranged always in the same way. One is, led to the conception of an ideal type of sternum for all vertebrates, which then, considered from a lower standpoint, resolves itself into several secondary forms according as the whole or the majority of the constituent materials are employed, or even as these elements come to change their respective dimensions or proportions, p. 134. As to the elementary constituents, they give proof of individuality, and sometimes even, in certain abnormalities, of independence, and rise to the level of primary organizatory materials, p. 132. What holds good for the sternum holds good for other organs, and accordingly the unity of plan and composition can be demonstrated for all the organs of vertebrates. Soon after the publication of the Philosophie Anatomique, 1818, Geoffroy went further in his search for unity, and maintained that the structure of insects and crustacea could be reduced to the vertebrate type. He proposed to replace Cuvier's classification of the animal kingdom into the four large groups, vertebrata, mollusca, articulata, and radiata by the following classification: 90 vertebrates, Hauptvertebrates, vertebrata, Cuv, dermovertebrates, articulata, Cuv. Invertebrates, mollusks, mollusca, Cuv. Rayons, radiata, Cuv. The idea upon which is based the comparison of articulates with vertebrates is that each skeletal segment of articulates is a vertebra. In the Hauptvertebrates the vertebrae are internal, in the dermovertebrates they are external. Every animal lives either outside or inside its vertebral column. 91 The essence of a vertebra is not its form, nor its function, but its composition from four elementary pieces which unite round a central space. Isis, LOCCIT, p. 532. Serres had shown that in the higher animals every vertebra is formed from four centers of ossification, that the body of the vertebra is at first tubular, and that afterwards it becomes filled up. In lobsters and crabs each segment is composed of four elementary pieces, as may be seen most easily in young ones. Accordingly each segment corresponds to a true vertebra in composition, there is the same number of materials, the same order in the course of ossification, the same kind of articulation, the same annular arrangement, the same empty space in the middle, p. 534. The only difference is that in articulates the central space is very great and contains all the organs of the body, whereas in the higher vertebrates the body of the vertebra becomes completely filled up. In the thoracic region of crustacea it is not the whole segment with part of the carapace which corresponds to a vertebra, but merely the part round the ventral nerve cord, endophragmal skeleton. Fig. 2. Vertebra of a pleuronectid. After Geoffroy. If the skeleton of the segment in articulates corresponds to the body of a vertebra and is here external, then the appendages of the articulate must correspond to ribs, p. 538. The full development of this thought is found in a memoir of 1822, Sur la vertebra. 92 He takes as the typical vertebra that of a pleuronectid, probably the turbot. His original figure is reproduced, Fig. 2. He includes as part of the vertebra not only the neural, E, and hemal, O, arches, but also, above and below these, the radialia, A, U, and the fin rays, A, U. Neither the radialia nor the fin rays are, by the way, in the same transverse plane as the body of the vertebra. Every vertebra, he considers, contains these 9 pieces: the psychial, or body, the 2 perials, E, and the 2 epials, A, above, the 2 parals, O, and the 2 catals, U, below. The epials and the catals are in reality paired bones which in fish mount one on top of the other to support the median fins. In the cranial region the skull is formed of modified vertebrae. The epials and perials open out so as to form the walls and roof of the brain. In the thoracic region the parals and catals reach their maximum of development and perform the same service for the thoracic organs, the parals becoming vertebral, and the catals sternal, ribs. We have seen that in arthropods the body of the vertebra, psychial, forms the open ring of the segment, which lies immediately under the skin, the vertebral tube coinciding with the epidermal tube. The homologues of the other 8 pieces of the vertebra must accordingly be sought in the external appendages. At first sight there seems here a contradiction of the principle of connections, for the appendages in arthropods are lateral, whereas the paired bones of the vertebra are dorsal and ventral. But there is in reality no contradiction, for what our law of connections absolutely requires is that all organs, whether internal or external, should stand to one another in the same relations, but it is all one whether the box, coffer, that encloses them lies with this or that side on the ground. What similarities in the organization of man and the digitate mammals, and yet what differences between their attitudes when standing. The same holds true as regards the normal attitudes of the pleuronectids and the other fishes, p. 107. The exact way in which Geoffroy homologous the parts of the appendages in arthropods with the paired pieces of the typical vertebra is best shown by the reproduction of his figure of an abdominal segment of the lobster, Fig. 3, in which the parts homologous with those represented in the figure of the typical vertebra, Fig. 2, are indicated by the same letters. The ingenuity of the comparison is astonishing. The comparison of the arthropod with the vertebrate is extended also to the internal organs. The internal organs of the arthropod are shown to stand in the same order to one another as in the vertebrate, only the organs are inverted. Thus the nervous system is dorsal in the vertebrate, ventral in the arthropod. Turn the arthropod on its back and the relative positions of the systems of organs are the same as in the vertebrate. The relation of the organs to the external tube is of course different in arthropods and vertebrates, but this is no contradiction of the principle of connections. Such a tube, although it is the organs essential to life that it contains, can yet behave in different ways with regard to the mass of these organs. The principle of connections demands only that all the organs maintain with one another fixed and definite relations, but the principle would be in no way invalidated if the whole mass had rotated inside the tube, p. 112. Fig. 3. Abdominal segment of the lobster. After Geoffroy pushed the analogy between arthropods and vertebrates very far, for he asserted that every piece in the skeleton of an insect was homologous with some bone in vertebrates, that it stood always in its proper place, and remained faithful to at least one of its connections. 93. It does not appear that he attempted to prove in detail this very big assumption, but the beginnings of a detailed comparison are found in the paper of 1820, Sur l'organisation des insectes. 6 segments are distinguished in an insect: the head, the 3 divisions of the thorax, the abdomen, and the terminal segment of the abdomen, p. 455. The skeleton of the insect's head is said to correspond to the bones of the face, to the bones of the cerebrum and to the hyoid of higher vertebrates, the skeleton of the prothorax to the bones of the cerebellum, of the palate, and the pieces of the larynx, the skeleton of the mesothorax to the parietals, interparietals, and opercular bones, and that of the metathorax to the skeleton of the thorax of vertebrates. The pieces of the abdomen and of the terminal segment correspond to the bones of the abdomen and coccyx, p. 458. It does not need the subsequent likening of the hind wings of insects to the air bladder of fish, and of the stigmata to the pores of the lateral line, to convince one finally of the fancifulness of the whole comparison. In 1832 young naturalists, Marinx and Lorenzit, presented to the Académie des Sciences a memoir in which they likened a cephalopod to a vertebrate bent back at the level of the umbilicus, saying that the vertebrate in this position had all its organs in the same order as in the cephalopod. Geoffroy took up this idea with enthusiasm, seeing in it a further application of his master idea of the unity of plan and composition. By means of this comparison mollusca definitely took their place in the échelle des êtres, after the articulata, just as Geoffroy had maintained in 1820, saying that crabs formed a link between the other crustacea and the molluscs. 94. The comparison brought him nearer to the end he had in view, the reference of all animal structure to one single type. But in championing the memoir of Marinx and Lorenzit, Geoffroy found himself in direct antagonism with Cuvier, who held that his 4 embranchements had each a separate and distinct plan of structure. In a paper read to the Academy in February 1830-95, Cuvier easily demolished the crude comparison of the cephalopod to the vertebrate. He gave diagrams of the internal organs of a cephalopod and of a vertebrate bent back in the manner indicated by Marinx and Lorenzit, and he showed in detail that the arrangement of the main organs was quite different, that the likeness would have been much greater if the cephalopod had been likened to a vertebrate doubled up the other way 96, but that even then the arrangement of the organs would not be the same. The organs, too, of the cephalopod are differently constructed. He sums up his criticism by saying, I give true and summary expression to all these facts when I say that cephalopods have several organs in common with vertebrates, which fulfill in either case similar functions, but that these organs are differently arranged with respect to one another, and often constructed in a different way, that they are in cephalopods accompanied by several other organs which vertebrates do not possess, whilst the latter on their side have many organs which cephalopods lack. P. 257. Geoffroy could not accept this common-sense view of the matter, but made a fight for his transcendental theories. This was the beginning of the famous controversy between Geoffroy and Cuvier which so excited the interest of Goethe. It was a struggle between comparative anatomy and morphology, between the common-sense teleological view of structure and the abstract, transcendental. Geoffroy brought forward all his theories on the homology of the skeleton of fish with the skeleton of higher vertebrates, and tried to prove by them his great principle of the unity of plan and composition. Cuvier took Geoffroy's homologies one by one, and showed how very slight was their foundation. Cuvier was on sure ground in insisting upon the observable diversities of structural type, and his vast knowledge enabled him to score a decisive victory. 97. The controversy was not, as we are sometimes told, a controversy between a believer in evolution and an upholder of the fixity of species, although it raised a question upon which evolution theory was to throw some light. In these Darwinian days Geoffroy has reaped a little posthumous glory as an early believer in evolution. That he did believe in evolution to a limited extent is certain, that his theory of evolution was, as it were, a byproduct of his life work, is also certain. Geoffroy was primarily a morphologist and a seeker after the unity hidden under the diversity of organic form. His theory of evolution had as good as no influence upon his morphology, for he did not to any extent interpret unity of plan as being due to community of descent. His morphological, non-evolutionary standpoint comes out quite clearly in several places in the Philosophie Anatomique. He does not derive the structure of the higher vertebrates from the simpler structure of the lower, but when he finds in fish a part at the maximum of its development, he speaks of the same part, rudimentary in the higher forms, as being, as it were, held in reserve for use in the fish. Thus, speaking of the episternal in fish which forms the central piece of its sternum, he says, it is a bone that is rudimentary in birds. One might almost add a bone that is held in reserve in birds for this fate, which is destined to form in the center the principal keel of this new machine. P. 84. Again, with reference to the homology of the ossicles of the ear with the opercular bones in fish, employing other resources equally hidden and rudimentary, nature makes profitable use of the four tiny ossicles lodged in the auditory passage, and, raising them in fish to the greatest possible dimensions, forms from them these broad opercula. P. 85. Or you may take it the other way about, and start from the organization of fishes. Opercular bones are of no use to air-breathing animals, so they dwindle away, and are pressed into the service of the ear, although they are of little use in hearing. P. 46. There is here no thought of evolution. In later years, however, his researches upon fossil crocodilians led him to consider the possibility that the living species were descended from the antediluvian. For the factors of the transformation he refers to Lamarck's Hypotheses 98 in a memoir of 1828-99 dealing with the possible genetic relation of living to fossil species. He still regards the question as more or less open. Although fossil species are mostly different from living species, are we therefore to conclude, He asks, that they are not the ancestors of the present-day forms. The contrary idea arises more naturally in the mind, for otherwise the 6 days creation would have had to be repeated and new beings produced by a fresh creation. Now this proposition, contrary as it is to the most ancient historical traditions, is inadmissible, p. 210. It is sufficiently clear from this quotation that Geoffroy was thinking only of a transformation of the antediluvian species created by God, and by no means of an evolution of all species from one primitive type. In matters of religion Geoffroy was orthodox. He goes on to point out how great a resemblance there is in essential structure between fossil and living species. All find their place in one scheme of classification. Does it not seem that all are modifications of one single being, of that abstract being or common type, which it is always possible to denote by the same name? p. 211. This type is abstract, not actual, and it is certainly not conceived as an original ancestor of all animals. The fullest development of Geoffroy's views on evolution is found in his memoir Les Degrés influence du monde ambient pour modifier les formes animales. 100. Here the relation of his evolution theory to his morphology is pointed out. The principle of unity of plan and composition cannot be the final goal of zoology. There must follow on it a philosophical study of the differences between organic forms. The causes of these differences are to be found in the environment, pages 66 to 7. Geoffroy seems here to be moving from a pure to a causal morphology. It is probable, he continues, that living species have descended by uninterrupted generation from the antediluvian species, p. 74, and that they have in the process become modified through external influences. Now of all functions respiration is the most important, and upon respiration everything is regulated. If it be admitted that the slow progression of the centuries has brought in its train successive changes in the proportion of the different elements of the atmosphere, it follows as a rigorously necessary consequence that the organization has been proportionately influenced by them, p. 76. The respiratory milieu changes, the species change with it, or are eliminated, p. 79. We may see, perhaps, in the stress which Geoffroy lays upon respiration and the respiratory milieu a result of his constant obsession with the comparison of fish with air-breathing vertebrates. In the first geological period, we read in another memoir of the same year 101 when ammonites and Gryphia flourished, hot-blooded animals with lungs could not exist. A lung constructed like that of mammals and birds would not have been adapted to the essence of the respiratory element such as in my conception of it the system of the environing air used to be 102, p. 58. Geoffroy does not tell us exactly how the milieu is to act upon the organism. The whole theory is little more than a sketch and a pointing out of the way for future research, and in this prophetic enough. The action of external agents was apparently considered as physical, and no power of active adaptation was ascribed to the organism. From a passage in the Memoir sur la vertèbre we may perhaps infer that he believed increasing complexity of structure to be due to a realization of potentialities, to the development of parts present in the lower animals only in potency. The organization only awaits favorable conditions to rise, by addition of parts, from the simplicity of the first formations to the complication of the creatures at the head of the scale, p. 112. Evolution takes place as the environment allows, and in a sense in opposition to the environment. He believed in saltatory evolution, for he considered that the lower oviparous vertebrates could not be transformed into birds by slow modification, but only by a sudden transformation of their lungs, which would bring about the other characteristics of birds, p. 80. He considered, too, that transformations could arise by means of monstrous development, p. 86. In this connection the experiments which he made on the hen's egg 103 in order to produce artificial monstrosities are significant. though his purpose was rather to obtain proof of the inadequacy of the preformation hypothesis 104. It seems probable enough that if Geoffroy had developed his views on evolution, he would finally have been led to interpret unity of plan in terms of genetic relationship. But as it was, he remained at his morphological standpoint. He did not interpret rudimentary organs as useless heritages of the past. He preferred to think that nature had prepared double means for the same function, one or other being predominant according as the animal lived in the water or on the land. To the animal that lives exclusively in the air, nature has granted an organization suited to this mode of respiration, without however suppressing the other corresponding means, that is to say, without depriving it of a second system which is applicable only to the mode of respiration by the intermediary of water, and vice versa. 105. He seems, in one instance at least, to have hit upon the root idea of the biogenetic law, but he was far from appreciating its significance. He recognized that an amphibian in its development passed through a stage when it was in all essentials similar to a fish, and he saw in this visible transformation a picture of the evolutionary transformation. An amphibian, he writes 106, is at first a fish under the name of tadpole, and then a reptile under that of frog. In this observed fact is realized what we have above represented as an hypothesis, the transformation of one organic stage into the stage immediately superior. But it is not clear that he considered the development of the amphibian to be a repetition of its ancestral history. He went, however, a certain length towards recognizing the main principle of a law which was a commonplace of German transcendental thought, and was developed later by his disciple Ceres, the law that the higher animals repeat during their development the main features of the adult organization of animals lower in the scale. Thus he compared fish as regards certain parts of their structure with the foetus of mammals. He compared also articulates with embryonic vertebrates in respect of their vertebrae, for in the higher vertebrates the body of the vertebra is tubular at an early stage of development, and in articulates the body of the vertebra remains tubular permanently, supra, p. 61. As regards their vertebrae, insects occupy a place in the series of the ages and developments of the vertebrate animals, that is to say, they realize one of the states of their embryo, as fishes do one of the states of their fetal condition. 107. This idea was destined to exercise a great influence upon the development of morphology. A further development of the thought is that certain abnormalities in the higher animals, resulting from arrest of development, represent states of organization which are permanent in the lower animals. 108. So far we have considered Geoffroy's theories in their application to the facts. We go on to discuss the theories themselves, and the general conception of living things which underlies them. The principle of unity of plan and composition is the keynote of Geoffroy's work. It states that the same materials of organization are to be found in all animals, and that these materials stand always in the same general spatial relations to one another. The materials of organization are not necessarily organs in the physiological sense, and indeed the principle of the unity of plan cannot be upheld if the unity has reference to organs only. This became clear to Geoffroy, especially in his later years. In 1835 he wrote, speaking of the principle of the unity of plan, I have, moreover, regenerated this principle, and obtained for it universality of application, by showing that it is not always the organs as a whole, but merely the materials composing each organ, that can be reduced to unity. 109. Even in the Philosophy Anatomique he deals rather with parts than with organs. He deals, for instance, with the elementary parts of the sternum, not with the organ sternum in its totality. The functions of the sternum vary, and the primary protective function of the sternum may be assumed by quite other parts, example by the clavicles in fish, which protect the heart. 110. True homologies can be established between materials of organization but not always between organs, which may be composed of different materials. Almost as a corollary to this comes the further view that form is of little importance in determining homologies. An organ is essentially an instrument for doing a particular kind of work, and its form is determined by its function. Organs which perform the same function are usually similar in form, though the elementary materials composing them may be different. This is seen in many cases of convergence. Organs, therefore, which perform the same function and are similar in external form are not necessarily homologous. Conversely, the same complex of materials, say a forelimb, may take on the most varied shapes according as the function of the organ changes, but homology remains though form changes. Accordingly, form is one of the least important elements to be considered in determining a homology. Nature, he wrote in one of his early papers, tends to repeat the same organs in the same number and in the same relations, and varies to infinity only their form. In accordance with this principle I shall have to draw my conclusions, in the determining the bones of the fish's skull, not from a consideration of their form, but from a consideration of their connections. 111 Again, after comparing a vertebra of the aurochs with an abdominal segment of the crab, he says, I have insisted upon an identity which has extended to the least important relation of all, that of form. 112 Geoffroy's morphological units or materials of organization were in the case of the skeleton with which his researches principally deal the single bones. But the interesting point is that he sought his skeleton units in the embryo, and considered each separate center of ossification as a separate bone. Coalescence of bones originally separate is one of the most usual events in development, and it is an occurrence which, more than any other, tends to obscure homologies. Because of its coalescence with the maxillaries, the intermaxillary in man was not discovered until Wieck d'Azer and Goethe found it separate in the embryo. Apparently quite independently of Goethe, Geoffroy hit upon this plan of seeking in the embryo the primary elements or materials of organization. In an early paper on the skull of vertebrates 113, where he is concerned with showing that each bone of the fish's skull has its homologue in the skull of higher vertebrates, he is faced with the difficulty that the skull of the fish has more bones than the skull of higher vertebrates. Having had the inspiration, he writes, to reckon as many bones as there are distinct centers of ossification, and having made a consistent trial of this method, I have been able to appreciate the correctness of the idea. Fish, in their earliest stages, are in the same conditions relatively to their development as the foetuses of mammals, and hence bear out the theory, p. 344. So, too, in dealing with the homologies of the sternal elements, supra, p. 57, he treats as separate bones the annexes of the sternum in birds, though these are separate only in the young. If the same materials of organization are present in all animals, and if they are arranged always in the same positions relatively to one another, how does it come about that animal forms are so varied? What explanation can be offered of the diversities of organic structure? Geoffroy's main answer to this question is his loi de balancement. The law was enunciated by him already in 1807. 114 We take the following quotation, which represents his thought most nearly, from the Cours de l'Histoire naturelle des mammifères, 1829. According to our manner of regarding the organization of mammals, there is only a single animal modified by the inverse reciprocal variation of all or some of its parts. Now, from the fact that there is only one single general animal, it follows that for each section of its components or for each of its organs there is available only a given quantity of formative materials. Now suppose that the distribution of these materials has not been made in such a way as to ensure an exact equilibrium between all the parts concerned. One organ will get more than its share, another less. My law of the compensation of organs is founded on these principles. I. Lecken 16, p. 12. The atrophy of one organ turns to the profit of another, and the reason why this cannot be otherwise is simple: it is because there is not an unlimited supply of the substance required for each special purpose. 115 The nutritive material available is limited for each species. If one part gets more than its share, the other parts must get less. That is all the law means. As an example, take the minuteness of the episternals and xiphisternals in birds, as contrasted with the huge size of the entosternal. The minuteness of the episternals and xiphisternals might be imputed to this gigantic piece diverting to its own profit the nutritive fluid, since the bigger it is the smaller these are. 116 One has constantly to remember in dealing with Geoffroy's theories that he was not an evolutionist, but purely a morphologist. It is therefore, perhaps, to ask too much to require of him an explanation of the causes of diversity. The morphologist describes, classifies, generalizes, he does not seek for causes. But we must leave this question aside in order to discuss how far Geoffroy's theory of the unity of plan and composition fits the facts. As Geoffroy himself admitted on several occasions, his theory was an a priori one, a theory hit upon by hasty induction, then erected into a principle and imposed upon the facts. No more than Goethe did he extract his principle from a sufficient mass of data. Now he found his theory to be in its pure form unworkable. He found, for example, that the skeleton of fishes could not be compared directly, bone for bone, with the skeleton of higher vertebrates. He had to admit differences of position of whole sets of organs in the two groups. He had to admit various metastases, before he could bring the skeleton of fish into line. And these metastases are due to functional requirements. For example, the forward position of sternum and thoracic organs in fish is an adaptation to swimming. So he does not so much demonstrate the unity of plan of whole organisms as the unity of plan of particular corresponding parts of them. Thus he does not prove or attempt to prove that articulates are in all points like vertebrates, but simply that their skeleton is built upon the same plan as that of vertebrates. The rest of the organs, while still comparable with the organs of vertebrates, stand in different relations to the skeleton. An articulate therefore, on his own showing, is not, as a whole, built upon the same general structural plan as a vertebrate. Further, he does not always remain true to his principles, for he does not establish homologies of parts entirely by their connections but sometimes by their functions as well. Thus the sternum, or rather the complex of sternal elements, is defined and discovered in particular cases not by its connections only but also by its functions. The framework of the gills is homologous part by part with the framework of the lungs, not because the relations of the framework to the rest of the skeleton are the same in fish and air-breathing vertebrates, but simply because gills are considered the equivalents of lungs, a comparison which is purely physiological. Even with these concessions to the functional view of living things, Geoffroy was unable to make good his contention that all animals are built upon the same plan. His arguments failed to carry conviction to his contemporaries, and Cuvier in particular subjected them to destructive, and indeed final, criticism. The paper, already referred to, in which Cuvier disposed of the transcendentalists' comparison of cephalopods and vertebrates is of great significance, for it states in the clearest way the radical opposition between the functional and the formal attitudes to living things. Cuvier points out that if by unity of composition is meant identity, then the statement that all animals show the same composition is simply not true. Compare a polyp with a man. On the other hand, if by unity is meant simply resemblance or homology, the statement is true within certain limits, but it has been employed as a principle since the days of Aristotle, and the theory of unity of composition is original only in so far as it is false. He admits, however, that Geoffroy has seized upon many hidden homologies, especially by his valuable discovery of the importance of fetal structure. In all this Cuvier is undoubtedly right. Unity of plan and composition, as Geoffroy conceived it, simply does not exist. Cuvier goes on to say that this principle of Geoffroy's, in the greatly modified form in which it can be accepted, and has been accepted from the dawn of zoology, is not the sole and unique principle of the science. On the contrary, it is merely a subordinate principle, subordinate to a higher and more fruitful principle, that, namely, of the conditions of existence, of the adaptation, convenance, of the parts, of the coordination of the parts for the role which the animal is to play in nature. That is the true philosophical principle, he says, whence may be deduced the possibility of certain resemblances, the impossibility of certain others. It is the rational principle from which follows the principle of the unity of plan and composition, and in which at the same time it finds those limits, which some would like to disregard, p. 248. Geoffroy's position is the direct contrary. He holds that the principle of the unity of plan and composition is the true base of natural history 117, and that this unity limits the possible transformations of the organism. Thus, speaking of the influence of the respiratory medium, he says, all the same this influence of the external world, if it has ever become a cause which disturbed organization, must necessarily have been confined within fairly narrow limits. Animals must have opposed to it certain conditions inherent to their nature, the existence of the same materials composing them, and a manifest tendency to resemble one another, and to reproduce invariably the same primordial type. 118 Unity of plan and composition is, on this view, prior to adaptation and limits adaptation. Cuvier's view, on the contrary, is that the necessity of functional and ecological adaptation accounts for the repetition of the same types of structure. There are, of all the possible combinations of organs, only a few viable types, those whose structure is adapted to their life. Therefore it is reasonable that these few types should be repeated in innumerable exemplars. One must remember, in order to appreciate Cuvier's view, that he was not obsessed, as we are, by the idea of evolution. Cuvier thought in terms of organs, not in terms of materials of organization. He held that the resemblances between the organs of one class of animals and the organs of another were due to the similarity of their functions. Let us conclude, then, that if there are resemblances between the organs of fish and those of other classes, it is only in the measure that there is a resemblance between their functions. 119 There are only a few kinds of organs, each adapted for a particular function, and these organs are necessarily repeated from class to class. As the animal kingdom has received only a limited number of organs, it is inevitable that some at least of these organs should be common to several classes. 120 Geoffroy thought in terms of materials, of parts of indefinite function, parts which might take on any function. He insists upon the necessity of disregarding function when tracing out the unity of composition. He considers, in direct opposition to Cuvier's interpretation of structural resemblance as due to similarity of function, that unity of composition is the primary fact, and similarity of function subsidiary. In his reply in the Mammifères, 1829, to Cuvier's criticisms in the Histoire naturelle des poissons, 1828, he insists on the necessity of excluding function from consideration in any truly philosophical treatment of comparative anatomy, Discours Prol, p. 25. Cuvier held that function determined structure, or at least that the necessity of adaptation ruled the transformations of form. Geoffroy considered that structure determined function, that changes of structure, however they might arise, caused changes of function. Animals, he writes, have no habits but those that result from the structure of their organs. If the latter varies, there vary in the same manner all their springs of action, all their faculties and all their actions. 121 Again, a vegetarian regime is imposed upon the quadrumana by their possession of a somewhat ample stomach, and intestines of moderate length. 122 The hand of the bat has become so modified as to constrain the bat to live in the air. 123 The best example of Geoffroy's insistence upon the priority of structure to function, and so of his purely morphological attitude, is perhaps his interpretation, already alluded to, of the appendages of articulates. The segments of the articulate are, he says, the equivalents of the bodies of the vertebrae of higher forms. Now from the circumstance that the vertebra is external, it results that the ribs must be so too, and, as it is impossible that organs of such a size can remain passive and absolutely functionless, these great arms, hanging there continually at the disposition of the animal, are pressed into the service of progression, and become its efficient instruments. 124 The ribs become locomotory appendages. We may compare the similar thought that the ear ossicles are simply opercular bones reduced and turned to other uses. Geoffroy could not but recognize the correlation of structure to function, for this is a fact which imposes itself upon every observer. He recognized also correlation between functions, as when he pointed out the connection between increased respiration and enhanced muscular activity in birds. 125 He interpreted structure at times in terms of function, the short, strong clavicle of the mole as an adaptation to digging, the keeled sternum of birds as an adaptation to flying, and so on. But we may say that his whole tendency was to disregard function, to look upon it as subsidiary. He protests against arguing from function and habits to structure, as an abuse of final causes. 126 He was not so convinced as Cuvier was of the all-importance of functional correlation. In this view he was probably confirmed by his work on teratology. It did not surprise him that insects, in which lungs, heart, and circulation have disappeared, should yet have a skeleton built upon the same plan as the skeleton of vertebrates, which possess these organs. The correlation of organ systems is not so close as to prevent this. 127 So too, although the other organs of the insect are all inside the body of the vertebrae, they are yet comparable with the organs of vertebrates. 128 The existence of rudimentary organs also seemed to him an argument against too strict a correlation of parts. The contrast between the teleological attitude, with its insistence upon the priority of function to structure, and the morphological attitude, with its conviction of the priority of structure to function, is one of the most fundamental in biology. Cuvier and Geoffroy are the greatest representatives of these opposing views. Which of them is right? Is there nothing more in the unity and diversity of organic forms than the results of functional adaptation, or is Geoffroy right in insisting upon an element of unity which cannot be explained in terms of adaptation? If there be an irreducible element of unity, is there any truth in Geoffroy's suggestion that this unity results from a power which is exercised in the world of atoms where are elements of inalterable character? 129 The problem as Geoffroy and Cuvier understood it was not an evolutionary one. But the problem exists unchanged for the evolutionist, and evolution theory is essentially an attempt to solve it in the one direction or the other. Theories such as Darwin's, which assume a random variation which is not primarily a response to environmental changes, answer the problem in Geoffroy's sense. Theories such as Lamarck's, which postulate an active responsive self-adaptation of the organism, are essentially a continuation and completing of Cuvier's thought. 86 Mémoire sur les rapports naturels de Maquis, Magasin encyclopédique, 7. 87 Discours préliminaires, pages 15xxiv. 88 Études progressives d'un naturaliste, p. 50, Paris, 1835. 89 Philosophie anatomique, I, Introduction, p. 1. 90 Sur un colonnet vertébral et ses côtes dans les insectes et pyropodes, Academic Sci., February 12, 1820. Printed in Isis, pages 527 to 52, 1820, 2. 91 Sur l'organisation des insectes, p. 458. Isis, pages 452 to 62, 1820, 2. 92 MEM. MUSD Hist. Nat. 9, pages 89 to 119, PLSV 7. 93 Sur l'organisation des insectes, p. 459. 94 Isis, p. 549. 95 published in Ansci Nat. 19, pages 241 to 59, 1830. 96 Cf. Aristotle, Supra, p. 10. 97 For an account of the controversy reference may be made to I. Geoffroy Saint-Hilaire, V. Travaux et Doctrines Scientifiques d'Étienne Geoffroy Saint-Hilaire, Paris, 1847, also Semper, Arb. Zoologie Zuid. Instead. Würzburg, 3, 1876-7, K. Yvonne Baer, Lebensgeschichtliche, ed. Elstede, 1897, and J. Kohlbrugge, in Zoologie. Annalen, v. pages 143 to 95. 1913-98 Recherches sur l'organisation de Gavials, MEM. MUSD Hist. Nat. 12, 1825. 99 MEM. MUSD Hist. Nat. 17, pages 209 to 29. 100 MEM. Academic Sci., 12, pages 63 to 92, 1833. 101 MEM. Academic Sci., 12, pages 43 to 61, 1833. 102 Geoffroy's French style is at times incredibly bad, and more or less literal translations of his sentences are apt to read queerly. 103 MEM. MUSD Hist. Nat. 13, p. 289, 1826. 104 MEM. MUSD Hist. Nat. 18, p. 221, 1828. His teratological work is important, and is chiefly contained in the second volume of the Philosophie Anatomique. 105 Philosophy Anatomy, I, p. 449. 106 MEM. Academic Sci., 12, p. 82, 1833. 107 MEM. MUSD Hist. Nat. 9, p. 101, 1822. 108 Cours de l'Histoire naturelle des mammifères, I, Leçon 3, p. 13, 1829. 109 Études progressives d'un naturaliste, p. 59, FN, Paris, 1835. 110 Philosophie Anat, I, p. 444. 111 and MUSD Hist. Nat. X, p. 344, 1807. 112 Isis, p. 534, 1820, 2. 113 and MUSD Hist. Nat. X, pages 342 to 65, 1807. 114 LOCCIT, X, p. 343. 115 Philosophy Anatomy, I. 450, FNCF Aristotle, Supra, p. 11. 116 LOCCIT, p. 136. 117 Mammifers, I. Discarsprol, p. 18. 118 Philosophy Anatomy, I. p. 208. 119 Cuvier and Valenciennes, Histoire Nat. Poissons, I. p. 550, 1828. 120 Cuvier and Valenciennes, LOCCIT, p. 544. 121 Mammifers, I. Lecan 4, p. 17. 122 LOCCIT, Lecan 5, p. 8. 123 LOCCIT, Lecan 13, p. 6. 124 Isis, p. 539, 1822. 125 Mammifers, I. Lecan 4, p. 6. 126 Mammifers, Discarsprol, p. 7. 127 Isis, p. 460, 1822. 128 MEM. MUSD Hist. Nat. 9, p. 102, 1822. 129 MEM. Academic Sci. 12, p. 76, 1833. Chapter 6 The followers of Etienne Geoffroy Saint-Hilaire Geoffroy's theories were not generally accepted by his contemporaries, but his methods had considerable influence, especially in France, where many made essays in pure morphology. His chief follower was Serres, who is mentioned indeed in the Philosophie Anatomique as a fellow worker. Serres was primarily a medical anatomist. His interest lay in human anatomy and embryology, normal and pathological. His best early work was an Anatomie comparée du cerveau, 1824-26, which met with a flattering reception from Cuvier. 130 He laid great stress upon the development of the brain and spinal cord in the different classes, and was quick to point out analogies not only between adult but also between embryonic structures. He paid much attention to cases of correlation, and noted a great many. He observed, for instance, a constant relation between the development of the spinal cord and of the corpora quadrigemina, and between the size of the corpora quadrigemina and the volume of the optic nerves and eyes. In this the influence of Cuvier is unmistakable. Serres' early theoretical views are to be found in a series of papers in the Annales des Sciences Naturelles 131 under the general title Recherches d'anatomie transcendante, sur les lois de l'organogénie appliquées à l'anatomie pathologique, also published separately. We follow these papers in our exposé of Serres' doctrine, reserving for a future chapter, Chap 12, the consideration of his matured views of 30 years later. In the first of them he points out how neither position nor function has proved altogether sufficient to establish homologies. In the early days anatomists were guided by form. When form failed them, they traced an organ in its changes throughout the series of animals by considering its function. This method was satisfactory enough as regards the organs of the nutritive life. But in the organs of the life of relation, in the nervous system, the functions of the parts were difficult to discover, and their form very changeful. Hence a new principle was required, and Serres found it in the thought which he probably owed to the German transcendentalists, see Chap 7, that the permanent structure of the lower animals could be compared with phases in the development of the higher, and particularly of man, or, as he put it, that comparative anatomy was often only a fixed and permanent anthropogeny, and Anthropogeny, a fugitive and transitory comparative anatomy, 11, p. 106. In Rising Towards the First Formations, he writes, Transcendental anatomy recognized that one and the same organ, however complicated its definitive form might be, repeated in its transitory states the organic simplicities of the lower classes. Thus the primitive heart of birds was first of all a canal, then a pocket or single cavity, then finally the complex organ of the class. Comparative anatomy was thus seen to be repeated and reproduced by embryogeny, 12, p. 85. His explanation of the fact of repetition is that, in animals belonging to the lower classes, the formative force, whatever it may be, has a less energetic impulsion than in the higher animals, and hence the organs pass through only a part of the transformations which those of the higher forms undergo, and it is for this reason that they show permanently the organic dispositions which are only transitory in the embryo of man and the higher vertebrates. Hence these double aortas, these double veni cavi which one observes more or less constantly among reptiles, XXI, p. 48. The number of stages in embryogeny is proportionate to the complexity of the adult. The younger the embryo, the simpler its organs. Such is the general formula of the relation between the embryo and the adult. But here in Serres' doctrine of parallelism a complication enters. He observed that embryonic organs did not always develop in a piece, by simple growth, but often were formed by the union of separately formed parts or layers. Thus the kidney in man is formed by the fusion of a number of little kidneys, and the spinal cord reaches its full development by the laying down of successive layers within it. He was greatly impressed with this fact, which, as a convinced believer in epigenesis, he used with great effect against the preformistic theories. This method of isolated formation, he wrote, is noticed in early stages in the thyroid, the liver, the heart, the aorta, the intestinal canal, the womb, the prostate, the clitoris, and the penis, 11, p. 69. So, too, in the development of the skeleton, ossification proceeds from separate centers, foramina are formed by the fusion of separate bones round them. In his memoir, Lois de Osteogeny, 1819, Serres established several laws of ossification based upon this principle of separate formation. 132 How is the fact of multiple formation to be reconciled with the principle of repetition, according to which organs are simplest in the early embryo and in the lower animals? But observation shows that, as a rule, the further down the scale you go, the more divided organs become, the more numerous the bones of the skull, for example. There is thus a parallel between multiple formation of organs in the embryos of the higher vertebrates and their subdivided state in the lower. Take, for example, the kidney. In the genus Felis, and in birds, each kidney has 2 lobes, in the elephant 4, in the otter 10, in the ox 12 to 14. The human kidney in its development starts with about a dozen lobes, and the number diminishes as the kidney grows. Thus the permanent state of the kidney in the animals mentioned is reproduced by the stages of its development in man, 12, p. 126. So, too, at the 2nd or 3rd month the uterus of the human embryo is bicornuate, and afterwards passes through stages comparable to the adult and permanent uterus of rodents, ruminants, and carnivores. There is indeed a time in the development of the human embryo when it resembles in many of its organs the adult stage of various lower animals. It is about this time that it possesses a tail. We note that Serres' theory of parallelism applies, strictly speaking, only to organs, not to organisms, although he, too, readily fell into the error of supposing that the organization of an embryo could be compared as a whole with the adult organization of an animal lower in the scale. Thus he wrote in one of his later papers 133, as our researches have made clear, An animal high in the organic scale only reaches this rank by passing through all the intermediate states which separate it from the animals placed below it. Man only becomes man after traversing transitional organizatory states which assimilate him first to fish, then to reptiles, then to birds and mammals. Ceres was not altogether free from the besetting sin of the transcendentalists' hasty generalization. The law of parallelism applied not only to vertebrates but also to invertebrates. In a short paper 134 of 1824, Ceres attempted an explanation of the nervous system of invertebrates. Invertebrates, he considered, lacked the cerebrospinal axis of vertebrates, and their nervous system was the homologue of the sympathetic system of vertebrates. The relation of the invertebrate to the vertebrate nervous system being thus fixed, can the nervous system of invertebrates be reduced to one plan? It does not seem possible to establish a common plan for the adult nervous systems. But apply the principle of parallelism, which has proved so valuable within the limits of the vertebrate series. Taking insects as the highest class, we find that there are three stages in the development of their nervous system. In the first, the nervous system is composed of two separate strands, in the second the strands unite round the esophagus, in the third they unite also behind. Now in Bulla aperta, stage 1, is permanent, in Cleo, Doris, Aplysia, Tritonia, Sepia, Helix, stage 2, is permanent, and in Unio stage 3. In fact, all the varieties of the nervous system of mollusks fall into one or other of these three classes. It follows, then, that as regards their nervous system, the mollusca are more or less advanced larvae of insects, p. 380. The law of parallelism is here applied to single organ systems, but in later years Ceres applied it to whole organizations also, saying that the lower invertebrates were permanent embryos of the higher. In the paper of 1834, already referred to, Ceres pushed his speculations further and attempted to establish the unity of type of all animals, vertebrates and invertebrates alike, a favorite pastime of the transcendentalists. It is incontestable, he admits, that adult invertebrates are quite different in structure from adult vertebrates, but if one regards them as what I take them to be, namely, permanent embryos, and if one compares their organization with the embryogeny of vertebrates, one sees the differences disappear, and from their analogies arise a crowd of unsuspected resemblances. LOCCIT, p. 247. The last point of Ceres' doctrine which calls for remark is his interpretation of abnormalities as being often comparable to grades of structure permanent in the lower animals. Thus the double aorta which may occur as an abnormality in man is the normal and permanent state in reptiles. This idea, of course, he got from Etienne Geoffroy Saint-Hilaire. It is further developed in his Théorie de formations et de déformations organiques appliquées à l'anatomie comparée de monstruosités, 1832, and in his final large memoir of 1860, see below, p. 205. In 1816 appeared a fine piece of work by J. C. Savigny on the homologies of the appendages in articulates. The standpoint was that of pure morphology. I am convinced, he wrote, that when a more complete examination has been made of the mouth of insects, properly so called, that is to say, having 6 legs and 2 antennae, it will be found that whatever form it affects it is always essentially composed of the same elements. The organ remains the same, only the function is modified or changed, such is nature's constant plan. 135. In this the influence of Geoffroy can be traced, but the work was very free from the exaggerations of the transcendentalists, and many of Savigny's homologies are accepted even today. The first memoir dealt with the mouthparts of insects, the second with the anterior appendages of articulates generally. Savinus shows that the mouthparts of insects can be reduced to the type shown in Orthoptera, where there are clearly two mandibles, two maxillae, and a lower lip formed by the fusion of two second maxillae. All other insects have these same mouthparts, disposed in the same order, however much their form may have been modified in response to new functions. He goes on to compare the anterior set of appendages in a long series of articulates, in Julus, Scolopendra, Cancer, Gammarus, Siamus, Nymphon, Phalangium, Apis, Caligus, Limulus, and a few others. For Crustacea he established the homologies now accepted, of the mandibles with the mandibles of insects, of the first and second pairs of maxillae with the parts so named in insects, and so on. He is quite clear that the maxillipeds of Crustacea are the homologues of the feet of Hexapoda. Their disposition must lead one to think that the 6 anterior feet of Julus, that is to say, all the feet of the Hexapoda, are here transformed into jaws, loccit, p. 48. In Scolopendra also there is a similar transformation of 2 pairs of legs into auxiliary jaws. In Gammarus, where there is only the first pair of maxillipeds, the other 2 pairs have become retransformed into feet. We find him supporting his comparison of the 3 anterior pairs of legs in Julus to the 3 pairs of legs in insects by an argument drawn from embryology, for only the first 3 pairs of feet are present in Julus at birth, de Geer, an observation, which, together with their position, should cause them to be considered as the representatives of the 6 thoracic feet of Hexapoda, p. 44. His comparison of the arachnid appendages with those of insects and Crustacea is very curious. As his starting point he takes Siamus, which has antennae, 2 pairs, and mouth parts, 4 pairs, as in many Crustacea, and then 7 pairs of legs. He compares with it Nymphon, which has in all 7 pairs of appendages. These appendages he homologizes with the 7 pairs of legs of Siamus, so that the first appendage in Nymphon corresponds to the 7th appendage of Siamus. This homology is extended to all arachnids. Their first 2 pairs of appendages, however they may be modified as false mandibles and false maxillae, really correspond to the 2nd and 3rd maxillipeds in Crustacea, and to the 2nd and 3rd pairs of feet in insects. It is interesting to note that he treats Limulus as an arachnid, pointing out that there is as much difference between Apis and Limulus as between Cancer and Phalangium. He describes the gnathobases in Phalangium and Limulus. We may note that he had just an inkling of the modern doctrine that all the appendages of articulates consist of a basal joint bearing an inner and an outer terminal piece, for he observes that the cirri of the maxillipeds of Crustacea give the appendage the same bifid appearance as the appendages of the abdomen and the thoracic legs of Mysis, p. 50. V. Audouin, in his memoir, Recherches anatomiques sur le thorax de animaux articules 136 applied the principle of the unity of plan and composition to the exoskeleton of insects, crustaceans, and arachnids. His guiding ideas were, 1. That the skeleton of articulated animals is formed of a definite number of pieces, which are either distinct or intimately fused with one another. 2. That in many cases, some pieces diminish or altogether disappear, while others reach an excessive development. 3. That the increase of one piece seems to exert on the neighboring pieces a kind of influence which explains all the differences one finds between the individuals of each order, family, and genus. September. Copy, p. 16p. Geoffroy had already stated, without proof, that the parts of the arthropod skeleton, however they might change in shape and size, remain faithful to the principle of connections, at least at their points of insertion. 137 Audouin gave the detailed demonstration of this by his accurate and minute determination of the pieces of the arthropod skeleton. He recognized that the body of arthropods was made up of a series of similar rings, and that even the compact head of insects consisted of fused segments. In each segment Audouin distinguished a fixed number of harchitinous parts, the dorsal tergum, the ventral sternum, the lateral flank of 3 pieces, all to be recognized by their positions relative to one another. Many of the names which he proposed are still in use. It was he who introduced the terms prothorax, mesothorax, and metathorax, for the 3 segments of the insect's thorax. He used Geoffroy's Lloyd balancement to explain cases of correlative development, such as the relation between the size of the front wings and the development of the mesothorax. In another paper Audouin compared the 3 pieces of the dorsal skeleton of trilobites to the tergum and the upper part of the flank. 138. In a third paper of about the same time he tried to establish the homologies of the segments throughout the articulate series with less success than Savigny. Later on, in conjunction with Milne-Edwards, he demonstrated the unity of composition of the nervous system in Crustacea, showing how the concentrated system of the crab was formed by the same series of ganglia as in the Macrura. The entomologist Latreille also tackled the problem of the homologies of the segments in the different classes of arthropods, Cuvier, Loccit, Piccolsi. He thought he could find 15 segments in all arthropods. He made the retrograde step of likening the head of insects to a single segment. But some of his homologies showed morphological insight, example his comparison of the first jaws of arachnids to antennae, because they were placed above the upper lip. It was he who first pointed out the resemblance of the leaf-like gills of ephemerid larvae to wings, and suggested that wings were a sort of tracheal feet. He made also a rather hazy and speculative contribution on Oconian lines to the problem of the relation of arthropods to vertebrates, likening the carapace of Crustacea to an enormously developed hyoid, the appendages of the tail to the ventral and anal fins of fish. The masticatory organs of arthropods were jaws disjointed at their symphysis, antennae, nostrils turned outside in. Duggs also made a comparison of articulates with vertebrates. 139. He did not accept Geoffroy's vertebral theory of the arthropod skeleton, though he admitted that in arthropods the dorsal surface was turned towards the ground, basing this assumption on the position of the nervous system, and also, curiously enough, on the inverted position of the embryo on the lower surface of the yolk. He considered that the mandibles and first maxillae of arthropods were the homologues of the upper and lower jaws of vertebrates, adducing as confirmatory evidence the fact that in snakes the rami are separate. The labium was the equivalent of the hyoid, the labial palps and maxillipeds the equivalent of the hyoid elements which form the bronchial arches. But Duggs' main contribution to morphological method was his conception of the living organism as a colony of lesser units, which were themselves real organisms. By organism the author means a complex of organs which taken together suffice to constitute, ideally or actually, a complete animal. An organism is, as it were, an elementary or simple animal. Several organisms combined form a complex animal, p. 255. Duggs hit upon this principle, which was first suggested to him by Amo Quintandon's work on the leech, 1827, as a great aid in demonstrating the unity of plan and composition throughout the animal kingdom. 140. According to his view there are 3 main types of animals: 1. Bezoarials, including bilaterally symmetrical animals, composed of 2 parallel series of organisms; 2. Radiates, composed of organisms arranged like the spokes of a wheel; and 3. Raceme animals, in which the separate organisms were disposed more or less irregularly, in bunches, p. 257. The unitary organism is supposed to be the same in all, only the arrangement differing. Duggs of course admitted that the centralization of the complete organism became greater the higher it stood in the scale, and that this held good also in individual development. The appendages of articulates and vertebrates were thought of as the members of as many separate organisms. He went so far as to suggest that the fingers of a man's hand were the free extremities of as many thoracic members. Doug's conception of the organism has often been revived since in a saner form, example by E. Perrier, and it has a certain validity. It has much affinity with the similar conceptions of Goethe and the German transcendentalists. 130 MEM. Academic Sci. 4, pages Klsksevachi, 1824. 131 and Sci. Nat. 11, 12, 1827, 16, 1829, XXI, 1830. 132 C. Radl, LOCCIT, I, pages 225 to 6. 133 and Sinat. 2, 2, p. 248, 1834. 134 and Sinat. 3, pages 377 to 80, 1824. 135 Memoirs sur les animaux sans vertebres, Part I, p. 10, Paris, 1816. 136 and Sci. Nat. 1, I, pages 97 to 135, 416 to 432, 1824. 137 Isis, p. 456, 1820, 2. 138 Cuvier, MEM. Academic Sci. 4, PCCLXX, 1824. 139 Academic Sci. October 18, 1831. Extract in An Sci. Nat. XXIV, pages 254 to 60, 1831. 140 His views were more fully elaborated in his memoir Sur la conformité organique dans l'échelle animale, Montpellier, 1832. Chapter 7 The German Transcendentalists. To complete our historical survey of the morphology of the early 19th century, we have now to turn back some way and consider the curious development of morphological thought in Germany under the influence of the philosophy of nature. We have already seen many of these notions foreshadowed by Goethe, who had considerable affinity with the Transcendentalists, but the full development of transcendental habits of thought comes a little later than the bulk of Goethe's scientific work, and owes more to Kielmayer and Oken than to Goethe himself. A great wave of transcendentalism seems to have passed over biological thought in the early 19th century, arising mainly in Germany, but powerfully affecting, as we have seen, the thought of Geoffroy and his followers. Many ideas were common to the French and German schools of transcendental anatomy: the fundamental conception that there exists a unique plan of structure, the idea of the scale of beings, the notion of the parallelism between the development of the individual and the evolution of the race. It is difficult to disentangle the part played by each school and to determine which should have the credit for particular theories and discoveries. The philosophy seems to have come chiefly from Germany, the science from France. It must be borne in mind that German comparative anatomy was largely derivative from French, that the Paris Museum was the acknowledged anatomical center, and that Cuvier was its acknowledged head. It is probably correct to say that the credit mainly belongs to the German Transcendental School for the law of the parallelism between the stages of individual development and the stages of the scale of beings, and the theory of the repetition or multiplication of parts within the individual. The vertebral theory of the skull is a particular application of the second of these generalizations. The law of parallelism 141 seems to have been expressed first by Kielmayer, 1793, 142, who gave to it a physiological form, saying that the human embryo shows at first a purely vegetative life, then becomes like the lower animals, which move but have no sensation, and finally reaches the level of the animals that both feel and move. The idea was next taught by Autenrieth in 1797. 143 Oken, 1779–1851, in his early tract Die Jugend, 1805, and in his Lehrbuch der Naturphilosophie, 1809–11, elaborated the thought, and taught that every animal in its development passes through the classes immediately below it. During its development the animal passes through all stages of the animal kingdom. The foetus is a representation of all animal classes in time. 144 The insect, for example, is at first worm, next crab, then a perfect volant animal with limbs, a fly, ibid, p. 542. As nature is the representation of the individual activities of the spirit, so the animal kingdom is the representation of the activities or organs of man. The animal kingdom is therefore a dismemberment of the highest animal, i.e., of man, p. 494. Now animals are gradually perfected, entirely like the single animal body, by adding organ unto organ. The way of evolution is the way of development. Hence animals are only the persistent fetal stages or conditions of man, who is the microcosm, and contains within himself all the animal kingdom. Oken was himself a careful student of embryology. Von Baer 145 speaks of his work, published in Oken and Kieser, Beitrag zur Vergleichenden Zoologie, Anatomie und Physiologie, 2 points, 1806–7, as forming the turning point in our understanding of the mammalian ovum. He had accordingly actually observed a resemblance in certain details of structure between the human foetus and the lower animals, but the peculiar form which the law took in his hands was a consequence of his hazy philosophy. He saw the relation of teratological to fetal structure, for he affirmed that malformations are only persistent fetal conditions, p. 492. The idea of comparing the embryo of higher animals with the adult of lower was widely spread at this time among German zoologists. We find, for example, in Tiedemann's brilliant little textbook 146 the statement that every animal, before reaching its full development, passes through the stage of organization of one or more classes lower in the scale, or, every animal begins its metamorphosis with the simplest organization, p. 57. Thus the higher animals begin life as a kind of fluid animal jelly which resembles the substance of a polyp. The young mammal, like the lower vertebrates, has only a simple circulation, and, like them, lives in water, the amniotic fluid. The frog is first like a worm, then develops gills and becomes like a fish, p. 57. In his work on the anatomy of the brain 147 Tiedemann established the homology of the optic lobes in birds by comparing them with fetal corpora quadrigemina in man, see Ceres, and Synat, 12, p. 112. J. F. Meckel, in 1811, devoted a long essay to a detailed proof of the parallelism between the embryonic states of the higher animals and the permanent states of the lower animals. In a previous memoir in the same collection 148, I. 1, 1808, he had made some comparisons of this kind in dealing with the development of the human foetus. In this memoir, 2, 1, 1811, he brings together all the facts which seem to prove the parallelism. His collection of facts is a very heterogeneous one. He mingles morphological with physiological analogies, and makes the most far-fetched comparisons between organs belonging to animals of the most diverse groups. He compares, for instance, the placenta with the gills of fish, of mollusks, and of worms, homologizing the cotyledons with the separate tufts of gills in tethys, cilia, and arenicola, p. 26. This is purely a physiological analogy. He compares the closed anus of the early human embryo with the permanent absence of an anus in Coelentra, and the embryo's lack of teeth with the absence of teeth in many reptiles and fish, in birds, and in many cetacea, p. 46. 149. These are merely chance resemblances of no morphological importance. He considers bladderworms as animals which have never escaped from their amnion, and volvox as not having developed beyond the level of an egg, p. 7. He lays much stress upon likeness of shape and of relative size, comparing, for instance, the large multilobate liver of the human foetus with the many-lobed liver of lower vertebrates and of invertebrates. In general he shows himself, in his comparisons, lacking in morphological insight. His treatment of the vascular system affords perhaps the best example of his method, pages 8 to 25. The simplest form of heart is the simple tubular organ in insects, and it is under this form that the heart first appears in the developing chick. The bent form of the embryonic heart recalls the heart of spiders. It lies at first free, as in the molluscanomia. The heart consists at first of one chamber only, recalling the one-chambered heart of crustacea. A little later 3 chambers are developed, the auricle, ventricle, and aortic bulb. At this stage there is a resemblance to the heart of fish and amphibia. At the end of the 4th day the auricle becomes divided into 2, affording a parallel with the adult heart of many reptiles. In his large textbook of a somewhat later date, the System der Vergleichenden Anatomie, I. 1821, he works out the idea again and gives to it a much wider theoretic sweep, hinting that the development of the individual is a repetition of the evolutionary history of the race. Meckel was a timid believer in evolution. He thought it quite possible that much of the variety of animal form was due to a process of evolution caused by forces inherent in the organism. The transformations, he writes, which have determined the most remarkable changes in the number and development of the instruments of organization are incontestably much more the consequence of the tendency, inherent in organic matter, which leads it insensibly to rise to higher states of organization, passing through a series of intermediate states. 150. His final enunciation of the law of parallelism in this same volume shows that he considered the development of the individual to be due to the same forces that rule evolution. The development of the individual organism obeys the same laws as the development of the whole animal series, that is to say, the higher animal, in its gradual evolution, essentially passes through the permanent organic stages which lie below it, a circumstance which allows us to assume a close analogy between the differences which exist between the diverse stages of development, and between each of the animal classes, p. 514. He was not, of course, able fully to prove his contention that the lower animals are the embryos of the higher, and we gather from the following passage that he could maintain it only in a somewhat modified form. It is certain, he writes, that if a given organ shows in the embryo of a higher animal a given form, identical with that shown throughout life by an animal belonging to a lower class, the embryo, in respect of this portion of its economy, belongs to the class in question, p. 535. The embryo of a vertebrate might at a certain stage of development, be called a mollusk, if for instance, it had the heart of a mollusk. He admits, too, that the highest animal of all does not pass through in his development the entire animal series. But the embryo of man always and necessarily passes through many animal stages, at least as regards its single organs and organ systems, and this is enough in Meckel's eyes to justify the law of parallelism, p. 535. In his excellent discussion of teratology, Meckel points out how the idea of parallelism throws light upon certain abnormalities which are found to be normal in other, lower, forms, p. 556. 151. We may refer to one other statement of the law of parallelism by K. G. Karras in his Lehrbuch der Vergleichenden Anatomie, Leipzig, 1834. The standpoint is again that of nature philosophy. It is a general law of nature, Karras thinks, that the higher formations include the lower, thus the animal includes the vegetable, for it possesses the vegetative as well as the animal organs. So it is, too, by irrational necessity that the development of a perfect animal repeats the series of antecedent formations. As we have said, the main credit for the enunciation of the law of parallelism belongs to the German transcendental school, but the law owes much also to Serres, who, with Meckel, worked out its implications. It might for convenience, and in order to distinguish it from the laws later enunciated by von Baer and Haeckel, be called the law of Meckel-Serres. Under the theory of the repetition or multiplication of parts within the organism may be included, first, generalizations on the serial homology of parts, and second, more or less confused attempts to demonstrate that the whole organization is repeated in certain of the parts. The recognition of serial homologies constituted a real advance in morphology. The philosophical idea of the repetition of the whole in the parts led to many absurdities. It led Oken to assert that in the head the whole trunk is repeated, that the upper jaw corresponds to the arms, the lower to the legs, that in each jaw the same bony divisions exist as in the limbs, the teeth, for instance, corresponding to the claws, LOCCIT, p. 408. It led him to distinguish two animals in every body, the cephalic and the sexual animal. Each of these has its own organs. Thus in the perfect animal there are two intestinal systems thoroughly distinct from each other, two intestines which belong to two different animals, the sexual and cephalic animal, or the plant and the animal, p. 382. The intestine of the sexual animal is the large intestine, the lungs of the sexual animal are the kidneys, its glottis is the urethra, its mouth the anus. So, too, the mouth is the stomach of the head. On another line of thought, the sternum is a ventral vertebral column. Limbs are connate ribs, the digits indicating the number of ribs included, cf. Duggs, Supra, p. 88. J. F. Meckel 152 discusses homologies of this kind in the thorough and pedestrian way so characteristic of him. Not only, he says, are the right and left halves of the body comparable with one another, but also the upper and the lower, the dividing line being drawn at the level of the diaphragm. The lumbar complex corresponds to the skull, the anus to the mouth, the urinogenital opening to the nasal opening. In general, the urinogenital system corresponds to the respiratory, the kidneys to the lungs, the ureters to bronchi, the testes and ovaries to the thymus. He had observed the physiological relation between the development of the thymus and the state of the genital organs, the prostate and the uterus to the thyroid gland, and the penis and clitoris to the tongue. The forelimbs and girdle correspond in detail with the hind limbs and the pelvis, a point already worked out by Wieck d'Azur. The dorsal and ventral halves of the body are likewise comparable in some respects, the sternum, for example, answering in the arrangement of its bones, muscles and arteries to the vertebral column. The skeleton of each member is in some respects a repetition of the vertebral column. His brother, D. A. Meckel 153 worked out an elaborate comparison between the alimentary canal and the genital organs, basing the legitimacy of the comparison upon early embryological relations and upon the state of things in coelentra, where genital and digestive organs occupy the same cavity. In his view, the uterus corresponded to the stomach, the vagina to the esophagus, the fallopian tubes to the intestine, and so on. The vertebral theory of the skull took its origin from the same habit of thought. As part of the wider idea of the metameric repetition of parts, it had some scientific worth, but the theory was pushed too far, and the facts were twisted to suit it. Among annulate animals, the theory of repetition found ample scope. Oken was able to compare with justice the jaws of crabs and insects with their other limbs, as Savina did later in a more scientific way. Among vertebrates, the application of the theory of serial repetition was not so obvious, except in the case of the vertebrae. Goethe seems to have been the first to hit upon the idea that the skull is composed of a number of vertebrae, serially homologous with those of the vertebral column. He tells us that the idea flashed into his mind when contemplating in the Jewish cemetery at Venice a dried sheep's skull. The discovery was made in 1790, but not published till 1820. 154. The idea seems to have been taught by Kielmeyer, one of the earliest of the philosophers of nature, but it was not published by him. In a book, Cours d'études médicales, published in 1803, Burdon assimilated the skull to the vertebral column. Oken, in an inaugural dissertation, Programm, über die Bedeutung der Schädelknochen 155, published in 1807, gave to the theory its necessary development. Autenrieth, also in 1807, 156, distinguishing separate ganglia in the brain, was not far from the hypothesis that each of these ganglia must have its separate vertebra. In 1808, Dumeril read a paper to the Académie des Sciences in which he compared the skull to a gigantic vertebra, basing his hypothesis on the similarity existing between the crests and depressions on the hinder part of the skull and those on the posterior surfaces of the vertebrae. After Oken's work, the vertebral theory was taken up generally by both the German and the French anatomists. Spix published in 1815 a large volume on the skull, entitled Cephalogenesis, distinguishing, as Oken did at first, 3 cranial vertebrae. Bohannes in his Anatome Testudinus Europea, 1819, and in a series of papers in Isis, 1817 to 1819 and 1821, established the existence of a 4th cranial vertebra, and this was accepted by Oken in the later editions of his Layer book. Meckel and Carus among the Germans, de Blainville and E. Geoffroy among the French, contributed to the development of the theory. In England the theory was championed particularly by Richard Owen. It was one thing to assert in a moment of inspiration that the skull was composed of modified vertebrae, it was quite another to demonstrate the relation of the separate bones of the skull to the supposed vertebrae. Upon this much uncertainty reigned, there was not even unanimity as to the number of vertebrae to be distinguished. Goethe found 6 vertebrae in the skull, Spix, and at first Oken, 3 only, Geoffroy 7, the accepted orthodox number seems to have been 4, Bohannes, Oken, Owen. As an example of the method of treatment adopted, we may take Oken's matured account of the composition of the cranial vertebrae, as given in the English translation of his Layer book. To a perfect vertebra, he says, belong at least 5 pieces, namely, the body, in front the 2 ribs, behind the 2 arches or spinous processes, p. 370. In the cervical vertebrae the transverse processes represent the ribs. The skull consists of 4 vertebrae, the occipital, the parietal, the frontal and the nasal, or, named after the sense with which each is associated, the auditory, the lingual, the ocular and the olfactory. The bodies of these vertebrae are the body of the occipital, basicipedal, the 2 bodies of the sphenoid, basi and presphenoid, and the vomer. The transverse processes of each are the condyles of the occipitals, ex-occipitals, the ali of the 2 sphenoids, alisphenoids and orbitasphenoids, and the lateral surfaces of the vomer. The arches or spinous processes are the occipital crest, the parietals, the frontals, and the nasals. The cranium is thus composed of 4 rings of bone, each composed of the typical elements of a vertebra. The arbitrary nature of the comparison is obvious enough. As Cuvier pointed out in the posthumous edition of his Lecons, it is only the occipital segment that shows any real analogy with the vertebra, an analogy which Cuvier ascribed to similarity of function. he admitted a faint resemblance of the parietal segment to a vertebra. The body of the sphenoid does indeed look like a repetition of the brachioccipitale, but having a different function it takes on another form, especially above, by reason of its posterior clinoid apophyses. 157 He denied the resemblance of the frontal and nasal vertebrae to true vertebrae, pointing out that both parietals and frontals are bones specially developed for the purpose of roofing over and protecting the cerebrum. A very curious development was given to the vertebral theory by K. G. Karras, who seems to have taken as his text a saying of Oken's, that the whole skeleton is only a repeated vertebra. 158 His system is worthy of some consideration, for he tries to work out a geometry of the skeleton. 159 His method of deduction is a good example of pure nature philosophy. Life, he says, is the development of something determinate from something indeterminate. A finite indeterminate thing, that is, a liquid, must take a spherical form if it is to exist as an individual. Hence the sphere is the prototype of every organic body. Development takes place by antagonism, by polarity, typically by the division and multiplication of the sphere. In the course of development the sphere may change, by expansion into an egg-shaped body, or by contraction into a crystalline form, the changes due to expansion being typical of living things, those due to contraction being typical of dead. At the surface of the primitive living sphere is developed the protective dermatoskeleton, which naturally takes the shape of a hollow sphere. Round the digestive cavity which is formed in the living sphere is developed the splanchnoskeleton. Round the nervous system, which is, as it were, the animal within the animal, is developed the neuroskeleton. All skeletal formations belong to one or other of these systems. Karras defines his aim to be the discovery of the inner law which presides over the formation of the skeleton throughout the animal kingdom. He desires to know how such and such a formation is realized in virtue of the eternal laws of reason. 3. p. 93. Here we touch the kernel of nature philosophy, the search for rational laws which are active in nature, the discontent with merely empirical laws. The thesis which Karras sustains is that all forms of skeleton, whether of dermatoskeleton, splanchnoskeleton, or neuroskeleton, can be deduced from the hollow sphere, which is the primary form of any skeleton whatsoever. p. 95. That means, put empirically, that every skeleton can be represented schematically by a number of hollow spheres, suitably modified in shape, and suitably arranged. The chief modification in shape exhibited by bones is one which is intermediate between the organic and the crystalline series of modifications of the sphere. The organic modifications are bounded by curved lines, the crystalline by straight, the intermediate partly by curved and partly by straight lines. They are the daikon, the shape of a diabolo, and the cylinder. These forms must necessarily be of importance for the skeleton, which is intermediate between the organic and the inorganic. The daikon embodies the real significance of the bone, writes Karras. Each daikon and cylinder composing the skeleton is called by Karras a vertebra. We may expect then all skeletons to be composed of spheres, cylinders, and daikones in diverse arrangements. Nature being infinite, all the possible types of arrangement of these elements must exist in the test or skeleton of some animal, living, fossil, or to come. p. 127. One conceives easily what the main types of skeleton must be. In some animals, example sea urchins, the skeleton is a simple sphere. In others, example starfish, secondary rows of spheres radiate out from a central sphere or ring. In annulate animals the skeleton consists of a row of partially fused spheres. In vertebrates the arrangement is more complex. There are first the protovertebral rings of the dermatoskeleton, these being principally the ribs, limb girdles, and jaws. Round the central nervous system are developed the deutovertebral rings of the neuroskeleton, vertebrae in the ordinary sense. the apophyses and bodies of the vertebrae, and the bones of the members 160 are composed of columns of tritovertebrae, or vertebrae of the third order. Thus the whole vertebrate skeleton is a particular arrangement of vertebrae, which in their turn are modifications of the primary hollow sphere. The German transcendentalists were more or less contemporary with E. Geoffroy, and no doubt influenced him, especially in his later years, as they certainly did his follower Serres. Oken indeed wrote, in a note 161 appended to Geoffroy's paper on the vertebral column of insects, that Mr. Geoffroy is without a doubt the first to introduce in France nature philosophy into comparative anatomy, that is to say, that philosophy one of whose doctrines it is to seek after the signification of organs in the scale of organized beings. This is, however, an exaggeration, for Geoffroy was primarily a morphologist, whereas the morphology of the German transcendentalists was only a side issue of their nature philosophy. Geoffroy, on his part, exercised some influence on the transcendentalists. He asserts 162 indeed that Spix got some of the ideas published in the Cephalogenesis, 1815, from attending his course of lectures in 1809. It is certainly the case that Spix published before Geoffroy the view that the opercular bones are homologous with the earosicles, adopting, however, a different homology for the separate bones 163. Some speculations seem to have been common to both schools, for instance, the law of Meckel-Serres, the vertebral theory of the skull, and the recognition of serial homology in the appendages of arthropods, Savina, Oken. Latreille and Duggs, as well as Serres, clearly show in their theoretical views the influence of Oken and the other transcendentalists. Geoffroy's principle of connections and law of compensation were recognized by some at least of the Germans. But whatever his actual historical relations may have been with the German school, Geoffroy was vastly their superior in the matter of pure morphology. He alone brought to clear consciousness the principles on which a pure morphology could be based. The Germans were transcendental philosophers first, and morphologists after. One understands from this how J. F. Meckel, who was in some ways the leading comparative anatomist in Germany at this time, could be at once a transcendentalist and an opponent of Geoffroy. Meckel had a curiously eclectic mind. A disciple of Cuvier, having studied in 1804-6 the rich collections at the museum in Paris, the translator of Cuvier's Leçons d'anatomie comparée, he earned for himself the title of the German Cuvier, partly through the publication of his comprehensive textbook, System der Virgel. Anatomy, 5 volumes, partly by his extensive and many-sided research work, partly by his authoritative teaching. His system shows in almost every page of its theoretical part the influence of Cuvier, and it is through having assimilated Cuvier's teaching as to the importance of function that Meckel combats Geoffroy's law of connections, at least in its rigorous form. He submits that the connections of bones and muscles must change in relation to functional requirements. He rejects Geoffroy's theory of the vertebrate nature of articulates. Generally throughout his work the functional point of view is well to the fore. Yet at heart Meckel was a transcendentalist of the German school. His vagaries on the subject of homologues leave no doubt about that, and, in spite of Cuvier, he believed, though not very firmly, in the existence of one single type of structure. A Cuvierian by training, his lack of morphological sense threw him into the ranks of the transcendentalists, to whom perhaps he belonged by nature. 141. For a full account, see Kohlbrugge, Zoel Annalen, 38th, 1911. 142. Reed über das Verhältnis der Organisken Kraft, Stuttgart Tübingen, 1793, 1814. C. Radl, LOCCIT, I, p. 261, 2, p. 57. 143 Supplem. Ad Historiam Embryonis, Tübingen, 1797. 144 Lehrbuch der Naturphilosophie, ENG Trans, p. 491, 1847. 145 Über Entwicklungsgeschichte Theorie, I, p. 17, 1828. 146 Zoology, Landshut, I, 1808. 147 Anatomie Bildungsgeschichte Gehirns im Fotos des Menschen, Nürnberg, 1816. 148 Beatrich zur Vergleichende Anatomie, Leipzig, I, 1808-9, 2, 1811-2. 149 Cetacea were generally considered at this time to be mammals of low organization. 150 from the French Trans, which appeared under the title Trait Gen. D'Anat. Compare, I, p. 449, 1828. 151 cf. Geoffroy, Supra, p. 70. 152 Beatrich, 2, 1812. Also in his system D. Virgil. Anat, I, 1821. 153 in J. F. Meckel's Beatrich, 2. 154 Zur Morphology, I, 2, p. 250, 1820, and 2, pages 122-4, 1824. 155 C. Translation, giving the gist of this paper, in Huxley's Lectures on the Elements of Comparative Anatomy, pages 282-6, London, 1864. 156 Rales Archive. F. Physiol, 7, 1807. 157 Lecons d'Anatomie Comparée, 3rd ed., Brussels reprint, I, p. 414, 1836. 158 in his program, UD Bedeut. D. Schotelnoken, 1807. 159 Trait élémentaire d'Anatomie Comparée, French Trans, Volume 3, Paris, 1835. First developed in his volume Von den Urteilen und Challengerusts, Leipzig, 1828. 160 Dutrochet in 1821 had tried to prove that the bones of the members belong to the type of the vertebra the dicon. 161 Isis, pages 552-9, 1820, 2. 162 MEM. MUSD Hist. Nat. 9, 1822. 163 Cuvier and Valenciennes, Histoire Nat. Poissons, I, p. 311, FN Chapter 8 Transcendental Anatomy in England. Richard Owen is the epigenos of transcendental morphology. In him its guiding ideas find clear expression, and in his writings are no half-truths struggling for utterance. Fig. for ideal typical vertebra. After Owen. But he was, though a staunch transcendentalist, an eclectic of the older ideas current in his time, for he picked out what was best in the older systems: Cuvier's teleology, Geoffroy's principle of connections, Oken's idea of the serial repetition of parts. In particular, he assimilated the teaching of Cuvier, the great opponent of the transcendentalists, and reconciled it in part with his own transcendentalism. His main theoretical views are to be found in his volume on the archetype and homologies of the vertebrate skeleton, London, 1848. The master idea of the book is that the vertebrate skeleton consists of a series of comparable segments, each of which Owen calls a vertebra. Fig. 5 Natural typical vertebra, thorax of a bird. After Owen. His definition of a vertebra is, one of those segments of the endoskeleton which constitute the axis of the body, and the protecting canals of the nervous and vascular trunks, p. 81. The parts of a typical vertebra are shown in Fig. 4, which is copied from Owen's Fig. 14. In Fig. 5, page 103, is shown an actual vertebra, as Owen conceives it, the vertebra being that of a bird. A segment of sternum is included as the hemal spine of the vertebra, HS, the vertebral rib is the pluripophysis, PL, the sternal rib the hemapophysis, H, the uncinate process of the vertebral rib is known as the diverging appendage, A. The whole vertebrate skeleton is composed of a series of vertebrae which show these typical parts. We arrive thus at the conception of an archetype of the vertebrate skeleton, such as is represented in Fig. 6. The archetype is only a scheme of what is usually constant in the vertebrate skeleton, and both the number and the arrangement of the bones in any real vertebrate are subject to variation. It has been abundantly proved, Owen writes, towards the end of his volume, that the idea of a natural segment, vertebra, of the endoskeleton does not necessarily involve the presence of a particular number of pieces, or even a determinate and unchangeable arrangement of them. The great object of my present labor has been to deduce the relative value and constancy of the different vertebral elements, and to trace the kind and extent of their variations within the limits of a plain and obvious maintenance of a typical character, p. 146. It goes without saying that Owen considered the skull to be formed of vertebrae. The vertebral theory of the skull was, in his system, a deduction from the vertebral theory of the skeleton. He recognized 4 cranial vertebrae, the arrangement of them, and the relation of their constituent bones to the parts of the typical vertebra are shown in the table appearing on page 106. So far as their first 3 elements are concerned, these vertebrae are practically identical with the vertebrae distinguished in the classical vertebral theory of the skull, as enunciated by Oken. A divergence appears with the determination of the other elements of the vertebrae. The upper and lower jaws are associated with the nasal and frontal vertebrae respectively, not however as limbs of the head, but as constituent elements of these vertebrae. In the same way the hyoid apparatus is part and parcel of the parietal vertebra, and the pectoral girdle and forelimbs part of the occipital vertebra. Fig. 6 The archetype of the vertebrate skeleton. After Owen. Cranial vertebrae 164, after Owen, 1848, p. 165. Vertebrae. Occipital. Parietal. Frontal. Nasal. Centra. Basio-occipital. Basis sphenoid. Presphenoid. Vomer. Neuropophyses. Ex-occipital. Alisphenoid. Orbitasphenoid. Prefrontal. Neural spines. Supraoccipital. Parietal. Frontal. Nasal. Parapophyses. Paraccipital. Mastoid. Postfrontal. None. Pluripophyses. Scapular. Stylohyal. Tympanic. Palatal. Hemapophyses. Coracoid. Ceratohyal. Articular. Maxillary. Hemal spines. Episternum. Basohyal. Dentary. Premaxillary. Diverging appendage. Forelimb or fin branchiostegals. Operculum. Pterygoid and zygoma. Owen's reasons for considering the pectoral girdle and the forelimb part of the occipital vertebra are as follows. In fish, the pectoral girdle is slung to the skull by means of the post-temporal bone, suprascapula, according to Owen, which abuts on the occipital arch. In Lepidosiren, whose skeleton resembles the archetype in many ways, the pectoral girdle is likewise attached to the occipital segment. In most other vertebrates, the pectoral girdle has shifted backwards along the vertebral column, by a metastasis, Geoffroy, similar to that by which the pelvic fins in many fish have shifted up close to the pectoral girdle. The scapula, with suprascapula, is the pluripophysis, the coracoid, the hemapophysis, of the occipital vertebra. The clavicle is homologous with the slender bone in fish now known as the postclavicle, which shows a connection with the first or atlas vertebra of the vertebral column, forming, according to Owen, the hemapophysis of the atlas. Owen considers it no objection to this view that in other vertebrates the clavicle is anterior to the coracoid. Its anterior position to the coracoid in the air-breathing vertebrata is no valid argument against the determination, since in these we have shown that the true scapular arch is displaced backwards. On the Nature of Limbs, p. 63, London, 1849. In the pelvic girdle, the ilium corresponds to the scapula, the ischium to the coracoid, the pubis to the clavicle. Hence the ilium is a pluripophysis, the ischium and pubis are both hemapophyses. The forelimb is the developed appendage of the occipital vertebra, the hind limb the developed appendage of the pelvic vertebra. They are serially homologous with, for example, the uncinate processes of the ribs in birds, see Figs 5 and 6. The forelimb is a simple filament in Lepidosiren, and presents few joints in Proteus and Amphioma. In other air-breathing vertebrates it shows a more complete development, the humerus, radius, and ulna, and the bones of the wrist and hand becoming differentiated out. As the forelimb is equivalent to a single bone of the archetype, it is said to be, in its developed state, teleologically compound, p. 103. Since in the archetype every vertebra has its appendage, more than 2 pairs of locomotory limbs might have been developed. Any given appendage might have been the seat of such developments as convert that of the pelvic arch into a locomotive limb, and the true insight into the general homology of limbs leads us to recognize many potential pairs in the typical endoskeleton. The possible and conceivable modifications of the vertebrate archetype are far from having been exhausted in the forms which have hitherto been recognized, from the primeval fishes of the Paleozoic ocean of this planet up to the present time, p. 102. It is not of the essence of the vertebrate type to be tetrapodal. In determining homologies, Owen remained true to Geoffroy's principle of connections. Speaking of an attempt which had been made to determine homologies by the mode of development, he writes, "There exists doubtless a close general resemblance in the mode of development of homologous parts, but this is subject to modification, like the forms, proportions, functions, and very substance of such parts, without their essential homological relationships being thereby obliterated. These relationships are mainly, if not wholly, determined by the relative position and connection of the parts, and may exist independently of form, proportions, substance, function, and similarity of development. But the connections must be sought for at every period of development, and the changes of relative position, if any, during growth, must be compared with the connections which the part presents in the classes where vegetative repetition is greatest and adaptive modification least, p. 6. It is interesting to note that in Owen's opinion comparative anatomy explains embryology. Thus the scapula, which is the pluripophysis of the occipital vertebra, is vertical on its first appearance in the embryo of Tetrapoda, and lies close up to the head. On the Nature of Limbs, p. 49, the embryo shows a greater resemblance to the archetype than the adult. We perceive a return to it, as it were, in the early phases of development of the highest organized of the actually existing species, or we ought rather to say that development starts from the old point, and thus, in regard to the scapula, we can explain the constancy of its first appearance close to the head, whether in the human embryo or in that of the swan, also its vertical position to the axis of the spinal column, by its general homology as the rib or pluripophysis of the occipital. Vertebra, limbs, p. 56. We owe to Owen the first clear distinction between homologous and analogous organs. It was he who first proposed the terms homologue and analog, which he defined as follows: analog, a part or organ in one animal which has the same function as another part or organ in a different animal. Homologue, the same organ in different animals under every variety of form and function. 165. He introduced also useful distinctions between special, general, and serial homology. The relations of homology, he writes, are of three kinds. The first is that above defined, viz., the correspondency of a part or organ, determined by its relative position and connections, with a part or organ in a different animal, the determination of which homology indicates that such animals are constructed on a common type, when, for example, the correspondence of the basilar process of the human occipital bone with the distinct bone called basioccipital in a fish or crocodile is shown, the special homology of that process is determined. A higher relation of homology is that in which a part or series of parts stands to the fundamental or general type, and its enunciation involves and implies a knowledge of the type on which a natural group of animals, the vertebrate, for example, is constructed. Thus when the basilar process of the human occipital bone is determined to be the centrum or body of the last cranial vertebra, its general homology is enunciated. If it be admitted that the general type of the vertebrate endoskeleton is rightly represented by the idea of a series of essentially similar segments succeeding each other longitudinally from one end of the body to the other, such segments being for the most part composed of pieces similar in number and arrangement, and though sometimes extremely modified for special functions, yet never so as to wholly mask their typical character, then any given part of one segment may be repeated in the rest of the series, just as one bone may be reproduced in the skeletons of different species, and this kind of repetition or representative relation in the segments of the same skeleton I call serial homology, p. 7. As an example of serial homology we might take the centra of the vertebrae, the vomer, the presphenoid, the basisphenoid, the basioccipital, and the series of centra in the spinal column. Such serially repeated parts are called homotypes, p. 8. Not all the bones of the vertebrate skeleton are included in the archetype as constituents of the vertebrae. Thus the bronchial and pharyngeal arches are accounted part of the splanchna skeleton, as belonging to the same category as the heart bone of some ruminants, and the ossicles of the stomach in the lobster, p. 70. The ossicles of the ear in mammals are peculiar mammalian productions in relation to the exalted functions of a special organ of sense, p. 140, fn. This recognition of a possible development of new organs to meet new functions shows unmistakably the influence of Cuvier. Owen was indeed well aware of the importance of the functional aspect of living things, and he often adopted the teleological point of view. As a true morphologist, however, he held that the principle of adaptation does not suffice to explain the existence of special homologies. The ossification of the bones of the skull from separate centers may be purposive in eutheria, in that it prevents injury to the skull at birth, but how explain on teleological principles the similar ossification from separate centers in marsupials, birds, and reptiles? How explain above all the fact that the centers are the same in number and relative position in all these groups? Surely we must accept the idea of an archetype on which it has pleased the divine architect to build up certain of his diversified living works, p. 73. In his study of centers of ossification, Owen made in point of theory a distinct advance on his predecessors. We saw that Geoffroy recognized the importance of studying the ossification of the skeleton, and that Cuvier accepted such embryological evidence as an aid in determining homologies. Owen pointed out that it was necessary to distinguish between centers of ossification which were teleological in import and such as were purely indicative of homological relationships. Many bones, single in the adult, arise from separate centers of ossification, but we must distinguish between those centers of ossification that have homological relations, and those that have only teleological ones, i.e., between the separate points of ossification of a human bone which typify vertebral elements, often permanently distinct bones in the lower animals, and the separate points which, without such signification, facilitate the progress of osteogeny, and have for their obvious final cause the well-being of the growing animal, p. 105. There is, for example, a teleological reason why in mammals and leaping amphibia, example frogs, the long bones should ossify first at their ends, for the brain is thus protected from concussion. In reptiles that creep there is less danger of concussion, and the long bones ossify in the middle, p. 105. But there is no teleological reason why the coracoid process of the scapula should in all mammals develop from a separate center. The coracoid is however a real vertebral element, hemapophysis, and in monotrams, birds and reptiles it is in the adult a large and separate bone. Its ossification from a separate center in mammals has therefore a homological significance. The scapula in mammals is an example of what Owen calls a homologically compound bone. All those bones which are formed by a coalescence of parts answering to distinct elements of the typical vertebra are homologically compound, p. 105. On the other hand, all those bones which represent single vertebral elements are teleologically compound when developed from more than one center, whether such centers subsequently coalesce, or remain distinct, or even become the subject of individual adaptive modifications, with special joints, muscles, etc., for particular offices, p. 106. The limb skeleton, corresponding as it does to a single bone of the archetype, is the typical example of a teleologically compound bone. Owen in his definition of teleological compoundness has combined two kinds of adaptation: 1. Temporary adaptation of bones to the exigencies of development, birth, and growth, example development of long bones from separate centers; 2. Definitive adaptation of a skeletal part to the functions which it has to perform, example teleological structure of limbs. Such adaptations are, so to speak, grafted on the archetype. Owen's general views on the nature of living things merit some attention. Organic forms, according to Owen, result from the antagonistic working of two principles, of which one brings about a vegetative repetition of structure, while the other, a teleological principle, shapes the living thing to its functions. The former principle is illustrated in the archetype of the vertebrate skeleton, in the segmentation of the articulates, in the almost mathematical symmetry of echinoderms, and the actually crystalline spicules of sponges. It is the same principle which causes repetition of the forms of crystals in the inorganic world. The repetition of similar segments in a vertebral column, and of similar elements in a vertebral segment, is analogous to the repetition of similar crystals as the result of polarizing force in the growth of an inorganic body, p. 171. This general polarizing force it is which mainly produces the similarity of forms, the repetition of parts, and generally the signs of the unity of organization. The adaptive or special organizing force or delta alpha, on the other hand, produces the diversity of organic beings. In every species these two forces are at work, and the extent to which the general polarizing or vegetative repetition force is subdued by the teleological is an index of the grade of the species. This view is analogous to the Geoffroyan conception that the diversity of form is limited by the unity of plan. Owen thus ranges himself with Geoffroy against Cuvier, who considered that diversity of form is limited only by the principle of the adaptation of parts. 164. Owen introduced most of the names of bones now current. 165. Lectures on Invertebrate Animals, pages 374, 379, 1843. Chapter 9. Carl Ernst von Baer. Von Baer was recognized as the founder of embryology even by his contemporaries. His predecessors, Aristotle 166, Fabricius 167, Harvey 168, Malpighi 169, Haller 170, Wolf 171 had made a beginning with the study of development. Von Baer, by the thoroughness of his observation and the strength of his analysis, made embryology a science. It was to one of the German transcendentalists that von Baer owed the impulse to study development. Ignatius Dollinger, professor in Würzburg, induced three of his pupils, Pander, D. Alton, and von Baer, to devote themselves to embryological research. The development of animals was at this time little known, in spite of recent work by Meckel, 1815 and 1817, Tiedemann, Anatomie Bildungsgeschichte Gehirns, 1816, by Oken, Loccit, Supra, p. 90, and some others. Pander, with whom apparently Dollinger and D. Alton collaborated, was the first to publish his results. 172. Von Baer, who through absence from Würzburg had for a time dropped his embryological studies, started to work in 1819, after the publication of Pander's treatise, and produced in 1828 the first volume of his masterwork, Über Entwicklungsgeschichte Theorie. Beobachtung und Reflexion, Königsberg, 1828. The second volume followed in 1837, but dates really from 1834, and was published in an incomplete form. This second volume is intended as an introduction to embryology for the use of doctors and science students. In it von Baer describes in full detail the development of many vertebrate types: chick, tortoise, snake, lizard, frog, fish, several mammals, and man, basing his remarks largely upon his personal observations, but taking account also of all contemporary work. A separate account of the development of a fish, Cyprinus blicca, appeared in 1835. 173. We shall concentrate attention on the first volume. This volume contains the first full and adequate account of the development of the chick, followed by a masterly discussion of the laws of development in general. When we consider that von Baer worked chiefly with a simple microscope and dissecting needles, the minuteness and accuracy of his observations are astonishing. He described the main facts respecting the development of all the principal organs, and if, through lack of the proper means of observation, he erred in detail, he made up for it by his masterly understanding and profound analysis of the essential nature of development. His account of the development of the chick is a model of what a scientific memoir ought to be. The series of scholia which follow contain the deductions he made from the data, and, in so far as they are direct generalizations from experience, they are valid for all time. The first scholion is directed against the theory of preformation, and succeeds in refuting it on the ground of simple observation. The theme of the second scholion is that the essential nature, die Wesenheit, of the animal determines its differentiation, that no stage of development is solely determined by the antecedent stage, but that throughout all stages the Wesenheit or idea of the definitive whole exercises guidance. This guidance is shown most clearly in the regulatory processes of the germ, whereby the large individual variations commonly presented by the early embryo are compensated for or neutralized in the course of further development. Baer in this shows himself a vitalist. It is, however, the third and subsequent scholia which must here particularly occupy our attention, for it is in these that von Baer comes to grips with morphological problems. Already in the second Scholion he had definitely enunciated the law which runs as a theme throughout the volume, the observational and the theoretical part alike, the law that development is essentially a process of differentiation by which the germ becomes ever more and more individualized. The essential result of development, he writes, when we consider it as a whole, is the increasing independence, Selbstständigkeit, of the developing animal, p. 148. In the third Scholion he elaborates this thought and shows that differentiation takes place in triple wise. The three processes of differentiation are primary differentiation or layer formation, histological differentiation within the layers, and the morphological differentiation of primitive organs. The first of these differentiations in time is the formation of the germ layers, which takes place by a splitting or separation of the blastoderm into a series of superimposed lamellae. Bayer's account of the process in the chick is as follows. First of all, the germ separates out into heterogeneous layers, which with advancing development acquire ever greater individuality, but even on their first appearance show rudiments of the structures which will characterize them later. Thus in the germ of the bird, so soon as it acquires consistency at the beginning of incubation, we can distinguish an upper smooth continuous surface and a lower more granular surface. The blastoderm separates thereupon into two distinct layers, of which the lower develops into the plastic body parts of the embryo, the upper into the animal parts. The lower shows clearly a further division into two closely connected subsidiary layers, the mucus layer and the vessel layer. The original upper layer also shows a division into two, which form respectively the skin and the parts which I have called the true ventral and dorsal plates, parts which contain in an undifferentiated state the skeletal and muscular systems, the connective tissues, and the nerves belonging to these. In order to have a convenient term for future use, I have named this layer the muscle layer, p. 153. The process of delamination results then in the formation of four layers, of which the upper two, composing the animal or serous layer, will give origin to the animal, neuromuscular, part of the body, the lower pair to the plastic or vegetative organs. The uppermost layer will form the external covering of the embryo, and also the amniotic folds. From it there differentiates out at a very early stage the rudiment of the central nervous system, forming a more or less independent layer. Below the outermost layer lies the layer from which are formed the muscular and skeletal systems, and beneath this muscle layer comes the vessel layer, which gives origin to the main blood vessels. The innermost layer of the four will form the mucous membrane of the alimentary canal and its dependencies. At the present stage, however, it is, like the other layers, a flat plate. From all these layers tubes are developed by the simple bending round of their edges. The outermost layer becomes the investing skin tube of the embryo. The layer for the nervous system forms the tubular rudiment of the brain and spinal cord. The mucus layer curls round to form the alimentary tube. The muscle layer grows upwards and downwards to form the fleshy and osseous tube of the body wall. Even the vessel layer forms a tube investing the alimentary canal, but a part of it goes to form the medial gacrose, or mesenterial complex, which departs considerably from the tubular form. When these tubes or fundamental organs are formed, the process of primary differentiation is complete. The fundamental organs, however, have at no time actually the form of tubes, they exist as tubes only ideally, for morphological and histological differentiation go on concurrently with the process of primary differentiation. Through morphological differentiation the various parts of the fundamental organs become specialized, through unequal growth, first into the primitive organs and then into the functional organs of the body. Single sections of the tubes originally formed from the layers develop individual forms, which later acquire special functions. These functions are in the most general way subordinate elements of the function of the whole tube, but yet differ from the functions of other sections. Thus the nerve tube differentiates into sense organs, brain and spinal cord, the alimentary tube into mouth cavity, esophagus, stomach, intestine, respiratory apparatus, liver, bladder, etc. This specialization in development is bound up with increased or diminished growth, p. 155. Rapid growth concentrated at one point brings about an evagination. In this manner are formed the sense organs from the nerve tube, the liver and lungs from the alimentary tube. Or increased growth over a section of a tube causes it to swell out. In this wise the brain develops from the nerve tube, the stomach from the alimentary tube. The segmentation, which soon becomes so marked, particularly in the muscle layer, is also due to a process of morphological differentiation. At the same time that the organs of the body are being thus roughly blocked out and molded from the germ layers, the third process of differentiation is actively going on. In addition to the differentiation of the layers, there follows later another differentiation in the substance of the layers, whereby cartilage, muscle, and nerve separate out, a part also of the mass becoming fluid and entering the bloodstream, p. 154. Through histological differentiation the texture of the layers and incipient organs becomes individualized. In its earliest appearance the germ consists of an almost homogeneous mass, containing clear or dark globules suspended in its substance, 2, p. 92. This homogeneity gives place to heterogeneity, the structureless mass becomes fibrous to form muscles, hardens to form cartilage or bone, becomes liquid to form the blood, differentiates in 100 other ways into absorbing and secreting tissues, into nerves and ganglia, and so forth. It will be noticed that the concept of histological differentiation is independent of the cell theory. It signifies that textural differentiation which leads to the formation of tissues in Bichat's sense. The tissues and the germ layers stand in fairly close relation with one another, for while certain tissues are formed chiefly but not exclusively in one layer, others are formed only in one layer and never elsewhere. For example, peripheral nerves are for the most part formed in the muscle layer, though the bulk of the nervous tissue is formed in the walls of the nerve tube. Similarly, blood and blood vessels may arise from almost any layer, though their chief seat of origin is the vessel layer. On the other hand, bone is formed only in the muscle layer, p. 155, 2, pages 92-3. This relation of tissue to germ layer was more fully discussed and brought into greater prominence by Remak, from the standpoint of the cell theory, and it will occupy us in a later chapter, Chap 12. The fourth Scholion elaborates the analysis of developmental processes still further, and discusses in particular the scheme of development which is shown by the vertebrata. The characteristic structure of the vertebrate body is brought about by a double symmetrical rolling together of the germ layers, whereby two main tubes are formed, one above and one below the axis of the body, which is the chorda. The dorsal tube is formed by the two animal layers, the ventral tube by all the layers combined, see Fig. 7. The process is indicated with sufficient clearness in the diagram. It will be seen that the real foundation and framework of the arrangement is the muscle layer, with its two tubes, one surrounding the central nervous system and forming the dorsal plates, the other surrounding the body cavity and forming the ventral plates. In the dorsal plates, which early show metameric segmentation, the investing skeleton of the neural axis develops. In the ventral plates are formed the ribs, the ventral arches of the vertebrae, the hyoid, the lower jaw and other skeletal structures. The alimentary or mucous tube and the part of the vessel layer which invests it become so closely bound up with one another as to form a single primitive organ, the alimentary canal. The muscles of the alimentary canal are accordingly in all probability developed in the investing part of the vessel layer. From the gacros, or remaining part of the vessel layer, develop the Wolffian bodies, Erniaron, pronephros, the kidneys, the sex glands, and the series of blood glands suprarenals, thyroid, thymus, and spleen. Baer did not attach any special morphological significance to the peritoneal lining of the body cavity, as is done in more modern forms of the germ layer theory. The gill slits were largely formed by outgrowths from the alimentary canal. Fig. 7 Ideal transverse section of a vertebrate embryo. After von Baer, A. chorda. E. vessel layer. I. amnion. B. dorsal plates. F. alimentary tube. K. serous membrane. C. ventral plates. G. pronephros. L. Toke sac. D. spinal cord. H. skin. In his germ layer theory, von Baer was influenced a good deal by Pander, to whom the actual discovery of the process of layer formation is due. Pander, however, had distinguished only three germ layers: an upper serous layer, a lower mucus layer, and a middle vessel layer. He it was who introduced the terms chemote, blastoderm, and cameblatt, germ layer. The honor of being the founder of the germ layer theory is sometimes attributed to C. F. Wolf, notably by Kalliker and O. Hertwig. Wolf, it is true, in his memoir De Formatione Intestinorum, 1768-9, showed that the alimentary canal was first formed as a flat plate which folded round to form a tube, and in a somewhat vaguely worded passage he hinted that a similar mode of origin might be found to hold good for the other organ systems. But it seems clear that Wolf had no definite conception of the process of layer formation as the first and necessary step in all differentiation. This, at any rate, was von Baer's opinion, who assigns to Pander the glory of the discovery of the germ layers. You, he writes, through your clearer recognition of the splitting of the germ, a process which remained dark to Wolf, have shed a light upon all forms of development, pxxi. We have now seen, following von Baer's exposition, how development is essentially a process of differentiation, a progress from the general to the special, from the homogeneous to the heterogeneous. We have analyzed the process into its three subordinate processes: primary, histological, and morphological differentiation. So far we have considered development in general and the laws which govern it. We have now to consider the varieties of development which the animal kingdom offers in such profusion, in order to discover what relations exist between them. This is the problem set in the fifth Scholion. Baer at once brings us face to face with the solution of the problem attempted in the Meckel-Serres law. It is a generally received opinion, he writes, that the higher animals repeat in their development the adult stages of the lower, and this is held to be the essential law governing the relation of the variety of development to the variety of adult form. This opinion arose when there was little real knowledge of embryology. It threw light indeed upon certain cases of monstrous development, but it was pushed altogether too far. It complicated itself with a belief in a historical evolution. People gradually learned to think of the different animal forms as developed one from another, and seemed, in some circles at least, determined to forget that this metamorphosis could only be conceptual. p. 200. At the same time, the theory of parallelism led men to rehabilitate the outworn conception of the scale of beings, to maintain that animals form one single series of increasing complexity, a scale which the higher members must mount step by step in their development, from which it followed that evolution, whether conceived as an ideal or as an historical process, could take place only along one line, could be only progressive or regressive. Not all the supporters of the theory of parallelism held these extreme views, but conclusions of this kind were natural and logical enough. Von Baer had soon found in the course of his embryological studies that the facts did not at all fit in with the doctrine of parallelism. The developing chick, for example, was at a very early stage demonstrably a vertebrate, and did not recapitulate in its early stages the organization of a polyp, a worm, or a mollusk. He had published his doubts in 1823, but his final confutation of the theory of parallelism is found in this scholion. If it were true, he says, that the essential thing in the development of an animal is this repetition of lower organizations, then certain deductions could be drawn, which one would expect to find confirmed in nature. The first deduction would be that no structures should appear in the embryo of the higher animals that are not found in the lower animals. But this is not confirmed by the facts no adult among the lower animals, for instance, has a yolk sac like that of the chick embryo. Again, if the law of parallelism were true, the mammalian embryo would have to repeat the organization of, among other groups, insects and birds. But the embryo in utero is surrounded by fluid and cannot possibly breathe free air, so it cannot possibly repeat the structure of either insects or birds, which are preeminently air organisms. Generally speaking, indeed, we find in all the higher embryos special structures which adapt them to the very special conditions of their development, and these we never find as permanent structures in the lower animals. The supporters of the theory of parallelism might, however, admit the existence of such special embryonic organs without greatly prejudicing their case, for these temporary organs stand to some extent outside the scope of the theory. But they would have to face a second and more important deduction from their views, namely, that the higher animals should repeat at every stage of their development the whole organization of some lower animal, and not merely agree with them in isolated details of structure. The deduction is, however, not borne out by the facts. The embryo of a mammal resembles in many points, at different stages of its development, the adult state of a fish. It has gill slits and complete aortic arches, a two-chambered heart, and so on. But at no time does it combine all the essential characters of a fish, nor has it ever the tail of a fish, nor the fins, nor the shape. Any recapitulation there may be is a recapitulation of single organs, there is never a repetition of the complete organization of a fish. This is indeed the fundamental criticism of the theory of parallelism, and if it applies even within the limits of the vertebrate phylum, so much the more does it apply to comparisons between embryonic vertebrates and adult invertebrates. There are also some lesser arguments which might be urged against the theory of parallelism. If the theory were strictly true, no state which is permanent in a higher animal could be passed through by an animal lower in the scale. But birds, which are lower in the scale than mammals, pass through a stage in which they resemble mammals in certain respects much more than they do when adult, for in an embryonic condition they agree with mammals in having no feathers, no air sacs, no pneumatic sacs in the bones, no beak. Their brain also resembles that of mammals more in an earlier stage than it does later. So, too, myriapods and hydrocnids have at birth 3 pairs of feet, and resemble at this stage adult insects, which form a higher class. Again, were the analogy between the development of the individual and the evolution of the Acheldaedrus complete, organs and organ systems ought to develop in the individual in the order in which they appear in the scale of beings. But this is not always the case. In fish the hinder extremity develops only its terminal joint, while in the embryos of higher animals the basal joint is the first to appear. Another consequence one would expect to find realized, were the theory of parallelism correct, is the late appearance in development of parts which are confined to the higher animals. In the development of a vertebrate accordingly one would not expect the vertebrae to appear before the embryo had passed through many invertebrate stages. But experience shows the direct contrary, for in the chick the rudiments of the vertebral axis appear sooner than any other part. The theory of parallelism or recapitulation then is not borne out by the facts, and clearly cannot be the law which we are seeking. But what then is the true relation between the variety of development and the variety of adult structure? Before answering this question we must review the varied forms of adult organization and consider in what relations they stand to one another. In particular we must inquire whether they belong to one type or to many. One point is here cardinal: we must distinguish between the type of organization and the grade of differentiation. By type, von Baer means the structural plan of the organism. I call the type the spatial relationship of the organic elements and organs, p. 208. Each type of organization characterizes one of the big groups of animals, the lesser groups represent grade modifications of the type. The product of the degree of differentiation and the type gives the several great groups of animals which are called classes, p. 208. Ausbildung, differentiation, takes place in one or other of several directions, in adaptation, for instance, to life in the water or to life in the air. There are, von Baer considers, four main types: 1. The peripheral or radiate type, 2. The longitudinal type, 3. The massive or molluscan type, 4. The vertebrate type. The radiate type is shown by discoid infusoria, by medusae, by starfish, and their allies. The longitudinal type characterizes such genera as Vibrio, Filaria, Gordius, and all the annulate animals. Mollusca, Rotifers, Polyzoa, and such infusoria as are not included in types 1 and 2, belong to the massive type, in which the body and its parts form rounded masses. The longitudinal type is predominantly animal, the massive type predominantly plastic, vegetative. The vertebrate type has both the animal and the plastic organs highly developed. In the symmetrical arrangement of the animal parts it resembles the longitudinal type, its plastic parts with their asymmetrical arrangement and rounded shape belong to the massive type. These types of von Baer inevitably recall the embranchements of Cuvier, with which they more or less coincide. It seems that von Baer arrived at his types, from the study of adult structure, independently of Cuvier, though the priority of publication rests with Cuvier 174. Now it is clear that the development of the individual, which is essentially an Ausbildung, a differentiation, is directly comparable with the grade differentiation of forms within the type. And just as the type rules all its varied modifications, so does the development of the individual take place always within the bounds imposed by type. This is von Baer's chief contribution to the theory of embryonic relationships, the law that the type of organization determines the manner of development, pxxii. Development is not merely from the general to the special. There are at least four distinct general types, from which the special is developed. The type is fixed in the very earliest stages of development. The embryo of a vertebrate is from the very beginning a vertebrate, p. 220, and it shows at no time any agreement in total organization with any invertebrate. The types are independent of one another, differentiation and development follow a different course in each of them. Not but what some analogies can be found between the very earliest stages of embryos of different type. Thus vertebrate and annulate embryos agree in certain points at the time of the formation of the primitive streak. And in the earliest stage of all, the egg stage, there is probably agreement between all the types. In eggs with yolk, whether vertebrate or annulate, there is always a separation into an animal and a plastic layer. It seems, too, as if a hollow sphere were a constant stage in the development of all animals, pages 224, 258. Apart from these analogies, development takes an entirely independent course in each of the four main types, and no embryo of one of the higher types repeats in its development the peculiar organization of any adult of the lower types. If we consider now development within the type, which is the only legitimate thing to do, we arrive at certain laws governing the relation of embryos to one another. For instance, at a certain stage vertebrate embryos are uncommonly alike. Von Baer had two in spirit which he was unable to assign to their class among amniotes. They might have been lizard, bird, or mammal, he could not say definitely which. 175. Generally, the farther back we go in the development of vertebrates, the more alike we find the embryos. The type characters are first to appear, then the class characters, then the characters distinguishing the lesser classificatory groups. From a more general type the special gradually emerges, p221. The chick is first a vertebrate, then a land vertebrate, then a bird, then a land bird, then a gallinaceous bird, and finally Gallus domesticus. Development within the type is a progress from the general to the special, a real evolution. The more divergent two adults are, the farther back we must go in their development to find an agreement between their embryos. We can sum up the case in the following laws. 1. That the general characters of the big group to which the embryo belongs appear in development earlier than the special characters. In agreement with this is the fact that the vesicular form is the most general form of all, for what is common in a greater degree to all animals than the opposition of an internal and an external surface. 2. The less general structural relations are formed after the more general, and so on until the most special appear. 3. The embryo of any given form, instead of passing through the state of other definite forms, on the contrary separates itself from them. 4. Fundamentally the embryo of a higher animal form never resembles the adult of another animal form, but only its embryo, p224. These laws relating to development within the limits of type are destructive of even a limited application of the theory of parallelism, for not even within the limits of the type is there a real scale which the higher forms must mount. Each embryo develops for itself, and diverges sooner or later from the embryos of other species, the divergence coming earlier the greater the difference between the adult forms. It is only because the lower less differentiated adult forms happen to be little divergent from the generalist or embryonic type, that they show a certain similarity with the embryos of the higher more differentiated members of the group. Such similarity, however, is due to no necessary law governing the development of the higher animals. It is, on the contrary, merely a consequence of the organization of these lower animals, p224. Von Baer goes on to show what are the distinguishing embryological characters of the types and classes, working out a dichotomous schema of development, which each embryo must follow, branching off early or late to its terminal point, according to the lower or higher goal it has to reach. One important consequence for morphology results from von Baer's laws of differentiation within the type. If the embryo develops from the general to the special, then the state in which each organ or organ system first appears must represent the general or typical state of that organ within the group. Embryology will therefore be of great assistance to comparative anatomy, whose chief aim it is to discover the generalist type, the common plan of structure, upon which the animals of each big group are built. And the surest way to determine the true homologies of parts will be to study their early development. For since each organ becomes what it is only through the manner of its development, its true value can be recognized only from its method of formation. At present, we form our judgments by an undefined intuition, instead of regarding each organ merely as an isolated product of its fundamental organ, and discerning from this standpoint the correspondences and dissimilarities in the different types, p233. Parts, therefore, which develop from the same fundamental organ, and in the last resort from the same germ layer, have a certain kinship, which may even reach the degree of exact homology. Now since the mode of development in each type is peculiar to that type, organs of the same name in different types must not necessarily be accounted homologous, even if they correspond exactly with one another in their general functional relations to the rest of the organs. Thus the central nervous system of arthropods must not be homologous with the central nervous system of vertebrates, for it develops in a different manner. So, too, the brain of arthropods or of mollusca is not strictly comparable with the brain of vertebrates. Again, the air tubes or tracheae of insects are, like the trachea and bronchi of many vertebrates, air-breathing organs. but the two organs are not homologous, for the air tubes of vertebrates are developed from the alimentary tube, fundamental organ of the alimentary system, developed from the vegetative layer, while the air tubes of insects arise either by histological differentiation, or by invagination of the skin, p. 236. Organs can be homologous only within the limits of the big groups. There can be no question of homology between members of different types. The development of plants, like the development of animals, is essentially a progress from the general to the special, p. 242. Botanists have not been troubled by any recapitulation theory, and in founding their big groups, acotyledons, monocotyledons, and dicotyledons, upon embryological characters, they were guided by true principles, which ought indeed to be followed in zoology. If we knew the development of all kinds of animals sufficiently well, then the best way to classify them would be according to the characters they show in their early development, for it is in early development that they show the characters of the type in their most generalist form. As it is, we have in our ignorance to establish the big groups by the study of adult structure, but we find, on putting together all we know of comparative embryology, that a classification of animals according to the mode of their development gives, as is only natural, the same four groups as does the study of adult structure. The four types of development are thus: 1. The double symmetrical, which is found in vertebrates. It is called the double symmetrical, because in vertebrates development takes place from a central axis, notochord, in two directions, upwards and downwards, in such a way that two tubes are formed, one above and one below the axis. 2. The second type is the symmetrical, which is shown by annulates. A primitive streak is formed on the ventral surface of the yolk. Development proceeds symmetrically on both sides of the streak. 3. Radiate development is probably typical of the radiate structural type. 4. In the massive type, the development seems to be a spiral one. Common to most modes is a separation of the germ into animal and plastic layers, a separation which seems to be conditioned largely by the presence of yolk. A classification based upon embryological characters ought to be applied even to the lesser groups and would here prove itself of service. Embryology, for instance, fully supports de Blainville's separation of Batrachia from true reptiles 176. For reptiles develop an amnion and Batrachia do not. We come now to the sixth and last scolion. Development is a true evolution of the special from the general, so runs von Bayer's most general law of all. This can be expressed in a slightly different way, and the words which he chooses in the sixth scolion to express this final and most general result are these: the developmental history of the individual is the history of the growing individuality in every respect, p. 263. The greatest modern treatise on embryology ends on a splendid note. One creative thought rules all the forms of life. And more, it is the same thought that in cosmic space gathered the scattered masses into spheres and bound them together in the solar system, the same that from the weathered dust on the surface of the metallic planets brought forth the forms of life. And this thought is not else but life itself, and the words and syllables in which life expresses itself are the varied forms of the living, p. 264. Von Baer reminds one greatly of Cuvier. There is the same sheer intellectual power, the same sanity of mind, the same synthetic grip. Von Baer, like Cuvier, never forgot that he was working with living things. He was saturated, like Cuvier, with the sense of their functional adaptedness. In his paper on the external and internal skeleton 177, he gives a masterly analysis of the functional modifications of the limbs in vertebrates, and the whole paper indeed, with its sober attack on transcendentalism, is a vindication as much of the functional point of view as of the importance of embryology. Both Cuvier and von Baer, by the very sanity of their views, found themselves in partial opposition to the theories current in their time. Cuvier was the critic of Geoffroy and the transcendentalists, of Lamarck and the believers in the échelle d'êtres, evolutionary or ideal. Von Baer also, though influenced greatly by nature philosophy, turned against the exaggerations of the transcendental school, and by his unanswerable criticism of the theory of parallelism took away the ground from those who too easily believed in an historical evolution. 178 We have seen what were von Baer's criticisms of the theory of parallelism. If we turn to the later writings of Cuvier, we find the essential criticism expressed in similar terms. Speaking of an attempt which had been made to show that fish were mollusks developed to a higher degree, he wrote in 1828 179 Let us draw the conclusion that even if these animals can be spoken of as ennobled mollusks, as mollusks raised to a higher power, or if they are embryos of reptiles, the beginnings of reptiles, this can be true of them only in an abstract and metaphysical sense, and that even this abstract statement would be very far from giving an accurate idea of their organization. From the fact that the respiratory and circulatory organs of fish greatly resemble those of tadpoles, the conclusion has been drawn that fish are in a sense embryos of amphibia, p. 547. But this manner of viewing things is none the less vicious, for this reason, that it considers only one or 2 points and neglects all the others, p. 548, and is directly contrary to common sense. There is never a recapitulation of total organizations, only at the most of single organs. It will be remembered that Cuvier opposed and demolished the theory of the échelle d'êtres, not only by showing that there were in nature 4 entirely different plans of animal structure, but also by demonstrating that even the animals of each single embranchement could not readily be arranged in one series, that a serial arrangement was really valid only for their separate organs. Von Baer also held that there are 4 distinct types of structure. He, too, combated the idea of gradation within the limits of the type. In so far as species represent successive stages in the development, the Ausbildung, of the type, so far can the idea of a scale of beings be applied. But the members of a type follow not one line of evolution but several diverging lines, in direct adaptation to different environmental conditions, so that a serial arrangement of them is not as a rule possible. It may be possible to establish a serial arrangement of single organs from the simplest to the most complex. But each organ or organ system will require a different serial arrangement, for the different systems vary on different lines, and an animal may be highly developed in respect of one system and little developed in respect of all the others. Man, for instance, is the highest animal only in respect of his nervous system. The idea of the scale of beings has therefore only a very limited application even within the limits of the type. Applied to the whole animal kingdom it becomes merely absurd. Another point of resemblance between Cuvier and von Baer was that Cuvier, though essentially a student of adult structure, did recognize the importance of embryology. Following up some observations of Dutrochet, he studied the fetal membrane of mammals and tried to establish their homologies. 180 And in his criticism of the vertebral theory of the skull he advanced as an argument against the basis phenoid being a vertebral centrum the fact, established by Kirkring, 1670, that it develops from 2 centers. 181 Von Baer's relation to transcendental anatomy was in some ways a close one, though he was a trenchant critic of the extreme views of the school. 182 He took from Oken the idea that a simple fundamental plan rules the organization of all vertebrates, that jaws and limbs are modifications of one fundamental form is readily apparent, and, after Oken, the fact ought to be accepted by the majority of those naturalists who do not refuse to admit the existence of a general type, from which the diversity of structure is developed. p. 192. He accepted the vertebral theory of the skull in its main lines, and used his embryological knowledge to support the idea that jaws correspond to limbs, the latter point as part of the transcendental idea that the hind end of the body repeats the organization of the anterior part, p. 192. The particular form which his theory of the relation of jaws to limbs took is shown in the following passage: the maxillary bone has the significance of an extremity and at the same time that of a rib or lower arch of a vertebra, just as the pelvic bones unite in themselves the signification of ribs and proximal members of the hinder extremity. Meckel's Archive, p. 367, 1826. He appreciated the morphological idea of the serial repetition of parts, and gave it accurate formulation. The whole vertebrate body, he considered, was composed of a longitudinal series of morphological elements, each of which was made up a section from each of the fundamental organs of vertebra, a section of the nerve cord, and so on, Entwicklungsgeschichte, 2, p. 53. Groups of these morphological elements formed morphological divisions, such as the vertebral segments of the head with their highly developed neural arches, or the segments of the neck with their undeveloped hemal arches. The morphological elements are clearly shown only in the animal parts, but there are indications in the embryo of a segmentation also of the vegetative parts, the gill slits, for instance, and the vascular arches. The vegetative parts, however, develop on the whole unsymmetrically, cf. Shaw. These elements which von Baer distinguishes are morphological units, as he himself points out, contrasting them with organs which are not usually units in a morphological sense. We call organ, he writes, each part that has by reason of its form or its function a certain distinctiveness, but this concept is very indefinite, and possesses, from a morphological point of view, little value. For this reason it seems necessary to introduce into scientific morphology the concepts of morphological elements and divisions. 2, p. 84. Von Baer exercised a very considerable influence upon the subsequent trend of morphological theory. By his criticism of the Meckel-Serres theory, he rid morphology for a time of an idea which was leading it astray. By his substitution of the law that development is always from the general to the special, he set morphologists looking for the archetype in the embryo, not in the adult alone, and made them realize that homologies could often best be sought in the earliest stages of development. By formulating the germ layer theory, he supplied morphologists with a new criterion of homology, based upon the special relations of the parts, germ layers, which are first differentiated in all development. He made the study of development an essential part of morphology. 166 Degeneratione Animalium. 167 De Formato Fetu. 1600, De Formatione Foetus, 1604. 168 Exercitations Degeneratione Animalium, 1651. 169 De Formatione Puli in Ovo, 1673, De Ovo Incubato, 1686. 170 De Formatione Puli in Ovo, 1757-8, Sur la formation du cordans le poulet, 1758. 171 Theoria Generationis, 1759, De Formatione Intestinorum, 1768-9. 172 Beitrag zur Entwicklung des Hähnchens im Ei. Würzburg, 1818. Also in Latin in shorter form, 1817. 173 Untersuchung die Entwicklungsgeschichte Fisk, Leipzig, 1835. 174 Cuvier, in 1812, NMUSD Hist. Nat. 19, von Baer in 1816, Nova Acta Academic Nat Cur. C. Entwicklungsgeschichte Thera, I. P7, FN 175. Compare a parallel passage in Prévost et Dumas. At the very first sight one will be struck with the resemblance between the forms of the very early embryos of these two classes, a resemblance so extraordinary that one cannot refuse to admit the conclusions resulting from it. The resemblance is so striking that one can defy the most experienced observer to distinguish in any way the embryos of dog or rabbit, from those of fowls or ducks of a corresponding age. Ansi Nat. 3, p. 132, 1824. 176 de l'Organisation de Animaux, I. p. 140, 1822. 177 Über das Äußere und die innere Skelett, Meckel's Archiv für Anatomy, pages 327-76, 1826. C. 2, his Entwicklungsgeschichte, I. pages 181, ff 178. Von Baer wrote an appreciative biography of Cuvier, published posthumously in 1897, Lebensgeschichte Cuviers, ed. Elstede. French trans. In Ansi Nat. Zoel, 9, 1907. 179 Cuvier et Valenciennes, Histoire naturelle des poissons, I. p. 550. 180 MEM. MUSD Hist. Nat. 3, pages 98 to 119, 1817. 181 Leçons d'anatomie comparée, 3rd ed., volume I, p. 414, Bruxelles, 1836. 182 In the aforementioned paper in Muller's Archive he criticizes Carus vigorously and is sarcastic on Geoffroy. Chapter X The embryological criterion. Pander's work of 1817 was the forerunner of an embryological period in which men's hopes and interests centered round the study of development. With bewilderment we saw ourselves transported to the strange soil of a new world, wrote Pander, and many shared his hopeful enthusiasm. K. E. von Bayer's Entwicklungsgeschichte was by far the greatest product of this time, but it stands in a measure apart. We have in this chapter to consider the lesser men who were Bayer's contemporaries, friends, followers, or critics. It was largely a German science, this new embryology, and its leaders were all personally acquainted. Pander, von Baer, and Rathke were on friendly terms with one another. Von Baer dedicated his masterwork to Pander, Rathke dedicated the second volume of his Abhandlungen to von Baer. Interest in the new science was, however, not confined to Germany. In Italy, Rusconi commenced in 1817 his pioneer researches on the development of the amphibia with the Descrizione anatomica degli organi della circolazione del larva del salamandra aquatic, Pavia, in which he traced the metamorphoses of the aortic arches. This was followed in 1822 by his Amours de Salamandres aquatiques, Milan, and in 1826 by his Memoire du développement de la grenouille, Milan. In this last paper he described how the dark upper hemisphere of the frog's egg grows down over the lower white hemisphere and leaves free only the yolk plug. He observed the segmentation cavity and the archenteron, but thought that the former became the alimentary canal. He observed and interpreted rightly the formation of the medullary folds. The circular blastopore in the frog in later years often went by the name of the anus of Rusconi. In France Dutrochet 183 investigated the fetal membranes in various vertebrate classes. Prévost and Dumas studied the very earliest stages of development in birds, mammals, and amphibia, Ansi Nat. 2, 3, 1824, 12, 1827. Fig. 8. Gill slits of the pig embryo. After Rathke. A little later came Doug's studies of the osteology and myology of developing amphibia, 1834, 184, and Kost's careful researches into the early developmental history of mammals 185. It was in 1825 that Heinrich Rathke, 1793–1860, published his famous discovery of gill slits in the embryo of a mammal 186, a discovery which aroused considerable interest, and greatly stimulated embryological research. He describes how in a young embryo of a pig he saw 4 slits in the region of the neck, going right through into the esophagus. They were separated by partitions which he called Kiemenbogen, gill arches, and immediately in front of the first gill slit lay the developing lower jaw. He compared these gill slits with those of a dogfish. We reproduce his drawing of the pig embryo, Isis, PL4, Figure 1. Later in the same year Rathke discovered gill slits in the chick 187, in this case finding only 3. He described growing out from in front of the first slit a structure which he compared to the operculum or gill cover of a fish. These discoveries were confirmed and extended for the chick 188 by the embryologist Huschke, a pupil of Oken. Like Rathke, he found only 3 indubitable gill slits, but he noticed that the body wall in front of the first gill slit was really composed of 2 arches, which were on the whole similar to the gill arches. The hinder of these 2 seemed to him to be a horn of the hyoid, the front one, which was bent at an angle, to be the rudiment of the upper and lower jaws, p. 401. Between these 2 arches he found an opening, just as between 2 gill arches a gill slit. This opening led into the mouth cavity, and according to Huschke it became the external ear passage. He discovered also 3 pairs of aortic arches in close relation with the gill arches, so close indeed, that he did not hesitate to call them gill arteries, and to recognize their resemblance with the aortic arches of fish. He traced, in part at least, the metamorphosis which these aortic arches undergo. This part of his discovery he developed in fuller detail in a paper of 1828–189 in which he gave some excellent figures. Shortly after Huschke's first paper, von Baer published his views and observations on this subject in a short memoir in Meckel's Archive 190. In this paper he confirmed Rathke's discovery, and described the slits and arches in the dog and the chick. Both Rathke and he found gill slits in the human embryo about this time, p. 557. There were generally present, he found, 4 gill slits, and, as Rathke had suggested, the first gill arch became the lower jaw. Von Baer also confirmed Rathke's discovery of the operculum, assigning it, however, to the second gill arch. He refused to accept Huschke's derivation of the auditory meatus from the first gill slit. Von Baer saw what had escaped Rathke and Huschke, that there were, not 3 nor 4, but as many as 5 aortic arches. In his view of the metamorphosis of the aortic arches in the chick, the first 2 pairs disappeared completely, the third pair gave rise to the arteries of the head and the forelimbs, the right side of the 4th arch became the aorta, the left half of the 4th and the right half of the 5th arch became the pulmonary arteries, while the left half of the 5th arch disappeared. This schema, which for the last 3 arches was the same as Huschke's, von Baer upheld for the chick even in the 2nd volume of his Entwicklungsgeschichte, p. 116, he rectified it, however, for mammals in the same volume, p. 212, deriving both pulmonary arteries from the 5th arch, and the aorta from the 4th left. He fully recognized the great analogy of the embryonic arrangement of gill arches and gill arteries in tetrapoda with their arrangement in fish, pages 53, 73. Huschke, in a paper of 1832–191 chiefly devoted to the development of the eye, figured and described the developing upper and lower jaws, and maintained against von Baer that the first slit turns into the auditory meatus and the eustachian tube. These were the first papers of the embryological period. Before going on to discuss the principles which guided embryological research during the next 10 or 20 years, it is convenient to note what were the main lines of work characterizing the period. The typical figure of the period is Rathke, who produced a great deal of first-class embryological work. He was, even more than von Baer, a comparative embryologist, and there were few groups of animals that he did not study. His first large publication, the Beiträge zur Geschichte der Tierwelt, I-4, Halle, 1820-27, contained much anatomical work in addition to the purely embryological. He commenced here his series of papers on the development of the genital and urinary organs, continued in the Abhandlung zur Bildungs- und Entwicklungsgeschichte Menschenende Tiere, I-2, Leipzig, 1832-3. A fellow worker in this line was Johannes Müller, whose Bildungsgeschichte der Genitalien, Düsseldorf, appeared in 1830. In a memoir on the development of the crayfish which appeared in 1829, 192 Rathke found in an invertebrate confirmation of the germ layer theory propounded by Pander and von Baer. He was greatly struck by the inverted position of the embryo with respect to the yolk. In following out the development of the appendages, he noticed how much alike were jaws and legs in their earliest stage, and how this supported Savina's contention that the limbs of arthropods belonged to one single type of structure. In his paper, 1832, on the development of the freshwater isopod, Acellus 193, Rathke returns to this point. Commenting on the original similarity in development of antennae, jaws, and legs, he writes, "Whatever the doubts one may have reserved as to the intimate relation existing between the jaws and feet of articulate animals after the researches of Savina on this subject and mine on developing crayfish, they must all fall to the ground when one examines with care the development of the freshwater Acellus, p. 147 of French translation." Further comparative work by Rathke is found in the 2 volumes of Abhandlungen and in a book, Zur Morphology, Reisbemerkungen aus Turien, 1837, which contains embryological studies of many different types, including a study of the uniform plan of arthropod limbs. Later on, Rathke devoted himself more to vertebrate embryology, producing among other works his classical papers on the development of the adder, 1839, of the tortoise, 1848, and of the crocodile, 1866. He laid the foundations of all subsequent knowledge of the development of the blood vascular system in a series of papers of various dates from 1838 to 1856. The diagrams in his paper on the aortic arches of reptiles, 1856, were for long copied in every textbook. Rathke was a foremost worker in another important line of embryological work, the study of the development of the skeleton and particularly of the skull. We shall discuss the history of the embryological study of the skull in some detail below. Meantime, we note the 2 other important lines of research which characterize this period. One is the intensive study of the development of the human embryo, a study pursued by, among others, Pockels, Seeler, Breschet, Velpo, Bischoff, Weber, Müller, and Wharton Jones. 194. The other important line, the early development of the mammalia, was worked chiefly by Valentine. 195, Cost 196, and, above all, by Bischoff, whose series of papers 197 was justly recognized as classical. What interests us chiefly in the work of this embryological period is, of course, the relation of embryology to comparative anatomy and to pure morphology. The embryologists were not slow to see that their work threw much light upon questions of homology, and upon the problem of the unity of plan. Von Baer, we have seen, recognized this clearly in 1828, Rathke, in one of his most brilliant papers, the Anatomische Philosophische Untersuchungen über den Chemenapparat und das Zungenbein, Riga and Dorpat, 1832, used the facts of development with great effect to show the homology of the gill arches and hyoid throughout the vertebrate series. Johannes Müller made great use of embryology in his classical Vergleichende Anatomie der Myxonoiden, I Thiel, 1836, and, according to his pupil Reichert, firmly held the opinion that embryology was the final court of appeal in disputed points of comparative anatomy. 198 Reichert himself in a book of 1838, Vergleichende Entwicklungsgeschichte des Kopfs der nackten Amphibien, discussed the two different methods of arriving at the type: the anatomical method of comparing adults, and the embryological method of comparing embryogenes. Of the embryological method, he says, its aim is to distinguish during the formation of the organism the originally given, the essence of the type, and to classify and interpret what is added or altered in the further course of development. Embryologists watch the gradual building up of the organism from its foundations, and distinguish the fundament, the primordial form, the type, from the individual developments. They reach thus, following nature in a certain measure, the essential structure of the organism, and demonstrate the laws that manifest themselves during embryogeny. p. 6. The embryologists, influenced in this greatly by von Baer, gradually felt their way to substituting for the archetype of pure morphology what one may perhaps best call the embryological archetype. How the transition was made we can best see by following out the course of discovery in one particular line. We choose for this purpose the development of the skull, a subject which excited much interest at this time and upon which much quite fundamental work was done, particularly by Rathke and Reichert. Following up his discovery of gill slits and arches in the embryos of birds and mammals, Rathke in two papers of 1832-199 and 1833-200 worked out the detailed homologies of the gill arches in the higher vertebrates. He describes how in the embryo of the blenny there is a short, thick arch between the first gill slit and the mouth. A furrow appears down the middle of the arch dividing it incompletely into two. In the anterior halves a cartilaginous rod is developed which is connected with the skull. These rods become on either side the lower jaw and quadrate. In the posterior halves two similar rods are formed which develop into the hyoid. The hyoid is at first connected with the skull, but afterwards frees itself and becomes slung to the quadrate. From the hinder edge of the hyoid arch grows out the membranous operculum, in which develop later the opercular bones and branchiostegal rays. The upper jaw is an independent outgrowth of the serous layer. The serial homology of the lower jaw and quadrate with the hyoid and with the true gill arches was thus established in fish, and Rathke had little difficulty in demonstrating a similar origin of lower jaw and hyoid in the embryos of higher vertebrates. He could even, as we have noted before, find the homologue of the operculum in a flap which grows out from the hyoid arch in the embryo of birds. But Rathke could not altogether shake himself free from the transcendental notion of the homology of jaws with ribs, and this led him to draw a certain distinction between the first two and the remaining gill arches, by which the homology of the former with the ribs was asserted and the homology of the latter denied. He thought he could show that the skeletal structures, lower jaw, quadrate, and hyoid, of the first two arches were formed in the serous layer, just like true ribs, and like them in close connection with the vertebral skeletal axis. The other, true, gill arches appeared to him to be formed in the mucous layer, in the lining of the alimentary canal. They had no direct connection with the vertebral column, and seemed therefore to belong to what Karras 201 had called the visceral or splanknoskeleton. He did not, however, let this distinction hinder him from asserting the substantial homology of all the gill arches inter esse, The first two included Rathke's discoveries relative to the development of the jaws, the hyoid, and the operculum, enabled him to make short work of the homologies proposed for them by the transcendentalists. He could prove from embryology that the jaws were not the equivalent of limbs, as so many Oceanians believed. He could reject, with a mere reference to the facts of development, Geoffroy's comparison of the hyoid and the branchiostegal rays in fish with sternum and ribs. He could show the emptiness of the attempts made by Carus, Treviranus, de Blainville, and Geoffroy, to establish by anatomical comparison the homologies of the opercular bones, for he could show that these bones were peculiar to fish, and were scarcely indicated, and that only temporarily, in the development of other vertebrates. 202 He did not, however, himself realize the relation of the earocicles to the gill arches, though he knew that Spix and Geoffroy were quite wrong in homologizing them with the opercular bones in fish. He described, it is true, the development of the external meatus of the ear and the eustachian tube from the slit which appears between the first and the second arch, as Huschka had done before him. He described, in confirmation of Meckel, the Mechelian process of the hammer running down inside the lower jaw, but the discovery of the true homologies of the earocicles was not made until a year or two later by Reichert. In his further study of the development of Blennius viviparus, Rathke observed some important facts about the development of the vertebral column and skull. He found that the vertebral centra were first formed as rings in the chorda sheath, which give off neural and hemal processes. The vertebra later ossifys from 4 centers. The chorda, notochord, is prolonged some little way into the head, and the base of the cranium is formed by the expanded sheath, which reaches forward in front of the end of the notochord. This cranial basis shows a division into 3 segments, in which Rathke was inclined to see an indication of 3 cranial vertebrae. It turned out that this division into 3 segments did not really exist, and Rathke later acknowledged that he had made an error of observation. The side walls of the skull grow out from this base and form a fibrous capsule for the brain. The cranial section of the chorda itself shows no sign of segmentation, but later on the cranial portion of the chorda sheath ossifys, like the vertebrae, from several centers. The vomer, which, in the classical form of the vertebral theory of the skull, was the centrum of the 4th, or foremost, cranial vertebra, does not, according to Rathke, develop in continuity with the cranial basis and the chorda sheath, but develops separately in the facial region. Von Baer, like Rathke at this time, was also to some extent a believer in the vertebral theory of the skull. In his second volume, 1834, pub 1837, he holds that the development of the skull, as the sum of the anterior vertebral arches, is in general the same as that of the other neural arches, and is modified only by the great bulk of the brain, Entwicklungsgeschichte, 2, p. 99. He had, however, some doubts as to the entire correctness of the vertebral theory, doubts suggested by a study of the developing skull. In the course of the formation of the head in the higher animals, something additional is introduced which does not originally belong to the cranial vertebrae. At first we see the vertebration in the hinder region of the skull very clearly. Afterwards it becomes suddenly indistinct, as if some new formation overlaid it, p. 194. Even more clearly is his doubt expressed in his paper on Cyprinus. Upon the formation of the vertebral column only this need be said, that at this stage the notochord is very clearly seen, and the upper and lower arches and spinous processes are visible right to the end of the tail, but the separation into vertebrae ceases abruptly where the back passes into the head. I do not hesitate to assert that bony fish, too, have at this stage an unsegmented cartilaginous cranium, as cartilaginous fish have all their life, the prominences and hollows of which constitute its only resemblance with the vertebral type, 1835, p. 19. A convinced supporter of the vertebral theory was Johannes Müller, who, in his classical memoir on the myxinoids 203 discussed at some length the relation between the development of the vertebrae and the development of the skull. His memoir is principally devoted to comparative anatomy, but in treating of the skeleton he pays much attention to development. He describes the formation of the vertebrae in elasmobranch embryos. For the facts regarding other vertebrates he relies largely on work by Rathke, Blenius, 1833, and Duggs, 1834. He recognizes as the basis of his comparisons the homology of the notochord in all vertebrate embryos with the persistent notochord which forms the chief part or the whole of the vertebral column in the cyclostomes. The notochord possesses an inner and an outer sheath, and the outer sheath is continuous with the basis cranii, p. 92. It is in the outer sheath that the vertebrae develop from 4 separate pieces, in fish at least, plus an additional element which helps to form the centrum. The skull of vertebrates consists, according to Müller, of 3 vertebrae, whose centra are the basia occipital, the basis sphenoid and the presphenoid. Other bones besides those belonging to the vertebrae are present, but this formation out of 3 vertebrae gives the essential schema for the skull. Now the brain capsule, like the sheath of the spinal cord, is a development from the outer sheath of the notochord. If the skull consists of vertebrae, we should expect the centra of the skull vertebrae to develop in the outer sheath at the sides of the cranial section of the notochord as 2 separate halves. Just as do the bodies of the vertebrae, we should expect further the cartilaginous side walls of the cranium to develop in the membranous brain sheath, just as the neural arches develop in the membranous sheath of the spinal column. In Rathke's discovery, of a segmentation of the basis cranii into 3 parts, and of the isolated formation of the vomer, Müller sees a confirmation of his view that the skull is composed of 3 and not 4 vertebrae. But there is nothing in Rathke's observations to support the idea that the centra of the cranial vertebrae are formed from separate halves. Müller has to be content with a reference to the state of things in Amosates, which, by the way, he did not know to be the young of Petromizon. In the simple skull of Amosates the base is formed chiefly by 2 cartilaginous bars lying more or less parallel with the longitudinal axis of the skull and embracing with their hinder ends the cranial portion of the notochord. These bars, declares Müller, are clearly the still separate halves of the pars basilaris cranii, and represent the divided centra of the 2 hinder cranial vertebrae. To complete the parallel between the development of the skull and of the vertebrae, it would have been necessary to show that the side walls of the cranium developed in a similar manner from separate pieces. Müller could not prove this point from the available embryological data, and indeed the facts which he did use had to be twisted to suit his theory. A curious apparent confirmation of his idea that the centra of the cranial vertebrae are formed from separate halves was supplied in 1839 by Rathke's discovery of the trabeculae in the embryonic skull of the adder. The next big step in the study of the development of the skull was taken by a pupil of Müller, C. B. Reichert, who showed in his work very distinct traces of his master's influence. Reichert's first and most important contribution to the subject was his paper on the metamorphosis of the gill, or, as he called them, the visceral arches in vertebrates 204, particularly in the 2 higher classes. Reichert describes the similar origin in embryo of bird and mammal, pig, of 3 visceral arches. These arches stand in close relation to the 3 cranial vertebrae which Reichert, like Müller, distinguishes. He makes the retrograde step of admitting only 3 aortic arches, and he is not inclined to consider the 3 visceral arches as equivalent to the gill arches of fish. In his opinion they have more analogy with ribs, though differing somewhat from ribs in their later modifications. The visceral arches are processes of the visceral plates, von Baer, which grow downwards and meet in the middle line, leaving between one another and the undivided body wall 3 visceral slits opening into the pharynx. The first visceral process is different in shape from the others, for it sends forward, parallel with the head and at right angles to its downward portion, an upper portion in which later the upper jaw is formed. The other two processes are straight. From the hinder edge of the second visceral arch there develops, as Rathke had seen, a fold which is comparable with the operculum of fish. The first slit develops externally into the ear passage, internally into the eustachian tube, and in the middle a partition forms the tympanic ring and tympanum. Inside each of the visceral processes on either side a cartilaginous rod develops. In the first process this rod shows three segments, of which the first lies inside that portion of the process which is parallel with the head. This upper segment forms the foundation for the bones of the upper jaw. The lowest segment of the cartilaginous rod becomes Meckel's cartilage, and on the outer side of this the bones of the lower jaw are formed. The middle segment becomes in mammals the incus, one of the earosicles, and in birds the quadrate. Meckel's cartilage, which was discovered by Meckel 205 in fish, amphibians, and birds, is a long strip of cartilage which runs from the earosicle known as the hammer in mammals 206 to the inside of the mandible. Reichert shows how this relation comes about. Fig 9 Meckel's cartilage and earosicles in embryo of pig. After Reichert, A. Mandible. H. Hammer. K. Incus. G. Meckel's cartilage. I. Handle of hammer. N. Stapes. The hammer, according to his observations on the embryo of the pig, is simply the proximal end of Meckel's cartilage, which later becomes separated off from the long distal portion, see Fig 9. The third earosicle of mammals, the stapes, comes not from the first arch but from the second. The cartilaginous rod of the second arch segments like the first into three pieces. Of these the uppermost disappears, the middle one, which lies close up to the labyrinth of the ear, becomes the stapes, and the lowest becomes the anterior horn of the hyoid. The stapes forms a close connection with the hammer and the incus. In birds, where there is a single earosicle, the columella, the middle piece of arch I forms, as we have seen, the quadrate, by means of which the lower jaw is joined to the skull. The proximal end of Meckel's cartilage, which in mammals forms the hammer, here gives the articular surface between the lower jaw and the quadrate. The columella is formed from the middle piece of the three into which the cartilage of the second arch segments. It is, therefore, the homologue of the stapes in mammals. The third arch takes a varying share, together with the second, in the formation of the hyoid apparatus. In this paper Reichert made a distinct advance on the previous workers in the same field Rathke, Huschke, von Baer, Martin St. Ange, Duggs. Huschke was indeed the first to suggest that both upper and lower jaws were formed in the first gill arch. But both von Baer and Rathke 207 held that the upper jaw developed as a special process independent of the lower jaw rudiment, and the actual proof that the upper jaw is a derivative of the first visceral arch seems to have been first supplied by Reichert. His brilliant work on the development of the earosicles founded what we may justly call the classical theory of their homologies. His views were attacked and in some points rectified, but the main homologies he established are even now accepted by many, perhaps the majority of morphologists. In a paper of 1838 on the comparative embryology of the skull in Amphibia 208, Reichert added to his results for mammals and birds an account of the fate of the first and second visceral arches in Anura and Urodela. The first visceral arch, he found, gave in Amphibia practically the same structures as in the higher vertebrates. Its skeleton segmented, as in mammals and birds, into three parts. The upper part gave rise to the palatine and pterygoid in Anura, but seemed to disappear in Urodels, where the so-called palatine and pterygoid developed in the mucous membrane of the mouth. The middle part gave, as in birds, the quadrate, which formed a suspensorium for both arches. The lower part, as Meckel's cartilage, formed a foundation for the bones of the lower jaw. Of arch 2, the lower part became the horn of the hyoid, the upper part had a varying fate. In some Anura it formed the ossicle of the ear, homologue of the columella of birds and the stapes of mammals, in others it disappeared. In reptiles the upper segment of the second arch formed, as in birds, the columella. The account of the metamorphoses of the visceral arches in amphibia forms only a small part of Reichert's memoir of 1838, the chief object of which was to discover the general types of the vertebrate skull, and to follow out its modifications in the different classes. Von Baer had shown that the generalist type appeared most clearly in the early embryo. Reichert therefore sought the archetype of the skull in the developing embryo. He brought to his task the preconceived notion that the skull could be reduced to an assemblage of vertebrae, but he saw that comparative anatomy alone could not effect this reduction. He had recourse, therefore, to embryology, hoping to find in the simplified structure of the embryo clear indications of three primitive cranial vertebrae, p. 121, 1837. Fig. 10. Cranial vertebrae and visceral arches in embryo of pig. Ventral aspect. After Reichert. In the head he distinguished two tubes, the upper formed by the dorsal plates, the lower by the ventral or visceral plates. Both of these tubes were derived from the serous or animal layer, cf. von Baer, Supra, p. 118. The walls of the lower tube were formed by the visceral processes, within which later the skeleton of the visceral arches developed. The walls of the upper tube formed the bones and muscles of the cranium proper. The facial part of the head was formed by elements from both upper and lower tubes. The dorsal tube showed signs of a division into three cranial vertebrae, Urwurbeln, primitive vertebrae. In mammals and birds, as Reichert had shown in his 1837 paper, the three cranial vertebrae were indicated by transverse furrows on the ventral surface of the still membranous skull, see Fig. 10, p. 148. Even in mammals and birds, however, the positions of the eye, the ear labyrinth, and the three visceral arches were the safest guides to the delimitation of the cranial vertebrae, pages 134 to 138, 1837. In amphibia generally there were no definite lines of separation on the skull itself. At this stage, he writes of the cartilaginous cranium of the frog, we find no trace of a veritable division into vertebrae in the cartilaginous trough formed by the basis cranii and the side parts. On the contrary, it is quite continuous, as it is also in the higher vertebrates during the process of chondrification, p. 44, 1838. The vertebrae in the membranous or cartilaginous skull could be delimited in amphibia by the help of the eye and the ear labyrinth, which lie more or less between the first and the second and third vertebrae, but, above all, by the vesicles of the brain. As in the higher vertebrates, the visceral arches are associated with the cranial vertebrae as their ventral extensions, being equivalent to the visceral plates which form the ventral portion of the primitive vertebrae or primitive segments of the trunk. If the three cranial vertebrae are not very distinct in the early stages of development when the skull is still membranous or cartilaginous, they become clearly delimited when ossification sets in. Three rings of bone forming three more or less complete vertebrae are the final result of ossification. The composition of these rings is as follows: base, sides, top. First vertebra presphenoid orbitus phenoids frontal, second vertebra basis phenoidalis phenoids parietals, third vertebra basia occipital ex occipitals supraoccipital. The other bones of the skull are not included in the vertebrae, and this is in large part due to the fact that the sense capsules are formed separately from the cranium, p. 29, 1838. The ear labyrinth, it is true, fuses indissolubly with the cranium at a later period, but the bones which develop in its capsule are not for all that integral parts of the primitive cranial vertebrae. This point, it is interesting to note, had already been made by Oken in his program, 1807. But many of the bones developed in relation to the sense organs can find their place in the generalist embryonic schema or archetype of the vertebrate skull, for they are of very constant occurrence during early development. Having arrived at a generalist embryonic type for the vertebrate skull, of which the fundamental elements are the three cranial vertebrae and their arches, Reichert goes on to discuss the particular forms under which the skull appears in adult vertebrates. He accepts in general von Bayer's law that the characters of the large groups appear earlier in embryogeny than the characters of the lesser classificatory divisions. When we observe new and not originally present rudiments in very early embryonic stages, as, for instance, that for the lacrimals, the probability is that they belong to the distinctive development of one of the larger vertebrate groups. From these are to be carefully distinguished such rudiments as arise later during ossification, mostly as ossa intercalaria, in order to give greater strength to the skull in view of the greater development of the brain, etc. The latter give their individual character to the smaller vertebrate groups, and comprise such bones as the vomer, the wormian bones, the lowermost turbinal, etc. p. 63, 1838. He did not accept the Meckel-Serres law of parallelism. He recognized the great similarity between the unsegmented cartilaginous cranium of elasmobranchs, and the primordial cranium of the embryos of the higher vertebrates, but he did not think that the cranium of elasmobranchs was simply an undeveloped or embryonic stage of the skulls of the higher forms. Rather do the holocephala, plagiostomata, and cyclostomata appear to us to be lower developmental stages individually differentiated, so that the other fully differentiated vertebrates cannot easily be referred directly to their type, p. 152, 1838. The skull of these lower fishes is itself a specialized one, it is an individualist modification of a simple type of skull. And this holds good in general of the skulls of the lower vertebrates. They are individualist exemplars of a simple general type, not merely unmodified embryonic stages of the greatly differentiated skulls of the higher vertebrates, p. 250, 1838. Differentiation within the vertebrate phylum is therefore not uniserial, but takes place in several directions. Reichert describes two sorts of modifications of the typical skull class: modifications and functional modifications. The causes of the modifications which characterize classificatory groups are unknown. The second class of modifications occur in response to adaptational requirements. Reichert's two papers are of considerable importance, and Muller's remark in his review 209 of them is on the whole justified. These praiseworthy investigations supply from the realm of embryology new and welcome foundations for comparative anatomy, Pekelskii. The development of the skull was, however, more thoroughly worked out by Rathke, and with less theoretical bias. In his classical paper on the adder 210, this memoir of Rathke's is an exhaustive one and deals with the development of all the principal organ systems, but particularly of the skeletal and vascular. He confirmed in its essentials Reichert's account of the metamorphoses of the first two visceral arches, describing how the rudiment of the skeleton of the first arch appears as a forked process of the cranial basis, the upper prong developing into the palatine and pterygoid, the lower forming Meckel's cartilage, while the quadrate develops from the angle of the fork. The actual bone of the upper jaw, maxillary, develops outside and separate from the palatopterygoid bar. The cartilaginous rod supporting the second visceral arch divides into three pieces on each side, of which the lower two form the hyoid, the uppermost the columella. Like Reichert, he held the visceral arches to be parts of the visceral plates, containing, however, Elements from all three germ layers, the serous, mucous, and vessel layers. The first gill slit, or, as Rathke here prefers to call it, pharyngeal slit, closes completely in snakes and in urodels. It forms the eustachian tube in all other tetrapoda. As regards the vertebrae, Rathke describes them as being formed in the sheath of the chorda from paired rudiments, each of which sends 2 branches upwards, and 2 branches downwards. The 2 inner pairs of processes coalesce round the chorda, and later form the centrum. The upper outer pair meet above the spinal column, the lower outer pair form ribs. The odontoid process of the axis vertebra is the centrum of the atlas, p. 120. The formation of vertebral rudiments begins close behind the ear labyrinth, but in front of this the chorda sheath gives origin to a flat membranous plate which afterwards becomes cartilaginous. This plate reaches forward below the third cerebral vesicle as far as the infundibulum. The notochord ends in this plate, which is the basis cranii, just at the level of the ear labyrinth. In no vertebrate does the notochord extend farther forward, p. 122. The basis cranii gives off 3 trabeculae. The middle one is small and sticks up behind the infundibulum. It is absent in fish and amphibia, and soon disappears during the development of the higher forms. The lateral trabeculae are long bars which curve round the infundibulum and reach nearly to the front end of the head. Together they are lyre-shaped. The cranial basis and the trabeculae are formed, like the vertebrae, in the sheath of the notochord, and the only differences between the two in the early stage of their development are that the formative mass for the cranial basis is much greater in amount than that for the vertebrae, and that the cranial basis by means of its processes, the trabeculae, reaches well in front of the terminal portion of the notochord, p. 36. The capsule for the ear labyrinth develops quite independently of the cranial basis and the notochord. It resembles on its first appearance, in form, position, composition, and connections, the ear capsule of cyclostomes, and so do the ear capsules of all embryonic vertebrates, p. 39. It manifests clearly the embryonic archetype. There exists one single and original plan of formation, as we may suppose, upon which is built the labyrinth of vertebrates in general, p. 40. When ossification sets in, the ear capsule forms 3 bones, of which 2 fuse with the supraoccipital and exoccipitals. During the formation of the ear capsule the cranial basis develops from a plate to a trench, for in its hinder section the side parts grow up to form the side walls of the brain, in exactly the same way as the processes of the vertebral rudiments grow up to enclose the spinal column, pages 122, 192. The foundations of the skull are now complete, and ossification gradually sets in. Fig. 11 Embryonic cranium of the adder. Ventral aspect. After Rathke, A. Basicipedal. D. Basis phenoid. G. Trabeculae. B. Exoccipitал. C. Illus phenoid. H. Foramen. C. Ear capsule. F. Orbitus phenoid. I. Tuitary space. The basicipedal is formed in the posterior part of the basis cranii, and the exoccipitals in the side walls of the trench in continuity with the fundament of the basicipedal, see Fig. 11. The supraoccipital is formed in cartilage above the exoccipitals. The basis phenoid develops, like the basicipedal, in the flat basis cranii, but towards its anterior edge, between the large foramen, H, and the pituitary space, I. It is formed from 2 centers, each of which is originally a ring round the carotid foramen. The presphenoid develops in isolation between the lateral trabeculae, just behind the point where they fuse. The side parts of the basis phenoid and presphenoid, forming the illus phenoids and the orbitus phenoids respectively, develop in cartilage separately from the cranial basis, not like the exoccipitals in continuity with it. The hinder parts of the trabeculae become enclosed by two processes of the basis sphenoid, their front parts remain in a vestigial and cartilaginous state alongside the presphenoid. The frontals and parietals show a peculiar mode of origin in the adder, differing from their origin in other vertebrates. The frontals develop in continuity with the orbitasphenoids, the parietals in continuity with the elasphenoids, and so have much resemblance with the vertebral neural arches which surround the spinal column, p. 195. Through Rathke's work, the real embryonic archetype of the vertebrate skull was for the first time disclosed. Rathke discussed this archetype and its relation to the vertebral theory of the skull in another paper of the same year, 1839, but before going on to this paper, we shall quote from the paper on the adder the following passage, remarkable for the clear way in which the idea of the embryological archetype is expressed. Whatever differences may appear in the development of vertebrates, there yet exists for the different classes and orders a universally valid idea, plan, schema, or type, ruling the first formation of their separate parts. This idea must first be worked out, though possibly with modifications, before more special ideas can find play. The result of the latter process, however, is that what was formed by the first idea is not so much hidden as partially or wholly destroyed, p. 135. Rathke's general paper on the development of the skull in vertebrates 211 treats the matter on a broader comparative basis than his paper on the adder, and takes into account all the vertebrate classes, insofar as their development was then known. He here makes the interesting suggestion, later entirely confirmed, that the basis cranii or basilar plate is first laid down as two strips, one on each side of the chorda, the structures now known as parachordals, pages 6, 27. For this supposition, he thinks, speaks the structure of the skull in Ammosates, which in this respect is the simplest of all vertebrates, pages 6, 22. In Ammosates, as Johannes Müller had shown, the foundation of the skull is formed by two long cartilaginous bars, between the hinder portions of which the notochord ends. In these Rathke was inclined to see the homologues of his trabeculae, and of the parachordals which he was ready to assume from his embryological observations. Müller was, of course, very ready to accept Rathke's opinions on this subject, for he considered that they supported his own theory of the vertebral nature of the skull. After describing in his Handbuch der Physiologie the cartilaginous bands in Ammosates and their highly differentiated homologues in the myxinoids, he writes in the later editions, hence we see that in the cranium, as in the spinal column, there are at first developed at the sides of the chorda dorsalis two symmetrical elements, which subsequently coalesce, and may wholly enclose the chorda. Rathke has recently observed, in the embryos of serpents and other animals, before the formation of the proper cranial vertebrae, two symmetrical bands of cartilage, similar to those which I discovered as a persistent structure in Ammosates. At a later period, the basis cranii of vertebrate animals contains three parts analogous to the bodies of vertebrae, the most anterior of which, in the majority of animals, is generally small, and its development frequently abortive, whilst in man and mammiferous animals the three are very distinct. These parts are developed by the formation of three distinct points of ossification, one behind the other, in the basilar cartilage. 212 Rathke was very cautious about accepting the vertebral theory of the skull. He saw that the facts of development were not altogether favorable to the theory, and he gave his adherents with many reservations and saving clauses. His general attitude may be summed up as follows: 213 The chorda sheath is the common matrix of the vertebrae and of a large part of the skull. The basilar plate and the trabeculae, which are developed from the chorda sheath, give origin to three bones, which might possibly be considered equivalent to vertebral centra: the basicipedal, the basis sphenoid, and the reachbein, ethmoid. The rechbein develops from the fused ends of the trabeculae. The presphenoid might also be considered as a vertebral body, but it develops independently of the basilar plate and trabeculae. Now of these bones, the basicipedal is in every way equivalent to a vertebral centrum, for it develops in the basilar plate round the notochord. With the exoccipitals, which arise just like neural arches, it forms a true vertebra. The supraoccipital is an accessory bone developed in relation to bigger brains. The basis sphenoid appears in the basilar plate, but in front of the notochord, nor does it arise in exactly the same way as the centrum of a vertebra. The basis sphenoid with the elasphenoids, which develop independently in the side walls of the brain, may, however, still be considered as forming a vertebra, though the resemblance is not so great as in the case of the occipital ring. The presphenoid, being long and pointed, is very unlike a vertebral body. The orbitasphenoids develop separately from it. The ethmoid also differs from a vertebra, for it surrounds not the whole nervous axis as the two hinder vertebrae do, but only two prolongations of it, the olfactory lobes. In its development and final form it shows no particular resemblance to a vertebra. Its body, the pars perpendicularis, mesthmoid, shows no similarity with a vertebral centrum. Completing the three hinder cranial vertebrae and roofing in the brain are the supraoccipital, the parietals and the frontals. The premaxillaris, vomer and nasals do not belong to the cranial scheme, they are covering bones connected with the ethmoid. So, too, the ear capsule is not part of the cranial vertebrae, but is rather to be compared to the intercalary bones in the vertebral column of certain fish. Summing up as regards the cranial vertebrae, Rathke writes, we find that the four different groups of bones, consisting of the basicipedal with its intercalary, the supraoccipital, the basis sphenoid with its intercalaries, parietals, the presphenoid with its intercalaries, frontals, and the ethmoid with its outgrowths, turbinals and cribriform plate, taking them in order from behind forwards, show an increasing divergence from the plan according to which vertebrae as commonly understood develop, so that the basicipedal shows the greatest resemblance to a vertebra, the ethmoid the least, p. 30. In a posthumous volume published in 1861 the same opinion is put forward. In the head, too, he writes, some vertebrae can be recognized, although in a more or less modified form. Yet at most only 4 cranial vertebrae can be assumed, and these differ from ordinary well-developed vertebrae in their manner of formation the more the farther forward they lie. 214 Rathke was an able and careful critic of the vertebral theory of the skull, but he accepted it in the main. Actual attack on the theory upon embryological grounds was begun by C. Voigt, in his work on the development of coorganus 215 and in his paper on the development of Alades 216 he described for coorganus an origin of the skull in the main similar to that established by Rathke for the adder. There was a nuchal plate in which the front end of the notochord was embedded, the notochord ended at the level of the labyrinth, there were 2 lateral bands, comparable to Rathke's lateral trabeculae, a facial plate was also formed, which seems on the whole equivalent to the plate formed by the fused anterior ends of the trabeculae. A little later the cranium formed a complete cartilaginous box surrounding the brain, very similar to the adult cranium of a shark. In his criticism of the vertebral theory of the skull, Voigt started by defining the vertebra as a ring formed round the chorda. Now since only the occipital segment of the skull is formed actually round the notochord, the parts of the skull lying in front of this cannot themselves be vertebrae, though they may be considered as prolongations of the occipital or nuchal vertebra. We must regard the nuchal plate as a true vertebra, modified, it is true, in its formation and development by its particular functions. Now, since the notochord ends with the nuchal plate we can no longer regard as vertebrae the parts of the skull that lie beyond, such as the lateral processes of the cranium and the facial plate, for they have no relation with the notochord, p. 123. To support this view he adduced the fact that the vertebral divisions, primitive vertebrae, visible in the trunk do not extend into the head. He used precisely the same arguments in his paper on alities to destroy the vertebral theory of the skull. We quote the following passage translated by Huxley, 1864, p. 295, from this paper. It has therefore become my distinct persuasion that the occipital vertebra is indeed a true vertebra, but that everything which lies before it is not fashioned upon the vertebrate type at all, and that efforts to interpret it in such a way are vain, that, therefore, if we accept that vertebra, occipital, which ends the spinal column anteriorly, there are no cranial vertebrae at all. L. Agassiz, himself a pupil of Dollinger, in the general part, 1844, of his Recherches sur les poissons fossiles, Neuchâtel, 1833-43, repeats in the main his pupil Vogt's criticism of the vertebral theory, volume I, pages 125-9. These arguments of Voigt and Agassiz were not considered by Müller to dispose of the theory 217, which maintained a firm hold even upon embryologists. It was still upheld by Reichert, and Kalliker in 1849 showed himself convinced of its general validity. A useful step in the analysis of the concept vertebra was taken by Remak 218, who showed what a complex affair the formation of vertebrae really is, involving as it does a complete resegmentation, negligence, of the vertebral column, whereby the original vertebral bodies were replaced by the secondary definitive bodies, p. 143. Remak showed, as he thought, that the protovertebral segmentation of the dorsal muscle plates did not extend into the head, and he denied Reichert's assertion, 1837, that the cranial basis in mammals showed transverse grooves delimiting 3 cranial vertebrae, p. 36. The gill slits, he considered, could not possibly be regarded as marking the limits of head vertebrae. In 1858 appeared Huxley's well-known Croonian lecture, on the theory of the vertebrate skull 219, in which he stated with great clearness and force the case for the embryological method of determining homologies, and criticized with vigor the vertebral theory of the skull. By this time the two rival methods in morphology had become clearly differentiated, and Huxley was able to contrast them, or at least to show how necessary the new embryological method was as a corrective and a supplement to the older anatomical, or, as he calls it, gradation method. Applied to the theory of the skull, the gradation method consists in comparing the parts of the skull and vertebral column in adult animals with respect to their form and connections. Using the other method, the investigator traces back skull and vertebral column to their earliest embryonic states and determines the identity of parts by their developmental relations, p. 541. This second method is the final and ultimate. The study of the gradations of structure presented by a series of living beings may have the utmost value in suggesting homologies, but the study of development alone can finally demonstrate them, p. 541. As an example of the utility and, indeed, the necessity of applying the embryological method, Huxley takes the case of the quadrate bone in birds. This bone had been generally regarded by anatomists as the equivalent of the tympanic of mammals, on account of its connection with the tympanum, but Reichert showed, 1837, that the same segment of the first visceral arch developed into the incus in mammals, and into the quadrate in birds, and that therefore the quadrate was homologous with the incus. Similarly, on developmental grounds, the malleus or hammer of mammals is the homologue of the articular of birds, since both are developed from a portion of Meckel's cartilage identical in form and connections in the two groups. The homologies of the bones connected with the jaws in bony fishes had long been a subject of contention among comparative anatomists. Huxley shows from his personal observations how the development of the visceral arches throws light upon these difficulties. The mandibular arch in the developing fish is abruptly angled, as in the embryo of Tetrapoda. The upper prong of it ossifies into the palatine and pterygoid. At the angle is formed the quadrate, jugal, cuvier, and to the quadrate is articulated the lower jaw, which ossifies round the lower prong or Meckel's cartilage. The scheme of development of the jaws is accordingly similar in fish to what it is in other vertebrates, and this similarity of development enables Huxley to recognize what are the true homologues of the quadrate, the palatine, and the pterygoid in adult bony fish, and to prove that the symplectic and the metapterygoid, tympanal, cuvier, are bones peculiar to fish. In developing amphibia, Huxley found a suspensorium of hyoid and mandibular arches similar to the hyomandibular of fish. Tackling his main problem of the unity of plan of the vertebrate skull, Huxley shows, by a careful discussion of the anatomical relationships of the chief bones in typical examples of all vertebrate classes, that there is on the whole unity of plan as regards the osseous skull. This unity of composition can be established, on the gradation method, by considering the connections of the bones of the skull with one another, their relations to the parts of the brain and to the foramina of the principal cranial nerves. The assistance of the embryological method is, however, necessary in determining many points with regard to the bones developed in relation to the visceral arches. But there is a further step to be taken. Admitting that a general unity of plan pervades the organization of the ossified skull, the important fact remains that many vertebrate animals, all those fishes, in fact, which are known as elasmobranchii, marsupobranchii, pharyngobranchii, and dipnoi, have no bony skull at all, at least in the sense in which the words have hitherto been used, p. 571. The membranous or cartilaginous skull of these fishes shows a general resemblance in its main features to the ossified skull of other vertebrates. The relations of the ear to the vagus and trigeminal nerves are, for instance, the same in both. The main regions of the cartilaginous skull can be homologous with definite bones or groups of bones in the bony skull, but discrepancies occur. It is again to development that we must turn to discover the true relationship of the cartilaginous to the ossified skull. The study of the development of the ossified vertebrate skull satisfactorily proves that the adult crania of the lower vertebrata are but special developments 220 of conditions through which the embryonic crania of the highest members of the subkingdom pass, p. 573. It is with the embryonic cranium of higher vertebrates that the adult skull of the lower fishes must be compared, and the comparison will show a substantial though not a complete agreement between them. Thus, speaking of the development of the frog's skull, Huxley writes, if, bearing in mind the changes which are undergone by the palatosuspensorial apparatus, we now compare the stages of development of the frog's skull with the persistent conditions of the skull in the amphioxus, the lamprey, and the shark, we shall discover the model and type of the latter in the former. The skull of the amphioxus presents a modification of that plan which is exhibited by the frog's skull when its walls are still membranous and the notochord is not yet embedded in cartilage. The skull of the lamprey is readily reducible to the same plan of structure as that which is exhibited by the tadpole when its gills are still external and its blood colorless. And finally, the skull of the shark is at once intelligible when we have studied the cranium in further advanced larvae, or its cartilaginous basis in the adult frog, p. 577. Development, therefore, proves what comparative anatomy could only foreshadow: the unity of plan of all vertebrate skulls, ossified and unossified alike. We have thus attained to a theory or general expression of the laws of structure of the skull. All vertebrate skulls are originally alike, in all, save amphioxus. The base of the primitive cranium undergoes the mesocephalic flexure, behind which the notochord terminates, while immediately in front of it the pituitary body is developed. 221 in all. The cartilaginous cranium has primarily the same structure: a basal plate enveloping the end of the notochord and sending forth three processes, of which one is short and median, while the other two, the lateral trabeculae, pass on each side of the space on which the pituitary body rests, and unite in front of it. In all, the mandibular arch is primarily attached behind the level of the pituitary space, and the auditory capsules are enveloped by a cartilaginous mass, continuous with the basal plate between them. The amount of further development to which the primary skull may attain varies, and no distinct ossifications at all may take place in it, but when such ossification does occur, the same bones are developed in similar relations to the primitive cartilaginous skull, p. 578. In a word, there is a general plan or primordial type which is manifested in the higher forms most clearly in their earliest development, an embryological archetype therefore. Huxley now goes on to consider the relation of this general plan or type of the skull to the structure and development of the vertebral column. Does the skull in its development show any signs of a composition out of several vertebrae? The vertebral column develops as a segmented structure round the notochord. The skull develops first as an unsegmented plate extending far beyond the notochord. The processes of this basilar plate, the trabeculae, are quite unlike anything in the vertebral column. It is true that when the process of ossification begins, separate bones are differentiated in the basilar plate one in front of the other, giving an appearance of segmentation. The hindmost of these bones, the basicipedal, ossifies round the notochord, quite like a vertebral centrum, and its side parts which form the occipital arch develop in a remotely similar way to the neural arches of the vertebrae. The next bone, however, the basis sphenoid, develops in front of the notochord, and shows very little analogy with the vertebral body. The analogy is even more far-fetched when applied to the axial bones in front of the basis sphenoid. The cranium might indeed be divided upon ossification into a series of segments bearing a more or less remote analogy with vertebrae. In the process of ossification there is a certain analogy between the spinal column and the cranium, but that analogy becomes weaker and weaker as we proceed towards the anterior end of the skull, p. 585. The best way to state the facts is to say that both skull and vertebral column start in their development from the same point, but immediately begin to diverge. The clear indications of segmentation which fully ossified adult skulls undoubtedly show are, therefore, secondary, and the vertebral theory of the skull, which was originally based upon the appearance of such fully ossified crania, is on the whole negatived by embryology. We have now to turn back a few years in order to follow up another line of discovery which had an important bearing upon the theory of the vertebrate skull: the working out of the distinction between membrane and cartilage bones. As early as 1731, R. Nesbitt 222 in 2 lectures delivered to the Royal College of Surgeons, demonstrated that in the human foetus some bones were formed not in cartilage but directly in fibrous tissue, and this observation was confirmed by other human anatomists, particularly by Sharpe at a considerably later date. In 1822 Arendt 223 focused attention upon the remarkable structure of the skull of the pike, with its cartilaginous brain box studded all over with bony plaques, an arrangement which had already attracted the interest of Cuvier and Meckel. K. E. von Baer 224 in 1826 discussed at some length the relation between the bony and the cartilaginous skull in fishes, with particular reference to the sturgeon, coming to the following just conclusion: if we consider the fibrous skeleton of Ammosates as the first foundation of the skeleton of vertebrates, we can form a series among the cartilaginous fishes, according as a cartilaginous skeleton penetrates more and more into this fibrous foundation. In the same way the process of ossification supplants the cartilaginous skeleton. So long as the ossifications lie in the skin, as in the sturgeon, they form corneous bones, hornoken, but when they lie under the skin, they form true bones, example the bones of the skull in the pike, p. 374. Embryologists soon become aware that a similar distinction between a primitive cartilaginous foundation and a secondary overlying ossification of the skull showed itself in the development of all vertebrates. Duggs, in his Recherches sur l'ostéologie et la myologie de Butraciens, 1834, distinguished between such bones as are formed by direct ossification of the cartilaginous groundwork of the skull, and such as are developed in the periosteal fibrous tissue. Reichert in 1838-225 noted that several of the skull bones in amphibia are formed without the intermediary of cartilage, such as the nasals, the maxillaries, and the lacrimals. So, too, the frontals and parietals of teleosts developed independently of the cartilaginous skull, and belong to the skeletal system of the skin, not to the true vertebral axial skeleton, pages 215-6. Even more interesting was his discovery, afterwards confirmed by Hertwig 226, that in the newt several bones connected with the palate were formed in the mucous membrane of the mouth by the fusion of a number of little conical teeth, p. 97. Certain of these bones he considered to be the substitutes, not the equivalents, of the palatine and pterygoid of other vertebrates, which are formed from the upper part of the first visceral arch, a part missing in the newt, p. 100. Owing to the difference of development he would not homologize these bones in the newt with the palatine and pterygoid of other vertebrates. He recognized also that the bone now known as the parasphenoid was developed in the frog in the mucous membrane of the mouth, and had originally no connection with the cranial basis, p. 34. Rathke in 1839 also allowed the distinction between cartilage and membrane bone, but laid no stress upon it, and D. Natter, p. 197. Jacobson in 1842-227 introduced the useful term, primordial cranium, for the primitive cartilaginous foundation of the skull, and drew a sharp distinction between cartilage bones and membrane bones. In his Recherches sur les poissons fossiles 228, L. Agassiz used Vogt's work on the development of coorganus to establish a classification of the bones of the skull in fish, a classification which had the merit of drawing a sharp distinction between the cartilaginous groundwork and the protective plates of the fish's skull. He recognized that the protective plates developed in a different way from the other bones of the skull. We must distinguish, he writes, two kinds of ossification, one which tends to transform the primitive parts of the embryonic cranium directly into bone, and another which leads to the deposition of protective plates round this core, which develop not only upon the upper surface, as has hitherto been supposed, but also on the lateral walls and on the lower surface of the cranium, p. 112. In the skull of all fish there are three elements: 1. The cartilaginous base, including the nuchal plate, the trabeculae, and the facial plate, together with the auditory capsules; 2. The cartilaginous cerebral envelope; 3. The bony protective plates, absent in elasmobranchs. The bones developed in relation to these cranial elements can be classified as follows: 1. The basioccipitals, exoccipitals, paraccipitals, supraoccipital, and petrose, Rocher, developed from the nuchal plate; the ali and orbitosphenoids developed from the trabeculae; the cranial ethmoid 229 developed from the facial plate; 2. The parietals, frontals and nasals formed from the superior protective plate; the anterior and posterior frontals and the temporal, from the lateral plates; the body of the sphenoid and the vomer from the inferior plates. The other element, the cartilaginous brain box, does not ossify, and tends to become absorbed, p. 124. In 1849 Kaliker published a paper 230 dealing with the morphological significance of the distinction between membrane and cartilage bones, and in 1850 231 he defended his views against the criticisms of Riker 232 in a further note entitled Die Theorie de primordial Schattels festgehalten. It is convenient to consider these papers together. Kaliker held that there was, 1. A histological and, 2. A morphological difference between the two categories of bones. The histological development of the two kinds was different, but this difference was not sufficient to establish a morphological distinction between them, a distinction in their anatomical Bedeutung. The true morphological distinction between them was their development in different skeleton-forming layers. Membrane bones were developed in fibrous tissue lying between the skin and the deep layer which formed the primordial cranium, and it was this formation in a separate layer that gave them a different morphological significance from the bones formed directly in the deep layer. Kaliker's distinction, therefore, was between the bones formed in the primordial cartilaginous cranium on the one hand, and the superficial ossifications in fibrous tissue on the other hand. The cartilaginous cranium in Kaliker's opinion was formed upon the vertebral type, and the membrane bones were accessory. This, at least, was his opinion in 1849. In 1850, after Stanius had shown that membrane bones occurred as integral parts of the vertebrae in certain fish, he modified his view of the membrane bones, and admitted them, at least in some cases, as constituents of the cranial vertebrae. On this morphological distinction of membrane and cartilage bones future comparative osteology was to be based. My sole aim is to state again the principle upon which comparative osteology is to be based and extended, and this is that first place should be assigned to anatomical considerations, and among these to the manner of origin of the whole bone in relation to the skeleton-forming layers, 1850, p. 290. The homologies established by this new principle might run counter to the homologies indicated by the study of adult structure. Thus, for instance, although the lower jaw in position, function, form, and shape, appears to be the same bone throughout, yet it must be admitted that it shows a difference in the different classes. In mammals and man it is an entirely secondary bone, an extremity according to Reichert, in birds, amphibia, and fishes only partially so, for its articular belongs to Meckel's cartilage and is accordingly analogous to a rib. Indeed, in the plagiostomes, etc., the whole lower jaw along with the articular is a persistent Meckel's cartilage, p. 290, 1850. So, too, the supraoccipital in man cannot be fully homologous with the supraoccipital of many mammals, for its upper half arises at first in isolation as a secondary bone, p. 290. Reichert objected to the distinction drawn by Kaliker, and denied that there was either a histological or a morphological difference between membrane and cartilage bones. It was shown a few years later by H. Muller 233 that there was in truth no essential difference in histological development between the two categories of bone, that the cartilage cells were replaced by bone cells identical with those taking part in the formation of membrane bones. The morphological distinction continued however to be recognized, particularly by the embryologists. Rathke in his volume of 1861 234 classified the bones of the skull according to their origin from the primordial cranium or from the overlying fibrous layer, distinguishing as membrane bones, the parietals, frontals, nasals, lacrymals, maxillaries and premaxillaris, jugulars, tympanic, parts of the temporal, vomer, part of the supraoccipitals in some mammals, and the mandible, with the exception of the articular in such as have a quadrate bone. Huxley was also inclined in 1864 235 to recognize the distinction, but he writes with some reserve: is there a clear line of demarcation between membrane bones and cartilage bones? Are certain bones always developed primarily from cartilage, while certain others as constantly originate in membrane? And further, if a membrane bone is found in the position ordinarily occupied by a cartilage bone, is it to be regarded merely as the analog and not as the homologue of the latter? p. 296. We may note here that many comparative anatomists of the period were quite ready to decide Huxley's last question in a sense favorable to the older, purely anatomical, view of homology. Owen, for instance, held that difference of development did not disturb homologies established by form and connections. Parts are homologous, he writes, in the sense in which the term is used in this work, which are not always similarly developed, thus the pars occipitalis strict dicta, etc., of Soemmerring is the special homologue of the supraoccipital bone of the cod, although it is developed out of pre-existing cartilage in the fish and out of aponeurotic membrane in the human subject. 236. Similarly, he pointed to the diversities of development of the vertebral centrum in the different vertebrate classes as proof that development could not always be relied upon in deciding homologies, p. 89. But he could not deny that the archetype was better shown in the embryo than in the adult, supra, p. 108. J. V. Karras 237 likewise stood firm for the older method of determining homologies by comparison of adult structure. We can regard as homologous, he writes, only those parts which in the fully formed animal possess a like position and show the same topographical relations to the neighboring parts, p. 389. Parts homologous in this sense might develop in different ways, but no great importance was to be attached to such a circumstance. Membrane and cartilage bones developed in practically the same way, from the same skeleton-forming layer, and no morphological significance attached to their distinction, pages 227, 457. Embryology was of considerable value in helping to determine homologies, but the evidence that it supplied was contributory, not conclusive. Perhaps the greatest service which the study of development rendered was to disentangle, by a comparison of the earliest embryos, the generalist type, p. 389. We have now traced, by our historical study of the theory of the skull, the gradual evolution of the tendency to find in development the surest guide to determining homologies. We have seen how the embryological type came to be substituted, in whole or in part, for the anatomical type derived from the study of adult structure. But we have had to do only with a modification, not with a transformation, of the criterion of homology recognized by the anatomists. Homology is still determined by position, by connections, in the embryo as in the adult. Similarity of development has become the criterion of homology in the eyes of the embryologist, but similarity of development means, not identity of histological differentiation, but similarity of connections throughout the course of development. For the purposes of morphology, development has to be considered as an orderly sequence of successive forms, not in its real nature as a process essentially continuous. Morphology has to replace the living continuity by a kinematographic succession of stages. Since it is the earliest of these stages that manifest the simplest and most generalist structural relations of the parts, it is in the earlier stages that homologies can be most easily determined. But these homologies are still determined solely by the relative positions and connections of the parts, just as homologies are determined in the last of all the stages of development, the adult state. And since the generalist type is shown most clearly in the earliest stages and tends to become obscured by later differentiation, homologies observed in embryonic life are to be upheld even if the relations in adult life seem to indicate different interpretations. 183. See review by Cuvier, M.E.M. MUS Hist. Nat. 3, pages 82 to 97, 1817. 184 mem. Savins et Rangers, 6. Extract in Ensignat. 2. I. Zoel, pages 366 to 72, 1834. 185 Recherches sur la génération de mammifères, 1834. Embryogenie comparée, 1837. 186 Kieman Basog Vieren, Isis, pages 747 to 9, 1825. 187 Kieman Bay Vogeln, Isis, pages 1100 to 1, 1825. 188 Uber die Kieman Bogen und Kiemensfass beim Bebruten Hünchen, Isis, XX, pages 401 to 3, 1827. Read in September 1826 to the Versammlung der Deutschen Naturforscher und Erd, then recently founded by Oken. 189 Isis, pages 160 to 4, PL2, 1828. 190 Über die Kiemen und Kiemensfass in den Embryonen der Wirbeltiere, Meckel's Archive for 1827, pages 556 to 68. Also in Ensignat, 15, pages 266 to 80, 280 to 4, 1828. 191 Meckel's Archive, 6, pages 1 to 47, 1832. 192 Untersuchungen über die Bildung und Entwicklung der Flusskrebses, Leipzig, Folio, 1829. Preliminary Notice in Isis, pages 1093 to 1100, 1825. 193 Untersuchungen über die Bildung und Entwicklung der Wasserzelle, ABH. Z Bild. Entwicklungs, I, pages 1 to 20, 1832. Translated in Ensignat. 2, Zoel, pages 139 to 57, 1834. 194 Kalliker, Entwicklungsgeschichte, 2nd ed., p. 17, Leipzig, 1879. 195 Handbuch der Entwicklungsgeschichte des Menschen und der Sagetier und Vogel, Berlin, 1835. 196 Embryogenie comparée, 1837, Histoire générale du développement des corps organisés, 1847 to 49. 197 Entwicklungsgeschichte des Koninklijks, Braunschweig, 1842, Entwicklungsgeschichte des Hunde-Eis, Braunschweig, 1845, Entwicklungsgeschichte des Meerschweinchens, Gießen, 1852, Entwicklungsgeschichte des Res, Gießen, 1854. 198 It is the role of embryology, as my great teacher says, to form the court of appeal for comparative anatomy, and it is from embryology particularly, which has in the last decades provided such signal instances of the unraveling of obscure problems, that we have to expect a definite clearing up of the problems relating to the development of the head. Muller's Archive, p. 121, 1837. 199 Anat Phil. Unters. Udiki Menapparat ud Zungenbien, Riga, and Dorpat, 1832. 200 Bildungs und Entwicklungsgeschichte Blenius Viviparus, Abhandel. Z Bild. Entwicklungs. De Menschen der Theorie, 2, pages 1 to 68, Leipzig, 1833. 201 von den Urteilen und Challengerusts, Leipzig, 1828. 202 Chemenapparat, pages 107 to 118. 203 Vergleich and Anatomie der Myxinoiden. Part I, Osteology and Myology. ABH Konigal. Akkad. Wyss. Berlin, for 1834, pages 65 to 340, 9 PLS, 1836. Also separately. 204 Über die Visceralbogen der Werbelthier in Allgemeinen und deren Metamorphosen bei den Vogeln und Säugetier, Muller's Archive, pages 120 to 222, 1837. 205 Handbuch des Menschen. Anatomie, 4, p. 47. 206 This was shown by Saras, and Sinat, 11, p. 54 fn, 1827, who found in a human embryo a long cartilaginous piece extending from the urosicles to the inside of the lower jaw, and suggested that it was the foundation of the permanent mandible. 207 Abhandel, I, p. 102, 1832, 2, p. 25, 1833. Blenius paper. 208 Vergleich und Entwicklungsgeschichte des Kopfs der nackten Amphibien, Königsberg, Quarto, 276 pages, 1838. 209 Muller's Archive for 1838. 210 Entwicklungsgeschichte der Natur, Königsberg, 1839. 211 Bemerkungen über die Entwicklung des Schädels der Werbelthier, Königsberg, 1839. 212 Handbuch der Physiologie des Menschen, Koblenz, 1835, ENG trans. By W. Balla, 2, p. 1615, 1838. 213 For a full statement of Rathke's conclusions, see the translation given by Huxley in Lectures on the Elements of Comparative Anatomy, London, 1864. 214 Entwicklungsgeschichte der Werbelthier, p.142, 1861. 215 Embryologie des Sammons. A separate volume of L. Agassiz Histoire naturelle des poissons d'eau douce de l'Europe centrale, Neuchâtel, 1842. 216 Untersuchungen über die Entwicklungsgeschichte der Geburtsschilfroute, Solothurn, 1842. 217 Muller's Archive for 1843, Peixley 8th. 218 Untersuchungen über die Entwicklung der Werbelthier, Berlin, 1850-55. 219 Delivered June 17, 1858. Reprinted in the Scientific Memoirs of T. H. Huxley, edited by M. Foster and E. Ray Lancaster, Volume I, pages 538 to 606, 1898. 220 C. F. Reichert, Supra, p. 149. 221 The origin of the pituitary body from the roof of the mouth was first described by Rathke, 1839. 222 Human osteogeny explained in 2 lectures, London, 1736. 223 Decapitis ossei esosis locii structura singulari. Dissart. Inog. Reggio Monte, 1822. 224 Über das Äußere und die innere Skelett, Meckel's Archive, pages 327 to 76, 1826. 225 Virgil. Entwicklung. Die Kopf die Nackten Amphibien, p. 186. 226 Arch F. Micro. Anat, 11, Supple, 1874. 227 Om Primordial Craniate, for Handlingarskund. Native. Mole, Stockholm, 1842. 228 Volume I, General Part, Pub. 1844 229 Anthosphenoid, Owen. 230 Zweiterbericht Zoatum. Anstalt zu Würzburg, 1849. 231 Zeitz. F. Wiss. Zoel, 2, pages 281 to 91. 232 Muller's Archive for 1849, pages 443 to 515. 233 Zeitz. F. Wiss Zoel, 9, 1858. 234 Entw. Die Werbelthier, pages 139 to 40, 1861. 235 Lectures on the Elements of Comparative Anatomy. 236 on the Archetype of the Vertebrate Skeleton, p. 1848. 237 System der Theoretischen Morphologie, Leipzig, 1853. Chapter 11 The Cell Theory. With the founding of the cell theory by Schwann in 1839, an important step was taken in the analysis of the degrees of composition of the animal body. Aristotle had distinguished three: the unorganized material, itself compounded of the four primitive elements, earth and water, air and fire, the homogeneous parts or tissues and the heterogeneous parts or organs, and this conception was retained with little change even to the days of Cuvier and von Baer. Those of the old anatomists who speculated on the relations of organic elements to one another were dominated by Aristotle's simple and profound classification, and proposed schemes which differed from his only in detail. Bichat enlarged and deepened the concept of tissue, but the degree of composition below this was for him, as for all anatomists of his time, a fibrous or pulpy cellulosity, living, indeed, but showing no uniform and elemental structure. It was Schwann's merit to interpose between the tissue and the mere unorganized material a new element of structure, the cell. And, as it happened, a few years before Schwann published his cell theory, Dujardin hinted at another degree of composition which was later to take its place between the cell and the chemical elements sarcode or protoplasm. As is well known, the concept of the cell arose first in botany. Robert Hooke discovered cells in cork and pith in 1667, and his discovery was followed up by Grue and Malpighi in 1671, and by Liu and Hooke in 1695. But they did not conceive the cell as a living, independent, structural unit. They were interested in the physiology of the plant as a whole, how it lived and nourished itself, and they studied cells and sieve tubes, wood fibers, and tracheae with a view rather to finding out their functions and their significance for the life of the plant than to discovering the minutiae of their structure. The same attitude was taken up by the few botanists who in the 18th century paid any heed to the microscopical anatomy of plants. For C.F. Wolf 238, the formation of cells was a result of the secretion of drops of sap in the fundamental substance of the plant, this substance remaining as cell walls when cell formation was completed. No idea here of cells as units of structure. In the early 19th century, interest in plant anatomy revived somewhat, and much work was done by Treviranus, Merbel, Moldenhauer, Mayen, and von Moll 239. As a result of their work, the fact was established that the tissues of plants are composed of elements which can, with few exceptions, be reduced to one simple fundamental form, the spherical closed cell. Thus the vessels of plants are formed by coalescence of cells, fibers by the elongation of cells and the thickening and toughening of their walls. At this time, interest was concentrated on the cell wall, to the almost total neglect of the cell contents. The matured framework of plant cells, to use Sachs' convenient phrase, was the chief, almost the sole, object of study. And it was natural enough that the mere architecture of the plant should monopolize interest, that the composition of the tissues out of the cells, and the fitting together of the tissues to form the plant should awaken and hold the curiosity of the investigator. Even the modifications of the cell walls themselves, their rings and spiral thickenings and pits, offered a fascinating field of inquiry. The idea that the cell contents might show a characteristic and individual structure had hardly dawned upon botanists when Schleiden published his famous paper, Beitrag zur Phytogenesis 240. Schleiden's theme in this paper is the origin and development of the plant cell, a subject then very obscure, in spite of pioneer work by Merbel. A few years before, Robert Brown had called attention to the presence in the epidermal cells of orchids and other plants of a characteristic spot which he called the areola or nucleus. 241. Schleiden saw the importance of this discovery, confirmed the constant presence of the nucleus in young cells, and held it to be an elementary organ of the cell. He named it the cytoblast because, in his opinion, it formed the cell. It was embedded in a peculiar gummy substance, the cytoplasm, which formed a lining to the cellulose cell wall. Within the nucleus there was often a small dark spot or sphere, the nucleolus. The nucleus, Schleiden thought, originated as a minute granule in the cytoplasm which gradually increased in size, becoming first a nucleolus, kernchen, and then, by further condensation of matter round it, a nucleus. Several nuclei might be formed in this way in a single cell. New cells took their origin directly from a full-grown nucleus, in a peculiar way which Schleiden describes as follows: as soon as the cytoblasts have reached their full size, a delicate transparent vesicle arises on their surface. This is the young cell, which at first takes the shape of a very flat segment of a sphere, of which the plane surface is formed by the cytoblast, the convex side by the young cell itself, which lies upon the cytoblast like a watch glass on a watch. P 145. The young cells increase in size and fill up the cavity of the old cell, which is in time resorbed. Cell development always takes place within existing cells, and either one or many new cells may be formed within the mother cell. Schleiden's views on cell formation were drawn from some rather imperfect observations on the embryo sac and pollen tube, but he extended his theory to cell formation in general. Though wrong in almost all respects, the theory had at least the merit of fixing attention upon the really important constituents of the cell, the nucleus, and the cell plasma. To Schleiden, too, we owe the conception of the cell as a more or less independent living unity, whose life is not entirely identified with the life of the plant as a whole. Each cell, he writes, carries on a double life, one a quite independent and self-contained life, the other a dependent life in so far as the cell has become an integral part of the plant. P 138. So long as the definition of the plant cell embraced little more than the hardened cell wall, it was little wonder that cells in this sense were not recognized in animal tissues, except in a few exceptional cases as in the notochord by Johannes Müller. 242. Careful observation of animal tissues discovered in some cases the existence of discontinuous units of structure, but these were not, as a rule, recognized before 1838 as analogous to plant cells. Von Baer, for example, observed that the young chick embryo was composed partly of an albuminous mass and partly of Kugelshin or little globules suspended in it, Entwicklungsgeschichte, I, pages 19, 144. Since such Kugelshin disposed in a row formed the notochord, I, p. 145, it seems probable that his Kugelshin were really cells. Similarly, A. de Quatrefages 243 in 1834 saw and figured segmentation spheres in the developing egg of Limnaea, but he called them globules and did not recognize their analogy with the cells of plants. According to M. Kendrick 244 Fontana, so far back as 1781 245 described cells with nuclei in various tissues, and used acids and alkalis to bring out their structure more clearly. But it was not till July 8, 1836 that a fairly widespread occurrence of cells in animal tissues was recognized. The pioneer in this seems to have been Pourquenier, who described cells in the choroidal plexus in 1836-246 and compared gland cells with the cells of plants in 1837-247. Henel in 1837-248 and 1838-249 described various kinds of epithelial tissue, distinguishing them according to the kind of cell composing them. He also discovered the mode of growth of stratified epithelium. Valentin 250 appears to have seen cells in cartilage and epithelium even before Henel, and to have observed cells in the blastoderm of the chick. In his report on the progress of anatomy during 1838, Johannes Müller was able to refer to quite a number of papers dealing with the occurrence of cells in animal tissues. In addition to those already noted, he mentions work by Breschet and Gluge on the cells of the umbilical cord, by Dumaertier on the cells in the liver of mollusks, by Rimac and by Pourquenier on nerve cells, by Dunn on the cells of the conjunctiva, cornea, and lens. He reports, too, that Turpin had compared the epithelial cells of the vagina with the cell tissue of plants. Müller himself had not only recognized the cellular nature of the notochord, but had observed the cells of the vitreous humor, fat cells, and pigment cells, and even the nuclei of cartilage cells. From Schwann, 1839, we learn that C.H. Schultz had followed back the corpuscles of the blood to their original state of nucleated cells, and that Wernicke had recognized cells in the embryonic lens. A preliminary notice of Schwann's own work appeared in 1838, Furiups Notizen, No. 91, 1838, the full memoir in 1839, under the title Mikroskopische Untersuchungen über die Übereinstimmung in der Struktur und dem Wachstum der Tiere und Pflanzen 251. Theodor Schwann was a pupil of Johannes Müller, and we know that Müller took much interest in the new histology. It is probably to his influence that we owe Schwann's brilliant work on the cell, which appeared just after Schwann left Berlin for Lowen. Schwann was himself, as his later work showed, more a physiologist than a morphologist. He did quite fundamental work on enzymes, discovering and isolating the pepsin of the gastric juice. He proved that yeast was not an inorganic precipitate but a mass of living cells. He carried out experiments directed to show that spontaneous generation does not occur. We shall see in his treatment of the cell theory clear indications of his physiological turn of mind. Schwann was only 29 when his masterwork appeared, and the book is clearly the work of a young man. It has the clear structure, the logical finish, which the energy of youth imparts to its chosen work. So the work of Rathsprime, the Anatomische Philosophische Untersuchungen of 1832 shows more vigor and a more reasoned structure than his later papers. Schwann's book is indeed a model of construction and cumulative argument, and even for this reason alone justly deserves to rank as a classic. The first section of his book is devoted to a detailed study of the structure and development of cartilage cells and of the cells of the notochord, and to a comparison of these with plant cells. He accepts Schleiden's account of the origin and development of nuclei and cells as a standard of comparison, and he seeks to show that nucleus and nucleolus, cell wall and cell contents, show the same relations and behave in the same manner in these two types of animal cells as in the plant cells studied by Schleiden. The types of cell which he chose for this comparison are the most plant-like of all animal cells, and he was even able to point to a thickening of the cell wall in certain cartilage cells, analogous to the thickening which plays so important a part in the outward modification of plant cells. The analogy indeed in structure and development between chorda and cartilage cells and the cells of plants seemed to him complete. The substance of the notochord consisted of polyhedral cells having attached to their wall an oval disc similar in all respects to the nucleus of the plant cell, and like it containing one or more nucleoli. Inside the mother cell were to be found young developing cells of spherical shape, lacking however a nucleus. Cartilage was even more like plant tissue. It was composed of cells, each with its cell membrane. The cells lay close to one another, separated only by their thickened cell wall and the intercellular matrix, showing thus even the general appearance of the cellular tissue of plants. They contained a nucleus with one or two nucleoli, and the nucleus was often resorbed, as in plants, when the cell reached its full development. Other nuclei were in many cases present in the cell, round which young cells could be seen to develop, in exactly the same manner as in plants. These nuclei had accordingly the same significance as the nuclei of plants, and deserved the same name of cytoblasts or cell generators. The true nucleus of the cartilage cell was probably in the same way the original generator of the mother cell. Having proved the identity in structure and function of the cells of these selected tissues with the cells of plants, as conceived by Schleiden, Schwann had still to show that the generality of animal tissues consisted either in their adult or in their embryonic state of similar cells. This demonstration occupies the second and longest section of his book. His method is throughout genetic. He seeks to show, not so much that all animal tissues are actually in their finished state composed of cells and modifications of cells, as that all tissues, even the most complex, are developed from cells analogous in structure and growth with the cells of plants. All animals develop from an ovum. It was his first task to discover whether the ovum was or was not a cell. It happened that, some years before Schwann wrote, a good deal of work had been done on the minute structure of the ovum, particularly by Pourquenier and von Baer. Pourquenier in 1825-252 discovered and described in the unfertilized egg of the fowl a small vesicle containing granular matter, which he named the cameblaskin or germinal vesicle. It disappeared in the fertilized egg. As early as 1791 Polly had seen the germinal vesicle in the eggs of mollusks, but the first adequate account was given by Pourquenier. In 1827-253 von Baer discovered the true ova of mammals and cleared up a point which had been a stumbling block ever since the days of von Graff, who had described as the ova the follicles now bearing his name 254. Even von Graff had noticed that the early uterine eggs were smaller than the supposed ovarian eggs. Prévost and Dumas 255 had observed the presence in the Graffian follicle of a minute spherical body, which, however, they hesitated to call the ovum. It was left to von Baer to elucidate the structure of the follicle and to prove that this small sphere was indeed the mammalian ovum. His discovery was confirmed by Sharpe and by Alan Thomson. Von Baer found the germinal vesicle in the eggs of frogs, snakes, mollusks, and worms, but not in the mammalian ovum. He considered the whole mammalian ovum to be the equivalent of the germinal vesicle of birds, a comparison rightly questioned by Pourquenier, 1834. In 1834 Cost 256 discovered in the ovum of the rabbit a vesicle which he considered to be the germinal vesicle of Pourquenier. He observed that it disappeared after fertilization. Independently of Cost, and very little time after him, Wharton-Jones 257 found the germinal vesicle in the mammalian ovum. Valentin in 1835 258, Wagner in 1836 259 and Krauss in 1837 260 added considerably to the existing knowledge of the structure of the ovum. Wagner in his prodromus called attention to the widespread occurrence, within the germinal vesicle, of a darker speck which he called the chiumfleck or germinal spot, known sometimes as Wagner's spot. He recognized the chiumfleck in the ova of many classes of animals from mammals to polyps. Frequently more than one chiumfleck occurred. Schwann had therefore a good deal of exact knowledge to go upon in discussing the significance of the ovum for the cell theory. There were two possible interpretations. Either the ovum was a cell and the germinal vesicle its nucleus, or else the germinal vesicle was itself a cell within the larger cell of the ovum and the germinal spot was its nucleus. Schwann had some difficulty in deciding which of these views to adopt, but he finally inclined to the view that the ovum is a cell and the germinal vesicle its nucleus, basing his opinion largely upon observations by Wagner which tended to prove that the germinal vesicle was formed first and the ovum subsequently formed round it. But the ovum was not, in Schwann's view, a simple cell, for within it were contained yolk granules, one set apparently containing a nucleus, the others not. Even the second set, those composing the yellow yolk, were considered by Schwann to deserve the name of cells, because, although a nucleus could not be observed in them, they had a definite membrane, distinct from their contents, a conception of the cell obviously dating from the earliest botanical notions of cells as little sacs. The yolk cells were not mere dead food material but living units which took part in the subsequent development of the egg. The relation between the unfertilized egg and the blastoderm which arises from it is not made altogether clear by Schwann. According to his account, the cells of the blastoderm are formed actually in the ovum. Round the nucleus of the egg appears a niederschlag or precipitate which is the rudiment of the blastoderm, p. 68. When the egg leaves the ovary, the nucleus disappears, leaving behind it this rudiment of the blastoderm, which rapidly grows and increases in size. The blastoderm of the chick before incubation is found to be composed of spherical anucleate bodies which Schwann considers to be cells, because they almost certainly develop into the cells of the incubated blastoderm, which are clearly recognizable as such after 8 hours incubation. The serous and mucus layers can be distinguished after 16 hours incubation, and it is found that the cells of the serous layer contain definite nuclei, though such seem to be absent in the cells of the mucus layer. Between the two layers other cells are formed belonging to the vessel layer, which is, however, in Schwann's opinion not a very definitely individualized layer. Schwann's next step is a detailed demonstration of the origin of each tissue from simple cells such as those composing the incubated blastoderm. The foregoing investigation has taught us that the whole ovum shows nothing but a continual formation and differentiation of cells, from the moment of its appearance up to the time when, through the development of the serous and mucus layers of the blastoderm, the foundation is given for all the tissues subsequently appearing. We have found this common parent of all tissues itself to consist of cells. Our next task must be to demonstrate not only in this general way that tissues originate from cells, but also that the special formative mass of each tissue is composed of cells, and that all tissues are either constituted by simple cells or by one or other of the manifold kinds of modified cells, p. 71. 5 classes of tissue can be distinguished, according to the extent and manner of the modifications which the cells composing them have undergone. There are first of all independent and isolated cells, such as the corpuscles of the blood and lymph, not forming a coherent tissue in the ordinary sense. Next there are the assemblages of cells lying in contiguity with one another, but not in any way fused. Examples of this class are the epidermal tissues and the lens of the eye. In the third class come tissues the cells of which have fused by their walls, but whose cell cavities are not in continuity, such as osseous tissue and cartilage. In the tissues of the fourth class, comprising the most highly specialized of all, not only are the cell walls continuous but also the cell cavities. To this class belong muscle, nerve, and capillary vessels. A fifth class, of rather a special nature, includes the fibrous tissues of all kinds. This is the first classification of tissues upon a cellular basis, and it marks the foundation of a new histology which took the place of the general anatomy of Bichat. The exhaustive account which Schwann gives of the structure and development of the tissues in this section of his book constitutes the first systematic treatise on histology in the modern sense, and it is still worth reading, in spite of many errors in detail. Schwann found it easy to demonstrate the cellular nature of the tissues of his first three classes. With the other two classes he had more difficulty. Fibers of all kinds, he considered, arose by an elongation of cells, which afterwards split longitudinally into long strips, forming as the case might be white or elastic fibrous tissue. Muscle fibers and nerve fibers were formed in a totally different way, by coalescence of cells. Each separate muscle fiber and nerve fiber was thus a compound cell. Capillaries, Schwann held, were formed by cells hollowed out like drain pipes, and set end to end, a mistaken view soon corrected by Voigt, Embryologie des Samens, p. 206, 1842. In this detail part of his book Schwann accumulates material for a general theory of the cell which he develops in the third and last section. Taking up the physiological or dynamical standpoint, he points out that one process is common to all growth and development of tissues both in animals and plants, namely, the formation of cells, a process which he conceives to take place in the following manner. There is, first of all, a structureless substance, the cytoplasm, the matrix in which all cells originate. The cytoplasm may be either inside the cells, or, more usually, in the spaces between them. It is not a substance of definite chemical and physical properties, for the matrix of cartilage and the plasma of the blood alike come within the definition. It has largely the significance of food material for the developing cells. In plants, according to Schleiden, cells are never formed in the intercellular substance. The cytoplasm is within the cells, but extracellular cell formation seems to be the general rule in animals. An intracellular formation of cells occurs only in the ovum, in cartilage cells and chorda cells and in a few others, and even there it is not the exclusive method of formation. A formation of cells within cells never occurs in muscles and nerves, nor in fibrous tissue, p. 204. In the cytoplasm granules appear, which gradually increase in size and take on the characteristic shape of nuclei. Round each of these a young cell is formed. Sometimes the young cells appear to have no nuclei, as in the intracellular brood of chorda cells, but, as a rule, a nucleus is clearly visible. The nucleus is indeed the most characteristic constituent of the cell. The most important and most constant criterion of the existence of a cell is the presence or absence of the nucleus, writes Schwann near the beginning of his book, p. 43. As a general rule the nucleolus is formed first, and round it by a sort of condensation or concretion the nucleus, which is frequently hollow, and round this again, by a somewhat similar process, the cell. The whole process of the formation of a cell consists in the precipitation round a small previously formed corpuscle, the nucleolus, of first one layer, the nucleus, and then later round this a second layer, the cell substance, p. 213. The outermost layer of the cell usually thickens to form the membrane, but this membrane formation does not always occur, and the membrane is not present in all cells. The nucleus is formed in exactly the same manner as the cell, and it might with much truth itself be called a cell of the first order, while ordinary nucleated cells might be designated cells of the second order, P212. In anucleate cells there is probably only a single process of layer formation round an infinitely small nucleolus. In almost all nucleate cells the nucleus is resorbed when the cell reaches its full development, and it is larger and more important the younger the cell is. The cell was for Schwann not a morphological concept at all, but a physiological. The cell was a dynamical, not a statical unit. Cell formation was the process at the back of all production of life, and cells were the centers of all vital activity. Each cell was itself an organism, and its life and activities were to some extent independent of the lives and activities of all the other cells. The multicellular organism was a colony of unicellular organisms, and its life was a sum of the lives of its constituent elements. This theory of the organism, which holds so important a place in biology even at the present day, is developed by Schwann in the concluding pages of his book. He begins by contrasting the teleological with the materialistic conception of living things. In the teleological view, a special force works in the living organism, guiding and directing its activities towards a purposeful end. According to the materialistic view, there are no other forces at work in the living organism than those which act in the inorganic realm, or at least there are none but forces at one with these in their blindness and necessity. True, the purposiveness of living processes cannot be denied, but its ground lies, according to this view, not in a vital force which guides and rules the individual life, but in the original creation and collocation of matter according to a rational plan. The purposiveness of life is part of the purposiveness of the universe, just as the stars circle forever in harmoniously adjusted paths, so do the processes of life work together towards a common end. Both are the inevitable result of the original distribution of matter in the primitive chaos, a distribution fixed by a rational and foreknowing being, P222. Which of the two conceptions is to be adopted in biology? Teleological explanations have long been banished from the physical sciences, and in biology they are only a last resort when physical explanations have proved incomplete, P223. And if the ground of the purposiveness of living nature is the same as the ground of the purposiveness of the universe, is it not reasonable to suppose that explanations which have proved satisfactory for inorganic things will in time with sufficient knowledge prove adequate also for organic things? The teleological conception, again, leads to difficulties particularly when it is applied to the facts of reproduction. If we suppose that a vital force unifies and coordinates the organism and is its very essence, we must also suppose that this force is divisible and that a part of it separated in reproduction can bring about the same results as the whole. If on the contrary the forces having play in the organism are the mere result of the particular combination of the matter composing it, the reconstruction of a particular combination of molecules in the ovum is all that is necessary to set development A going along exactly the course taken by the ovum of the parent. Another argument against the teleological view is derived from the facts of the cell theory. The cell theory tells us that the molecules of the living body are not immediately built up in manifold combinations to form the organism, but are formed first into unit constructions or cells, and that these units of composition are invariably formed in all development of plants and animals alike, however diverse the goal of development may be. If there were a vital principle, would we not expect to find that, scorning this roundabout way of reaching its goal, it went straight to the mark, taking a different and distinctive course for each individual development, building up the organism direct without the intermediary of cells? But since there is a universal principle of development, namely, the formation of cells, does it not seem that the cells must be the true organisms, that the whole individual organism must be an aggregate of cells, and that the concept of individuality applied to the organism is accordingly a logical fiction? And it is just upon this notion of the individuality of the organism that the teleological concept is based. The teleological view can perhaps not be completely refuted until the adequacy of materialistic explanations has been finally shown, but it is certain that the most promising method for research is the materialistic, p. 226. We start out then from the assumption that the basis of the organism is not a force acting according to a definite plan. On the contrary, the organism arises through the action of blind and necessary laws, of forces which are as much implicit in matter as those of the inorganic world. Since the chemical elements in organic nature differ in no way from those of inorganic nature, the ground, or cause of organic phenomena can consist only in a different mode of combination of matter, either in a peculiar mode of combination of the elementary atoms to form atoms of the second order, or in the particular arrangement of these compound molecules to form the separate morphological units of the organism or the whole organism itself, p. 226. Accepting then the materialistic conception of the organism, we have to consider this further problem. Does the ground of organic processes lie in the whole organism or in its elementary parts? Translated into terms of metabolism, note the physiological point of view. The question runs, are metabolic processes the result of the molecular construction of the organism as a whole, or does the center of metabolic activity lie in the cell? Is it the cell rather than the organism that is the immediate agent of assimilatory processes? In the first alternative, the cause of the growth of the constituent parts lies in the totality of the organism. In the other alternative, growth is not the result of a force having its ground in the organism as a whole, but each of the elementary parts possesses a force of its own, a life of its own, if you will, that is to say, in each elementary part the molecules are so combined as to set free a force whereby the cell is enabled to attract new molecules and so to grow, and the whole organism exists only through the reciprocal action of the single elementary parts. In this eventuality it is the elementary parts that form the active element in nutrition, and the totality of the organism can be indeed a condition, but on this view it cannot be a cause, p. 227. To help in the decision of this question, appeal must be made to the facts established as to the cellular nature of the organism and of its reproductive elements. We know that every organism is composed of cells, which are formed and grow according to the same laws wherever they are found, whose formation therefore is everywhere due to the same forces. If we find that certain of these cells, all of which we know to be essentially identical one with another, have the power when separated from the others of growing and developing into new organisms, we can infer that not only such cells but also all other cells have this assimilatory power. The ova of animals, the spores of plants, the isolated cells of lower organisms in general, all show the power of separate assimilation and development. We must therefore, in general, ascribe to the cell an individual life, that is to say, the combination of the molecules in the single cell does suffice to produce the force whereby the cell is enabled to draw to itself new molecules. The ground of nutrition and growth lies not in the organism as a whole, but in the separate elementary parts, the cells. The fact that it is not every cell that can continue to grow when separated from the organism is not in itself an objection to this theory, any more than it is an objection to the individual life of a bee that it cannot continue to exist apart from the swarm. The activation of the forces existing within the cell depends on conditions which the cell encounters only in connection with the whole, pages 228-9. Schwann's next step is to discover what are the essential forces active in the cell, and here he enters the realm of hypothesis. He finds they can be reduced to two: an attractive force and a metabolic force. The attractive force is seen in the process of cell formation, where first of all the nucleolus is formed by a concentration and precipitation of substances found free in the cytoplasm, and in the same way the nucleus and later the cell are laid down as concentric precipitates from the cytoplasm. Cell formation also involves the second or metabolic force, by means of which the cell alters the chemical composition of the medium surrounding it so as to prepare it for assimilation. Schwann's attractive force brings about the actual taking up of the prepared substance. His metabolic force is the cause of the digestion of food substances, and is nearly identical with enzyme action. With what inorganic process, he now asks, p. 239, can the process of cell formation be most nearly compared, and the answer obviously is, with the process of crystallization. Cells are, it is true, quite different in shape and consistency from crystals, and they grow by intussusception, not by apposition. Their plastic or attractive forces seem therefore to be different. A still more important difference is that the metabolic force is peculiar to the cell. Yet there are important analogies between crystals and cells. They agree in the important respect that they both grow in solutions at the cost of the dissolved substance, according to definite laws, and develop a definite and characteristic shape. It might even be maintained, Schwann thinks, that the attractive force of crystals is really identical with that of cells, and that the difference in result is due merely to the difference between the substance of the cell and the substance of the crystal. He points out how organic bodies are remarkable for their powers of imbibition, and he seeks to show that the cell is the form under which a body capable of imbibition must necessarily crystallize, and that the organism is an aggregate of such imbibition crystals. The analogy between crystallization and cell formation he works out in the following manner: the substance of which cells are composed possesses the power of chemically transforming the substance with which it is in immediate contact, in somewhat the same way as the well-known preparation of platinum changes alcohol into acetic acid. Each part of the cell possesses this property. If now the cytoplasm is altered by an already formed cell in such a way that a substance is formed that cannot become part of the cell, it crystallizes out first as the nucleolus of a new cell. This in its turn alters the composition of the cytoplasm. A part of the transformed substance may remain in solution in the cytoplasm or may crystallize out as the beginning of a new cell. Another part, the cell substance, crystallizes round the nucleolus. The cell substance is either soluble in the cytoplasm and crystallizes out only when the latter is saturated with it, or it is insoluble and crystallizes as soon as it is formed. According to the aforementioned laws of the crystallization of imbibition bodies, it forms thus one or more layers round the nucleolus, etc. If one imagines cell formation to take place in this way, one is led to think of the plastic force of the cell as identical with the force by means of which a crystal grows, pages 249 to 50. Two difficulties have to be faced by this theory: 1. The origin of the metabolic power of the cells; 2. The reason why the cells arrange themselves so as to form an organism of complex and definite structure. Schwann tries to explain the origin of the metabolic action, the analogy of which with the contact action of colloidal platinum he recognizes, by attributing it to the peculiar structural arrangements of molecules. In attempting to account for the harmonious structure of the organism he points to the analogy of ordinary crystals, which often form complex and regular tree-like arrangements. Plants in particular resemble these regularly shaped crystal aggregates. The whole ingenious theory is offered merely as an hypothesis and a guide to research. It is interesting as one of the most carefully thought-out attempts ever made to give a thoroughgoing materialistic account of the origin and development of organic form, and it arose directly out of the cell theory. Schleiden and Schwann started out from an erroneous theory of the origin and development of cells, which impaired to some extent the value of their results. It was not long, however, before their theory of the origin of cells by crystallization from an intra- or extracellular cytoplasm was challenged and overthrown, and the generalization that cells originate by division from pre-existing cells put in its place. This was established for plant cells by Mayen, Unger, von Moll, Naegeli and Hofmeister in or about the 40s. 261 Criticism of the Schwanz-Leiden theory from the zoological side was suggested by the study of the segmentation of the ovum, the developmental process in which the multiplication of cells is most easily observed. The segmentation of the ovum was well known to Schwann, for the process had been described in the frog by Prévost and Dumas in 1824. 262 in the frog and newt by Rusconi 263, and an elaborate study of the process in the frog had been made by von Baer 264. Schwann indeed suspected that there must be some connection between the segmentation of the ovum and the formation of cells, but he did not realize that the cellular blastoderm of the chick was formed by the division or segmentation of the egg cell. Segmentation was soon found to be of widespread occurrence. Von Siebold in 1837 described the process in Entozoa 265, and in the same year Lovin saw segmentation in Campanularia 266 and SARS in the starfish, and in Nudibranchs 267. In 1838 Bischoff 268 observed segmentation in the mammalian ovum, and the whole course of segmentation in the ovum of the rabbit from the toothed to the morula stage was carefully described and figured by Berry 269 in 1839. Savoy 270 in 1842 described segmentation in Coregonus and Alodes. The discovery of segmentation in the ovum of birds was not made until 1847, by Bergman 271, confirmed independently by Cost 272 in 1850. By 1848 segmentation had been noted in hydra and various hydroids, in acalyphs, in starfish, polyzoa, nematodes, rotifers, leeches, oligochaetes, polychaetes, in most groups of mollusks and arthropods, and in all the vertebrate classes. 273 The process was at first held to be merely one of yolk division, or Dotterverchung, and its details were by most interpreted in the light of the Schleiden-Schwann theory of cell formation. The first steps towards a truer conception of the process seem to have been taken by Bergman, who in 1841-274 called attention to the presence of nuclei in the segmentation spheres of the frog's egg, and by Baggy in the same year, who observed that division of the nuclei preceded the multiplication of the segmentation spheres. 275 He considered the nuclei to be anucleate cells, and the same view was taken by Kaliker in 1843. 276 Next year, however, in his classical paper on cephalopod development 277, Kaliker came to the opinion that they were really nuclei. He showed that segmentation was brought about by cell division, that between total and partial segmentation there was a difference of degree and not of kind, and that the cells of the body were formed by division of the segmentation spheres. He held, however, that the nuclei multiplied endogenously and not by division. The division of nuclei was observed by Cost in 1846. 278 Leidig in 1848. 279 took the necessary step in advance and maintained that the nuclei as well as the cells increased always by division. He was supported by Remak, who in a paper of 1852 280 and more fully in his monumental Untersuchungen über die Entwicklung der Wurzeltiere, Berlin, 1850-55, proved that in the frog's egg at least segmentation was a simple process of cell division, initiated always by division of the nucleus. 281 One point Remak left undecided the fate of the Cameblaskin or egg nucleus. It was generally held, even so late as the 50s, that the egg nucleus disappeared just before segmentation began. Bischoff clung to this belief even in 1877. 282 Though Berry had held in 1839 that the egg nucleus does not disappear in segmentation, J. Muller seems to have been the first actually to prove that it forms by division the nuclei of the first two segmentation spheres. He furnished the demonstration in the egg of Entoconcha mirabilis 283, and his paper was known to Remak, who could not, however, observe a similar division of the egg nucleus in the frog. Muller's discovery was confirmed for Oceania armata by Gegenbohr 284 and for Notomata Seboldii by Leydig 285 in 1854. Virchow 286, previously a supporter of Schwann, crystallized the new views in the famous phrase omnes cellula e cellula and gave wide publicity to them in his classical lectures on cellular pathology, delivered in 1858. 287. The new doctrine of cell formation was also taught by Leydig 288 in his textbook of histology, published in 1857. The Schleiden-Schwann theory of the origin of cells by generation in a cytoplasm was now definitely overthrown. The importance of the protoplasmic content of the cell was brought into prominence through the work of Dujardin 289, Pourcagnier 290, Cohen 291 and Max Schulze 292. The last named in 1861 proposed a definition of the cell which might be accepted at the present day. A cell, he wrote, is a little blob of protoplasm containing a nucleus, p11. 238. Theoria Generationis, Haley, 1759. 239. C. J. V. Sachs, Geschichte der Botanik, Book 2, ENG Transaction, 2nd Impair, 1906. 240. Muller's Archive, pages 137-76, 1838. 241. Transaction Linnean SOC, 16, p. 710, 1833. 242. Myxinoiden, Ithiel, p. 89, 1835. 243. And Synad. 2, Zoel, 2, pages 107-18, pl 11, 1834. 244. PROC Philosophy SOC Glasgow, 19, pages 71-125, 1887-8. 245. Traits sur le venin de la vipera, 1781. 246. Muller's Archive, 1836. 247. J. Muller, Jahresbericht ud Fortschritt der Anatomie Physialwissenschaften im Jahr 1838. Muller's Archive, 1838. 248. Symboli ad anatomiam villarum imprimis eorum epithelii, Berlin, 1837. 249. Ud Ausbreitung de Epitheliums im menschlichen Körper. Muller's Archive, 1838. 250. C. Schwann's Bemerkungen at the end of his Mikroskopische Untersuchungen. 251. Republished in Ostwald's Klassiker der Exakten Wissenschaften, No. 176, Leipzig, 1910. References in the text are to the original pagination. 252. Symboli ad ovi avium historium. 253. De ovi mammalium et hominis genesi. 254. De mulierum organis, 1672. 255. And Synad, 3, p. 135, 1842. 256. Recherches sur la génération de mammifères. Report by Academy Committee. And Synad. 2, Zoel, 2, pages 1-18, 1834, also Embryogeniae Compari, 1837. 257. London. And Eden. Philosophy Mag, 3, 7, 1835, Philosophy Transaction 1837. 258. Handbuch der Entwicklungsgeschichte, 1835, and Muller's Archive, 1836. 259 Prodromus Historiae Generationis Hominis et Animalium, Lipsii, 1836. 260 Muller's Archive, 1837. 261 Sachs, History of Botany, Book 2. 262 and Synat, I, pages 110 to 14, 1824. Swammerdam is said to have observed the two-celled stage in the egg of the frog, Biblnat, 1752, and Rosel v. Rosenhoff the same stage in the tree frog, Histori nat ranarum nostratium, 1758. 263 Developiment de la Grenouille Commune, Milan, 1826. Biblioteca Italiana, L6, 1836, and Muller's Archive, 1836. Agassiz is said by Voigt, 1842, to have seen segmentation in the perch as early as 1831. 264 Muller's Archive, 1836. 265 in Berdake, Die Physiologie als Erfahrungswissenschaft, 2nd ed., Volume 2. 266 Wiegmann's Archive, 1837. 267 Berichtversum. Deutsch. Naderf. In Prague, 1837. 268 Berichtversum. Deutsch. Naderf. In Freiburg, 1838. Later in his Entwurf. Die Werbelth, and in his papers on the development of the rabbit. 269 Philosophy Transaction, 1839. See particularly PL6, figures 105 to 12. 270 Embryologie des Salmons 1842. 271 Muller's Archive, 1847. 272 CR Academic Sci, XXX, p. 638. 273 C Review by Leydig in Isis, 1848, pages 161 to 193. 274 Muller's Archive, pages 89 to 102, 1841. 275 De Evolution Strenzili Auric. L. Ascaridesicum, Erlangen, 1841. 276 Muller's Archive, pages 66 to 141, 1843. 277 Entwicklungsgeschichte Cephalopoden, Zurich, 1844. 278 Furiops Notizen, number 800, 1846. 279 Isis, 1848. 280 Muller's Archive, p. 47, 1852, also 1854 and 1858. 281 See particularly Plate 9, figures 3 to 7. 282 History Crit. Bemerkungen zu den neuesten Mitteilungen u die erste Entwicklung die Sagathierier, München, 1877. 283 Minitzber. Akkad. Wyss. Berlin, 1851. 284 Zur Lehre von Generationswechsel u die Fortpflanzen die Medicine u Polypen. 285 UD Bau UD System. Stellung die Rater the Air, 1854. 286 Arch F path. Anat Physical, 7, pages 1 to 39, 1854. Also in his Beitrage Z spec path. Eutherapy. 287 Dicellular Pathology, Berlin, 1858. 288 Lehrbuch der Histologie, 1857. 288 N, Synat. 2, 3, pages 108 to 9 and pages 312 to 4, 1835. Also 4, pp 343 to 77. 291,839 or 1,840. 291 Nova Acta Academic Leop, XXII, 1850. Transaction in 1853 for Ray Society. 292 Arch F. Anat Physiol, pages 1 to 27, 1861. Chapter 12 The close of the pre-evolutionary period. The influence of the cell theory on morphology was not altogether happy. The cell theory was from the first physiological. Cells were looked upon as centers of force rather than elements of form, and the explanation of all the activities of the organism was sought in the action of these separate dynamic centers. There resulted a certain loss of feeling for the problems of form. The organism was seen no longer as a cunningly constructed complex of organs, tissues, and cells. It had become a mere cell aggregate. The higher elements of form were disregarded and ignored. We have seen this physiological attitude expressed with the utmost clearness by the founder of the cell theory himself. We shall see the same attitude taken up by most of his successors. Thus Voigt, who was later to become one of the protagonists of materialism in Germany, developed in his memoir on the embryology of Coorganus 293 the theory of the independent or individual life of the cell. Each cell, he wrote, represents in some measure a separate organism, and while their development necessarily conforms to the general plan and the particular tendencies of the parent organism, they nevertheless each follow their own particular tendency and do not lose their independence until, by reason of the metamorphoses which they undergo, they lose their cellular nature, p. 275. And again, we are obliged to admit the existence in the cell of an independent life, which makes its development self-sufficient. Each cell consequently represents a little independent organism, which assimilates foreign substances, builds them up, and rejects those that are useless. From this point of view the embryo can be compared up to a certain point with a zoophyte stock, of which each polyp, while living its own independent life, is yet incorporated in the common corm, which impresses its distinctive character upon every polyp, p. 293. Classical expression was given to the colonial theory of the organism by Virchow in his lectures on cellular pathology. 294 For Virchow the organism resolves itself into an assemblage of living centers, the cells. The organism has no real existence as a unity, for there is no one single center from which its activities are ruled. Even the nervous system, which appears to act as a coordinating center, is itself an aggregate of discrete cells. A tree is a body of definite and orderly composition, the ultimate elements of which, in every part of it, in leaf and root, in stem and flower, are cellular elements. So also are animal forms. Every animal is a sum of vital units, each of which possesses the full characteristics of life. The character and the unity of life cannot be found in one definite point of a higher organization, for example in the brain of man, but only in the definite, constantly recurring dispositions shown individually by each single element. It follows that the composition of the major organism, the so-called individual, must be likened to a kind of social arrangement or society, in which a number of separate existences are dependent upon one another, in such a way, however, that each element possesses its own particular activity, and, although receiving the stimulus to activity from the other elements, carries out its own task by its own powers. 2nd ed., pages 12 to 13. Analysis, decomposition, or disintegration of the organism is here pushed to its extreme point, and the problem of recomposition, synthesis, and coordination shirked or forgotten. The harmful influence of the cell theory upon morphology did not pass unnoticed by the broader-minded zoologists of the day. Virchow's earlier paper 295 on the application of the cell theory to physiology and pathology called forth a vigorous protest from Riker 286, who discussed in a very instructive way the contrast between the older systematic and the newer atomistic attitude to living nature. Is it really true, he asks, that the cell is the dominant element in all organization? Is the cell comparable in importance to the atom of the chemists, or is it not rather the servant of a higher regulatory power? Johannes Müller, who was Reichert's master, had in his Physiology 297 argued splendidly for the existence of a creative force which guides and rules development, and brings to pass that unity and harmony of composition which distinguish living things from inorganic products. Reichert sought in vain in the writings of the biological atomists for any smallest recognition of these broader characteristics of living things upon which Müller had rightly laid stress. For the atomists the cell was the only element of form. They ignored the combination of cells to form tissues, of tissues to form organs, of organs to form an organism. For the morphologists the cell was one element among many, and the lowest of all. The difference of attitude is clearly shown if we consider from the 2 points of view a complicated organ system such as the central nervous system. The atomist sees in this a mere aggregate of cells, or at the most of groups of cells. The morphologist, on the other hand, sees in the central nervous system a proximate element in the composition of the body, a primitive organ. From this point of view he apprehends and judges its morphological relations with, in the first place, the other coordinated primitive organs in the system as a whole. In all this the cells remain in the background, and have nothing to do directly with the determination of these morphological relations. p. 6. Within the nervous system there are separate organs which stand to one another in a definite morphological and functional relationship. These organs are, it is true, composed of cells, but between the form and connections of these organs and the cells which compose them there is no direct and necessary relation. p. 6. It is true that the cell is the ultimate element of organic form, and that all development takes place by multiplication and form change of cells. Yet is the cell in all this not independent of the unity of the developing embryo, and what the cells produce, they produce, so to speak, not of their own free will, nor by chance, but under the guiding influence of the unity of the whole, and in a certain measure as its agents. p. 7. The atomists will not admit the truth of this. They see in development nothing more than a process of the form change and multiplication of cells. The full meaning of development escapes them, for they take no cognizance of the increasing complexity of the embryo, of the separating out of tissues, of the molding of organs, of the harmonious adaptation and adjustment of the parts to form a working whole. In general, the fault of the atomists is that they do not respect the limits which nature herself has prescribed to the process of logical analysis and disintegration of the organism. They do not recognize the existence of natural and rational units or unities. They forget the one great principle of rational analysis, that, by universally valid, inductive, logical method, natural objects must in all cases be accepted and dealt with in the combination and concatenation in which they are given. p. 10. The atomists at least recognized one natural organic element, the cell. The materialistic physiologists of the time resolved even this unity into an aggregate of inorganic compounds, and regarded the organism itself as nothing but a vastly complicated physico-chemical mechanism. From this point of view, morphology had no right of existence, and we find Ludwig, one of the foremost of the materialistic school, maintaining that morphology was of no scientific importance, that it was nothing more than an artistic game, interesting enough, but completely superseded and robbed of all value by the advance of materialistic physiology. 298. Naturally enough, morphologists did not accept this rather contemptuous estimate of their science, but held firmly to the morphological attitude. So Lückert in his reply to Ludwig, so Rathke in a letter to Lückert published in that reply, so Reichert in his Bericht, so J. V. Karras in his System der Theoretischen Morphologie. 299 upheld the validity, the independence, of morphological methods. Lückert and Rathke called attention to the absolute impossibility of explaining by materialistic physiology the unity of plan underlying the diversity of animal form. J. V. Karras, who was convinced of the validity of physiological methods within their proper sphere, drew a sharp distinction between systematics and morphology on the one hand, and physiology on the other. Physiology had nothing to do with the problems of form at all. Its business was to study the physical and chemical processes which lay at the base of all vital activities. Morphology, on its part, had to accept form as something given, and to study the abstract relations of forms to one another. On this point, he writes, stress is to be laid, that morphology has to do with animal form as something given by nature, that though it follows out the changes taking place during the development of an animal and tries to explain them, it does not inquire after the conditions whose necessary and physical consequence this form actually is. p. 24. He expressed indeed a pious hope, p. 25, that physiology might one day be so far advanced that it could attempt with some hope of success to discover the physico-chemical determinism of form, but this remained with him merely a pious hope. Reichert, in his Bericht, applied to the rather wild theorizings of the physiologist Ludwig the same clear common-sense criticism that he bestowed on the other atomists. It would take too long to describe the great development that materialistic physiology took at this time, and to show how the separation of morphology from physiology, which originally took place away back in the 17th century, had by this time become almost absolute. The years towards the end of the first half of the century marked indeed the beginning of the classical period as well of physiology as of dogmatic materialism. Mohlschott and Buchner popularized materialism in Germany in the 50s, while Ludwig, Du Bois-Reymond and von Helmholtz began to apply the methods of physics to physiology. In France, Claude Bernard was at the height of his activity, rivaled by workers almost as great. The doctrine of the conservation of energy was established about this same time. Between the cell theory on the one side, and physiology on the other, it was a wonder that morphology kept alive at all. The only thing that preserved it was the return to the sound Cuvierian tradition which had been made by many zoologists in the 30s and 40s. It is a significant fact that this return to the functional attitude coincided in the main with the rise of marine zoology, and that the man who most typically preserved the Cuvierian attitude, H. Milne Edwards, was also one of the first and most consistent of marine biologists. Milne Edwards describes in his interesting Rapport sur les progrès récents des sciences zoologiques en France, Paris, 1867, how about the year 1826, two young naturalists, formed in the schools of Cuvier, Geoffroy and Mayendi, considered that zoology, after having been purely descriptive or systematic and then anatomical, ought to take on a more physiological character. They considered that it was not enough to observe living objects in the repose of death, and that it was desirable to get to understand the organism in action, especially when the structure of these animals was so different from that of man that the notions acquired as to the special physiology of man could not properly be applied to them. p. 17. The two young naturalists were H. Milne Edwards and V. Audouin. In pursuance of these excellent ideas they set to work to study the animals of the seashore, producing in 1832 to 42 volumes of Recherches pour servir à l'histoire naturelle du littoral de la France. After Audouin's early death, A. de Quatrefages was associated with Milne Edwards in this pioneer work, and their valiant struggles with insufficient equipment and lack of all laboratory accommodation, and the rich harvest they reaped, may be read of in Quatrefages' fascinating account of their journeyings. 300 Note that though they called themselves physiologists, they meant by physiology something very different from the mere physical and chemical study of living things. They were interested, as Cuvier was, primarily in the problems of form. They sought to penetrate the relation between form and function. Their chief aim was, therefore, the study not of physiology 301 in the restricted sense, but physiological morphology. As a matter of fact, they produced more taxonomic and anatomical work than work on physiological morphology, but this was only natural, since such a wealth of new forms was disclosed to their gaze. Milne Edwards' masterly Histoire naturelle de crustacés 302 and A. de Quatrefages' Histoire naturelle des annales marins et d'eau douce 303 were typical products of their activity. In the north, men like Sars and Lovin were starting to work on the littoral fauna of the fjords. In Britain, Edward Forbes was opening up new worlds by the use of the dredge. Johannes Müller was using the townet to gather material for his masterly papers on the metamorphoses of echinoderms. 304 Work on the taxonomy and anatomy of marine animals was in general in full swing by the 50s and 60s. This return to nature and to the sea had a very beneficial effect upon morphology, bringing it out from the laboratory to the open air and the seashore. It saved morphology from formalism and aridity, and in particular from a certain narrowness of outlook born of too close attention paid to the details of microscopical anatomy. It brought morphologists face to face again with the wonderful diversity of organic forms, with the unity of plan underlying that diversity, with the admirable adjustment of organ to function and of both to the life of the whole. Milne Edwards' theoretical views, as expounded in his Introduction à la zoologie générale, 1851, well reflect this Cuvierian attitude. 305 He acknowledges himself the debt he owes to Cuvier. The further I advance in the study of the sciences which he cultivated with so sure a hand, he writes in 1867, the more I venerate him. Milne Edwards frankly takes up the teleological standpoint, and interprets organic forms on the assumption that they are purposive and rationally constructed. To arrive at an understanding of the harmony of the organic creation, he writes, it seemed to me that it would be well to accept the hypothesis that nature has gone about her work as we would do ourselves according to the light of our own intelligence, if it were given us to produce a similar result. Comparing and studying living things as if they were machines created by the industry of man, I have tried to grasp the manner in which they might have been invented, and the principles whose application would have led to the production of such an assemblage of diversified instruments, p. 435. The problem is to discover the laws which rule the diversity of organic forms. The first and most obvious of these laws is the law of economy, or the law of unity of type. Nature, as Cuvier pointed out, has not had recourse to all the possible forms and combinations of organs. She appears to work with a limited number of types and to get the greatest possible diversity out of these by varying the proportions of the constitutive materials of structure. Within the limits of each type, nature has brought about diversity by raising her creatures to different degrees of perfection. This is the second law of organic form, and it is this law that Milne Edwards chiefly elaborates. Degrees of perfection mean for him, as for Aristotle, primarily degrees of perfection of function, but since structure is necessarily in close relation with function, perfection of function brings in its train increased perfection of organization. This can only be attained by a division of labor 306 among the organs and by their consequent differentiation. An animal is like a workshop where some complicated product is manufactured, and the organs are like the workmen. Each workman has his own special piece of work to do, at which he becomes thoroughly expert, and the finished product is manufactured more rapidly and efficiently by the cooperation of workers each skilled in one department than it would be if each workman had to produce the whole. Applied to the organism, this principle of the division of labor means the differentiating out of the separate functions, their localization in different parts of the organism, and their coordination to produce a combined result. This differentiation of functions implies a corresponding differentiation of organs, but it is functional differentiation which always takes the lead. Where division of labor has not been introduced into the organism, there must exist a great simplicity of structure. But just as uniformity in the functions of the different parts of the body implies a uniformity in their mode of constitution, so diversity in function must be accompanied by particularities in structure, and, in consequence also, the number of dissimilar parts must be augmented and the complication of the machine increased. P 463. Since function comes before form, there is not always a special organ for every function. It is a grave error to believe that a particular function can be performed only by one and the same organ. Nature can arrive at the desired result by various ways, and when we look down through the animal kingdom from the highest to the lowest forms, we see that the function does not disappear even when the special instrument provided for the purpose in the higher type ceases to exist. P 470. Nature, holding fast to the law of economy, does not even always create a new organ for a new function. She may simply adapt an undifferentiated part to special functions, or she may even convert to other uses an organ already specialized. P 464. So, for example, the function of respiration is in the lowest animals diffused indifferently over the whole surface of the body, and only as organization advances is it localized in special organs, such as gills. Now suppose that nature wishes to adapt a fish, which breathes by gills, to life in the air. She does not create an organ specially for this purpose, but utilizes the moist gill chamber, example in Anabas scandens, modifying it in certain ways so that the fish can take advantage of the oxygen it contains. But this gill chamber lung is at best a makeshift, and when she comes to the more definitely terrestrial amphibian, nature gives up the attempt to use the gill chamber as a lung, and creates a new organ, the true vertebrate lung, specially adapted for breathing air. P 475. But whatever means nature adopts, her aim is always the same: to specialize, to differentiate, to produce diversity from uniformity. Differentiation not only raises the level of organization, it usually also takes the direction of adaptation to particular habits of life, and this is perhaps the most fruitful cause of diversity. Everywhere we find animals specialized in adaptation to their environment, to life in air or water, or on land, and many of their most striking differences are due to this cause. But adaptation may also act in reducing diversity, for there necessarily occur many instances of parallel adaptation or convergence. So we get the extraordinary parallelism between the families of marsupials and the orders of placentals. 307. The remarkable similarity between the respiratory organs of land crabs and air-breathing fish, to mention only two out of an immense range of analogous facts. The last cause of diversity that Milne Edwards adduces is what he calls a borrowing of peculiarities of structure from another systematic group. Thus, among reptiles, the tortoises seem to have borrowed from birds some of their characteristic features of organization, and among the sauroid fishes the piscine type seems to have been influenced by the type from which reptiles are derived. P 479. So many riddles that, a little later on, stimulated the ingenuity of the evolutionists. Such, then, were the factors which Milne Edwards considered adequate to explain the rich variety of animal forms. We cannot do better than quote his own summary of his doctrine to sum up, then, the great differences introduced by nature into the constitution of animals seem to depend essentially upon the existence of a certain number of general plans or distinct types, upon the perfecting in various degrees either of the whole or of parts of each of these structural plans, upon the adaptation of each type to varied conditions of existence, and upon the secondary imitation of foreign types by certain derivatives of each particular type, p. 480. We have laid stress on the fact that Milne Edwards put function before form, for this is the mark of the true Cuvierian. With it goes the belief that nature forms new parts to meet new requirements, that she is not limited, as Geoffroy thought, to a definite number of materials of organization, but can produce others at need. Cuvier held, for example, that many of the muscles and even the bones of fish were peculiar to them, and without homologues in the other vertebrates, having been created by nature for special ends. 308. So, too, Johannes Müller, who in many ways and not least in his sane vitalism was a follower of the Cuvierian tradition, recognized that many of the complicated cartilages in the skull of cyclostomes were specially formed for the important function of sucking, and had no equivalent in other fish. 309. So, too, the embryologists after Cuvier often came across instances of the special formation of parts to meet temporary needs. Thus Reichert interpreted the palatine and pterygoid, which are formed in the mouth of the newt larva by a fusion of conical teeth, as special adaptations to enable the little larva to lead a carnivorous life. 310. Not many years after the publication of Milne Edwards' Introduction à la Zoologie Générale, 1851, there appeared a book by H. G. Braun in which was offered a very similar analysis of organic diversity. The curious thing was that Braun approached the problem from quite a different standpoint, from the standpoint, indeed, of nature philosophy. Of this the title of the book is itself sufficient proof. Morphologische Studien über die Gestaltungsgesetze der Naturkörper überhaupt und der Organismen insbesondere, Leipzig and Heidelberg, 1858. 311. The linking up of organic with inorganic form is characteristic. There is much talk, too, in the book of Erstoff and Erkraft, but underlying the nature philosophy we can trace the same Cuvierian treatment of form, and see crystal out laws of progressive development that bear no small analogy with the laws established by Milne Edwards. According to Braun, the ideal fundamental form of the plant is an ovoid or strobiloid. 312. Body, for a plant reaches out in two directions in search of food towards the sun and towards the earth. Animals differ from plants in being endowed with sensation and mobility, cf. Aristotle and Cuvier, and it is this characteristic that gives them their distinctive form. The main types of animal form, the Amorphozoa, Actinozoa, and Hemisphenozoa, are essentially adaptations to particular modes of locomotion. Animals either are fixed, or they move in all directions without reference to any definite axis, or they move in one main direction. The Amorphozoa or shapeless animals include many of the protozoa and sponges. They have no typical form, and most of them are sessile. The Actinozoa include such animals as the Coelentra, which are fixed, and the Echinoderms, which have a central point and move indifferently along any radial axis. Their form differs from the strobiloid mainly in having radiate rather than spiral symmetry. The Hemisphenozoa, or bilaterally symmetrical animals, include all those that habitually move forward. They have a front end and a hind end, a dorsal surface and a ventral, and the mouth, sense organs, and brain are concentrated in the front end to form a head, all in direct adaptation to this forward movement. They make up the vast majority of animals. The fundamental forms of living things are, however, merely so many themes on which a multitude of further variations are woven, through the action of the laws which rule the detail of organic diversities. These further laws may be set down under four main heads. Under the first comes the law of the existence of certain fundamentally distinct structural types, which are distinguished from one another by their ground form, by the number of organ systems, and by the number of homotypic organs they possess, but principally by the relative position of the organs to one another, principle of connections. The form and connections of the nervous system are of particular importance in distinguishing the types, cf. Cuvier. The second factor in the diversity of organic form is the action of certain laws of progressive development 313, Entwicklungsgesetze, which bear the same relation to the development of the animal kingdom as the laws of individual development bear to the development of the embryo, for organs appear in the different animal series in much the same order and manner as they develop in the individual. These laws are, 1. Progressive differentiation of functions and organs, 2. Numerical reduction of serially repeated parts, 3. Concentration of functions and their organs in particular parts of the body, 4. Centralization of organ systems and parts of such, so that they come to depend upon one central organ, 5. Internalization of the noblest organs, unless these are necessarily external, and 6. Increase in size of the whole or of parts. Of these the law of differentiation is by far the most important, and most of the others are in a sense merely special cases of this fundamental law. To this law of differentiation is due the increase in complexity or perfection of organization which is shown by all the animal series. Braun himself recognized the great similarity of this law of progressive differentiation to Milne-Edwards' principle of the division of labor. He seems, however, to have arrived at it independently. Braun's third factor in the production of variety of form is adaptation to environment, or better, functional response to environment. Braun gives an excellent account of adaptational modifications and calls attention, just as Milne-Edwards did, to the numerous analogies of structure which adaptation brings about. He works out the interesting view that there is some connection between classificatory groups and adaptational forms, especially such as are connected with the function of locomotion based upon a common characteristic method of locomotion are whole or nearly whole subphyla, hexapoda, classes, mammals and reptiles, birds, fishes, gastropods, pteropods, brachiopods, bryozoa, rotifera, jellyfish, polypes, sponges, subclasses, mobile and immobile lamellibranchs, echinoderms, walking and swimming crustacea, parasitic and free-living worms, and so on, often, however, only orders and quite small groups, snakes, eels, bats, sepias, medusae, etc. p. 141. It was characteristic of the 40s and 50s that transcendental anatomy, along with nature philosophy, went rather out of fashion, its false simplicities and premature generalizations being overwhelmed by the flood of new discoveries. A few stalwarts indeed upheld transcendental views. We have already discussed the morphological system built up by Richard Owen in the late 40s, a system transcendental in its main lines. We have seen the vertebral theory of the skull still maintained in the 50s by such men as Reichert and Kalliker, and we find J. V. Karras in 1853-314 taking it as almost conclusively proved. 315 we may mention, too, as showing clear marks of the influence of transcendental ideas, L. Agassiz' work on the principles of classification 316 and Serres, who was Geoffroy's chief disciple, recanted not a whit of his doctrine of recapitulation, but reaffirmed and expanded it from time to time. And particularly in a lengthy memoir published in 1860-317. But in general we may say that pure morphology in the Geoffroyan or Ocanian sense was becoming gradually discredited. A curious indication of this is seen in the fact that not only the idea but the very word archetype came to be regarded with suspicion. Thus even J. V. Karras, who had much affinity with the Transcendentalists, wrote of the vertebrate archetype, which he took over almost bodily from Owen. It may here be observed that this schema may be used as a methodological help, but it is not to be placed in the foreground. LOCCIT, p. 395. Huxley, who was definitely a follower of von Baer, was much more outspoken with regard to ideal types. In an important memoir on the general anatomy of the gastropoda and cephalopoda 318, he set himself the task of reducing all their complex forms to one type. In summing up, he writes, from all that has been stated, I think that it is now possible to form a notion of the archetype of the Cephalus mollusca, and I beg it to be understood that in using this term, I make no reference to any real or imaginary ideas upon which animal forms are modelled. All that I mean is the conception of a form embodying the most general propositions that can be affirmed respecting the Cephalus mollusca, standing in the same relation to them as the diagram to a geometrical theorem, and like it, at once imaginary and true. p. 176. Again, in his Croonian lecture on the theory of the vertebrate skull, he remarks that a general diagram of the skull could easily be given. There is no harm, he continues, in calling such a convenient diagram the archetype of the skull, but I prefer to avoid a word whose connotation is so fundamentally opposed to the spirit of modern science. Sci Memoirs, Volume I, p. 571. It is instructive to find that between Serres and Milne-Edwards there existed the same antagonism as between von Baer and the German Transcendentalists. Milne-Edwards was a constant critic of the law of parallelism, which Serres continued to uphold with little modification for over 30 years, just as von Baer was a critic of that form of the doctrine which was current in the early part of the century. As early as 1833, Milne-Edwards, through his studies of crustacean development 319, had come to the conclusion, independently of von Baer, that development always proceeded from the general to the special, that class characters appeared before family characters, generic characters before specific. In an interesting paper published in 1844 320 he discussed the relation of this law of development to the problems of classification, and arrived at results almost identical with those set forth by von Baer in his Fifth Scholion. Like von Baer, he rejected completely the theory of parallelism and the doctrine of the scale of beings. Like von Baer, he held that the type of organization, of which there are several, is manifested in the very earliest stages and becomes increasingly specialized throughout the course of further development. Like von Baer, too, he sketched a classification based upon embryological characters. These views were further developed in his volume of 1851, and also in his rapport of 1867. They brought him into conflict with his confrere in the Academy of Sciences, Etienne Serres, who in a number of papers published in the 30s and 40s 321, and particularly in his comprehensive memoir of 1860, still maintain the theory of parallelism and the doctrine of the absolute unity of type. His memoir of 1860 shows how completely Serres was under the domination of transcendental ideas. Much of it indeed goes back to Oken. The animal kingdom, he writes, may be considered in its entirety as a single ideal and complex being, p. 141. His views have become a little more complicated since his first exposition of them in 1827, and he has been forced to modify in some respects the rigor of his doctrine. But he still holds fast to the main thesis of transcendentalism, the absolute unity of plan of all animals, vertebrate and invertebrate alike. 322 The gradual perfecting of organization from monad to man, the repetition in the embryogeny of the higher animals of the zoogeny of the lower. He recognized, however, that the idea of a simple scale of beings is only an abstraction, and that the true repetition is of organs rather than of organisms. he was willing even to admit, at least in the later pages of his memoir, that there might be not one animal series but several parallel series, as had been suggested by Isidore Geoffroy Saint-Hilaire, p. 749. In general, his views are now less dogmatic than they were in his earlier writings, but they are not for all that changed in any essential. For, in summing up his main results, he writes, the whole animal kingdom can in some measure be regarded ideally as a single animal, which, in the course of formation and metamorphosis in its diverse manifestations, here and there arrests its own development, and thus determines at each point of interruption, by the very state it has reached, the distinctive characters of the phyla, the classes, families, genera, and species, p. 833, 323 to settle the dispute pending between two of its most illustrious members. The Academy proposed in 1853, as the subject of one of its prizes, the positive determination of the resemblances and differences in the comparative development of vertebrates and invertebrates. A memoir was presented the next year by Lear-Bulliet 324 which met with the approval of the Academy in so far as its statements of fact were concerned, but seemed to them to require amplification in its theoretical part. But even in this memoir Lear-Bulliet was able to show that the balance of evidence was greatly in favor of Milne-Edwards' views, and his general conclusions in 1854 were that in the presence of such fundamental differences, one is obliged to give up the idea of one single plan in the formation of animals, while, on the contrary, the existence of diverse plans or types is clearly demonstrated by all the facts, p. 79. To fulfill the Academy's requirements, Lear-Bulliet continued his work, and in 1861–63 he published a series of elaborate monographs 325 on the embryology of the trout, the lizard, and the pond snail Limnaea, and rounded off his work with a full discussion 326 of the theoretical questions involved. In this considered and authoritative judgment he completely disposed of Serre's theories of the unity of plan and the unity of genetic formation. Except in the very earliest stages of oogenesis there is no real similarity between the development of a zoophyte, a mollusk, an articulate and a vertebrate, but each is stamped from the beginning with the characteristics of its type. The lower animals are not, and cannot possibly be the permanent embryos of the higher animals. The results which I have obtained, he writes, are diametrically opposed to the theory of the zoological series constituted by stages of increasing perfection, a theory which tries to demonstrate in the embryonic phases of the higher animals a repetition of the forms which characterize the lower animals, and which has led to the assertion that the latter are permanent embryos of the former. The embryo of a vertebrate shows the vertebrate type from the very beginning, and retains this type throughout the whole course of its development. It never is, and never can be, either a mollusk or an articulate, XX, p. 54. We are led to establish, as the general result of our researches, the existence of several types, and, consequently, of different plans, in the development of animals. These different types are manifested from the very beginning of embryonic life, the characters distinguishing them are therefore primordial, and we can say with M. Milne-Edwards that everything goes to prove that the distinction established by nature between animals belonging to different phyla is a primordial distinction, p. 58. In other directions also von Bayer's work was confirmed and extended by later observers, those parts of it particularly that had reference to the germ layer theory, and to the concept of histological differentiation. His germ layer theory was accepted in its main lines by Rathke, Bischoff, and Lear-Bulliet, and applied by them to the multitude of new facts they discovered. Rathke, in particular, was a firm upholder of the doctrine, and made considerable use of it in his writings. 327 Even before the publication of von Bayer's book, he had interpreted in terms of the germ layer theory sketched by his friend Pander the splitting of the blastoderm which occurs in the early development of Astacus, whereby there are formed a serous and a mucus layer, one inside the other like the coats of an onion. To use his own expressive phrase, 328 An ingenious application of the Pander-Bayer theory was made by Huxley, who compared the outer and inner cell layers which form the groundwork of the coelentra with the serous and mucus layers of the vertebrate germ. 329 He laid stress, it is true, rather on the physiological than on the morphological resemblance. A complete identity of structure, he writes, connects the foundation membranes of the medusae with the corresponding organs in the rest of the series, and it is curious to remark, that throughout, the outer and inner membranes appear to bear the same physiological relation to one another as do the serous and mucus layers of the germ, the outer becoming developed into the muscular system, and giving rise to the organs of offense and defense, the inner, on the other hand, appearing to be more closely subservient to the purposes of nutrition and generation. p. 24. Von Baer had already hinted at this homology in the second volume of his Entwicklungsgeschichte, 1837, where he says with reference to the separation of the blastoderm of the chick into two layers. Yet originally there are not two distinct or even separable layers, it is rather the two surfaces of the germ which show this differentiation, just as polyps show the same contrast of an external surface and an internal digestive surface. In between the two layers there is in our germ as in the polyp an indifferent mass. p. 67. The terms ectoderm and entoderm were introduced by Ullmann 330 in 1853 for the two cell layers in the hydrozoa. Remak is the second great name in the history of the germ layer theory. He had the great advantage over von Baer of being able to make use of the cell theory in interpreting the formation of the germ layers. Microscopical technique also had been greatly improved since 1828. 331 Remak's greatest service was that he put the germ layer theory in direct relation with the cell theory by demonstrating the cellular continuity from egg cell to tissue, and by showing that each germ layer possessed distinctive histological characteristics. Hardly less important was his clear marking off of the middle layer as a separate and distinct layer of the germ. He it was who introduced the modern conception of the mesoderm, and cleared up the confusion in which Pander and von Baer had left the organs formed between the serous and the mucus layer. Remak's middle layer was a different thing from Pander's ill-defined vessel layer, it included and unified from a new point of view the vessel and muscle layers of von Baer. There are in the unincubated blastoderm of the chick, according to Remak 332 two-cell layers, of which the undermost subsequently splits into two. Three layers are thus formed: the upper, middle and lower. The upper layer differentiates into a medullary plate and an epidermic plate, Remak's hornblatt, and gives origin to the medullary tube with all its evaginations, and to the skin with all its derivatives and pockets. It forms such diverse structures as the brain, the spinal cord, the eye, the ear, the mouth, hairs, feathers, nails, sweat glands, lacrimal glands, and so forth. All these parts are connected directly or indirectly with sensation, and the upper germ layer may accordingly be called the sensory layer. The lower layer gives rise to the epithelium and the proper tissue of the alimentary canal and its derivatives, as the liver, lungs, pancreas, kidneys, thyroid, thymus, etc. These parts are all concerned in the processes of assimilation and assimilation, and the lower layer may accordingly be called the trophic layer. Now between the upper or sensory layer and the lower or trophic layer there exists, in spite of their very different functions, a close histological likeness, for both are essentially epithelial layers. The resemblance is particularly strong if we compare the lower layer with the hornblatt of the upper layer. Both consist of epithelial tissue, and of its derivative, glandular tissue, and form neither vessels nor nerves. The middle layer, on the contrary, forms nerves and muscles, vessels and connective tissue, and little or no epithelium. It does not form all the blood vessels without exception, and so cannot be called the vessel layer, for the blood vessels of the central nervous system are in all probability formed from the upper layer. So, too, it does not form all the nerves and muscles. The optic and auditory nerves and the nerves and muscles of the iris probably arise in the upper layer. But, in spite of these exceptions, its general histological character is so well defined that it may be contrasted with the other two as preeminently the layer that forms muscular, nervous, vascular, and connective tissue. In view of its functional significance, it may be called the motory layer, or better, since it forms also the sexual glands, the motor germinative layer. The middle layer, early in its history, shows a division into dorsal plates, Urwerbelplatten, and ventral plates, Setonplatten. The former exhibit almost as soon as they are formed the characteristic protovertebral segmentation, the latter split to form the pleuroperitoneal or body cavity. Remak describes the latter process as follows: in the region of the trunk, where a greater independence of the fate of the alimentary canal and its annexes becomes necessary for the voluntary executive organs, the ventral plates undergo a process of splitting, leading to the formation of the sensitive part of the integument, the hoplaten, the muscular part of the alimentary tube, the darmfaserplaten, and the mother tissue of the generative organs, the middle platen. From the hoplaten there develops, without the dorsal plate seeming to take any part in the process, the rudiment of the extremities, p79. His darmfaserplaten form the nervous and muscular tissue of the alimentary canal and its dependencies, and also the heart. The hoplaten form the general body wall, exclusive of the skin, and the appendages. In the embryo they line the amniotic cavity. The skeleton and peripheral nerves originate wholly within the middle layer. Remak's conception of the relations of the three germ layers to one another and to the body cavity is well illustrated in Fig 12. Fig 12 transverse section of chick embryo. After Remak, H. epidermis. H. Podplat X edge of the smniotic fold. M. spinal cord. And pH pleuroperitoneal cavity. Mu. Dorsal plate. UG. Pronephric duct. MP. Middle plat D. Epithelium of alimentary canal. PA. Aortic root. DF. Darmfaserplatte. In his germ layer theory, Remak's standpoint is histological rather than morphological. The distinction which he draws between the sensory and trophic layers on the one hand, and the motor germinative layer on the other, is entirely a histological one. The greater part of his book, indeed, is devoted to a study of the histogenesis of the different organs of the body. He is bent chiefly upon unraveling the part which each germ layer takes in the formation of each tissue and organ. His generalization that two of the germ layers give rise exclusively or almost exclusively to one kind of tissue excited great interest at the time, and gave the direction to histogenetic research for quite a number of years, though in the end it turned out to be insufficiently founded. Though Remak's germ layer theory had thus principally a histological orientation, it laid down the main lines of the modern morphological treatment of the germ layers. 293 Embryologie des Samens, 1842. 294 Die Cellularpathologie in ihrer Begründung auf physiologische und pathologische Jobler, Berlin, 2nd ed. 1859, ENG trans, by chance, 1860. 295 Archpath. Anat Physical, 7, pages 1 to 39, 1854. 296 Bericht über die Fortschritt der mikroskopischen Anatomie im Jahr 1854. Muller's Archive, 1855. See also 1856. 297 HNDBD Physiol, I, 1835. 298 See Lückert's reply to Ludwig's criticism, Insight. F. Wyss. Zoll, 2, p. 271, 1850. 299 Leipzig, 1853. 300 Souvenirs d'un Naturaliste, 2 volumes, Paris, 1854. ENG Transaction as Rambles of a Naturalist on the Coasts of France, Spain, and Italy, 2 volumes, 1857. 301 Milne Edwards later published a classical textbook on comparative anatomy and physiology, Leçons sur la physiologie et l'anatomie comparée, 14 volumes, Paris, 1857-80. 302 Paris, 1834-40. 3 volumes of the Suites à Buffon. 303 Paris, 1865. 2 volumes of the Suites à Buffon. 304 UD Metamorphose der Aufführung u Siegel, Berlin, 1848. UD Metamorphose der Holothurian u Asterin, Berlin, 1851. 305 As I have been unable to obtain a copy of the introduction, the passages which follow are taken from the Rapport of 1867, where Milne Edwards gives a complete exposition of his doctrine, sometimes in the words of the original. 306 This principle was first developed by Milne Edwards in 1827, in the Dictionnaire classique des Histes naturelles. It was probably suggested to him by his studies on the crustacea, among which the principle is so beautifully exemplified in the concentration and specialization of the appendages and the ganglionic chain. 307 Studied by Isidore Geoffroy Saint-Hilaire in his paper Classification parallèle de mammifères, Cr Academics I, XX, 1845. Remarked upon by Cuvier, Regni Animal, I, p. 171, 1817, also by de Blainville. 308 Cuvier et Valenciennes, Histoire nat. De Poissons, I, p. 550, 1828. 309 Mixonoiden, Thiabh. K. Akkad. Wyss. Berlin for 1834, pages 100, 110, 179, etc. 310 Virgil. Entw. Kopf. Nacht. Amphibian, p. 101, 1838. 311 I have not seen the companion volume on paleontological progression, Unters. UD Entwicklungsgesetze der Organisken Weltwaren der Bildungszeit unserer Erdoberfläche, Stuttgart, 1858. 312 Strobiloid because of its spiral development. The theory of the spiral growth of plants played an important part in botanical morphology about this time. 313 Cf. Meckel's Principle of Progressive Evolution, Supra, p. 93. 314 System der Theorischen Morphologie, pages 33, 457. Also see Bruck, Die Wirbeltheorie des Schattels, am Skelett de Lachses geprüft, Frankfurt am Main, 1862. 315 In France, the vertebral theory was advocated by Lavoisier in his Nouvelle Ostéologie comparée de la tête des animaux domestiques, Toulouse, 1864. It seems also that Lacazette held fast to it even in 1872. Archzoologie exp. Gen. I. p. 51, 1872. 316 An Essay on Classification, Boston, 1857, London, 1859. He considered the classificatory categories to be the categories of the Creator's thought, and hence natural, and in no sense mere conventions. 317 Principes de embryogenie, de zoogenie et de teratogenie, MEM. Academic Sci. XXV, pages 1 to 943, PLSXXV, 1860. 318 On the Morphology of the Cephalus mollusca, Philosophy Transaction, 1853, Sci Memoirs, I, pages 152 to 92. 319 Observations sur les changements de forme que les divers crustacés éprouvent, and Synad. 1, XXX, p. 360, 1833. 320 Considerations sur quelques principes relatifs à la classification naturelle des animaux, and Synad. 3, I. p. 65, 1844. 321 Supra, pages 79 to 83. Also Précis d'anatomie transcendante, Principes d'organogenie, Paris, 1842. 322 The inversion of the organs shown by vertebrates as compared with invertebrates is due to the reversed position of the embryo relatively to the yolk. Pages 821 to 6. 323 It is worthwhile recording that Serres enunciated a law of symmetry according to which the embryo is formed by the union of its two symmetrical halves, a law which recalls the concrescence theory of his and some modern embryologists. 324 Embryologie comparée du Brochet, de la Perche, et de la Crevice, and Synad. 4, I. p. 237, 1854, 2, p. 39, 1854. MEM. Savants étrangers, 17. 325 and Synad. 4, 16, p. 113, 1861, 17, p. 88, 1862, 18, p. 5, 1862, 19, p. 5, 1863. 326 XX, p. 5, 1863. 327 particularly in his Blennius, 1833, and Natter, 1839. 328 in the preliminary notice of his crayfish paper Isis, pp 1093 to 1100, 1825. 329 on the anatomy and the affinities of the family of the Medusae, Philosophy Transaction, 1849, Sci Memoirs, I, pages 9 to 32. 330 Philosophy Transaction, Xlien, p. 368, 1853. 331 The principle of achromatism was discovered, by Fraunhofer, and achromatic microscopes introduced in the early part of the 19th century. The use of chemical reagents, such as acetic acid, and various hardening fluids, came into fashion not long after. J. Muller seems to have been one of the first to realize their importance. Remak himself invented one or two fixing and hardening mixtures, pages 87, 127, 1855, which enabled him to cut excellent hand sections. Section cutting machines were not invented till later. V. Henson, 1866, his, 1870. 332 Unter suchen über die Entwicklung der Wirbeltiere, folio, pages XXXVII plus 195, 12 plates, Berlin, 1850–1855. Chapter 13 The relation of Lamarck and Darwin to morphology. It is a remarkable fact that morphology took but a very little part in the formation of evolution theory. When one remembers what powerful arguments for evolution can be drawn from such facts as the unity of plan and composition and the law of parallelism, one is astonished to find that it was not the morphologists at all who founded the theory of evolution. It is true that the noticeable resemblances of animals to one another, the possibility of arranging them in a system, the vague perception of an all-pervading plan of structure, did suggest to many minds the thought that systematic affinities might be due to blood relationship. Thus Leibniz considered that the cat tribe might possibly be descended from a common ancestor 333, and another great philosopher, Immanuel Kant, was led by his perception of the unity of type to suggest as possible the derivation of the whole organic realm from one parent form, or even ultimately from inorganic matter. In the course of his masterly discussion of mechanism and teleology 334 he writes, "The agreement of so many genera of animals in a certain common schema, which appears to be fundamental not only in the structure of their bones, but also in the disposition of their remaining parts, so that with an admirable simplicity of original outline, a great variety of species has been produced by the shortening of one member and the lengthening of another, the involution of this part and the evolution of that allows a ray of hope, however faint, to penetrate into our minds, that here something may be accomplished by the aid of the principle of the mechanism of nature, without which there can be no natural science in general." This analogy of forms, which with all their differences seem to have been produced according to a common original type, strengthens our suspicions of an actual relationship between them in their production from a common parent, through the gradual approximation of one animal genus to another from those in which the principle of purposes seems to be best authenticated, i.e., from man down to the polypi, and again from this down to mosses and lichens, and finally to the lowest stage of nature. Noticeable by us, viz., to crude matter. 335 So, too, Buffon's evolutionism was suggested by his study of the structural affinities of animals, and Erasmus Darwin in his Zoonomia, 1794, brought forward as one of the strongest proofs of evolution, the essential unity of plan in all warm-blooded animals. 336 But, as a matter of historical fact, no morphologist, not even Geoffroy, deduced from the facts of his science any comprehensive theory of evolution. The pre-Darwinian morphologists were comparatively little influenced by the evolution theories current in their day, and it was in the anatomist Cuvier and the embryologist von Baer that the early evolutionists found their most uncompromising opponents. Speaking generally, and accepting for the moment the theory of Lamarck, we may say that the evolution theories of the 18th and 19th centuries arose in connection with the transcendental notion of the échelle des êtres, or scale of perfection. This notion, which plays so great a part in the philosophy of Leibniz, was very generally accepted about the middle of the 18th century, and received complete and even exaggerated expression from Bonnet and Robinet. Buffon also was influenced by it. Towards the beginning of the 19th century the idea was taken up eagerly by the transcendental school and by them given, in their theories of the one animal, a more morphological turn. Their recapitulation theory was part and parcel of the same general idea. One understands how easily the notion of evolution could arise in minds filled with the thought of the ideal progression of the whole organic kingdom towards its crown and microcosm, man. Their theory of recapitulation led them to conceive evolution as the developmental history of the one great organism. 337 Many of them wavered between the conception of evolution as an ideal process, as a Vorstellian start, and the conception of it as an historical process. Bonnet, Oken, and the majority of the transcendentalists seem to have chosen the former alternative. Robinet, Treviranus, Tiedemann, Meckel, and a few others held evolution to be a real process. We have already in previous chapters 338 briefly noticed the relation of one or two of the transcendental evolution theories to morphology, and there is little more to be said about them here. They had as good as no influence upon morphological theory, nor indeed upon biology in general. 339 It is different with the theory of Lamarck, which, although it had little influence upon biological thought during and for long after the lifetime of its author, is still at the present day a living and developing doctrine. Lamarck's affinity with the transcendentalists was in many ways a close one, but he differed essentially in being before all a systematist. Nor is the direct influence of the German transcendentalists traceable in his work. His spiritual ancestors are the men of his own race, the materialists Condillac and Cabanis, and Buffon, whose friend he was. The idea of a gradation of all animals from the lowest to the highest was always present in Lamarck's mind, and links him up, perhaps through Buffon, with the school of Bonnet. The idea of the Échelle d'Êtres had for him much less a morphological orientation than it had even for the transcendentalists, for he was lacking almost completely in the sense for morphology. Lamarck's scientific, as distinguished from his speculative work, was exclusively systematic, and it was systematics of a very high order. He introduced many reforms into the general classification of animals. He was the first clearly to separate Crustacea, 1799, and a little later, 1800, arachnids, from insects. He reduced to a certain orderliness the neglected tribes of the invertebrates, and wrote what was for long the standard work on their systematics, the Histoire naturelle des animaux sans vertébrés, 1816-22. His speculative work on biology is contained in 3 publications: the small book entitled Considerations sur l'organisation des corps vivants, 1802, the larger work of 1809, the Philosophie zoologique, and the introductory matter to his Animaux sans vertébrés, volume I, 1816. It is no easy matter to give in short compass an account of Lamarck's biological philosophy. He is an obscure writer, and often self-contradictory. In the first part of the Philosophie zoologique, Lamarck is largely preoccupied with the problem of whether species are really distinct, or do not rather grade insensibly into one another. As a systematist of vast experience, Lamarck knew how difficult it is in practice to distinguish species from varieties. The more, he writes, we collect the productions of nature, the richer our collections become, the more do we see almost all the gaps filled up and the lines of separation effaced. We find ourselves reduced to an arbitrary determination, which sometimes leads us to seize upon the slightest differences of varieties, and form from them the distinctive character of what we call a species, and at other times leads us to consider as a variety of a certain species individuals a little bit different, which others regard as forming a separate species. 344 Lamarck, as for Darwin later, the chief problem was not the evolution and differentiation of types of structure, but the mode of origin of species. Lamarck is at great pains to show how arbitrary are our determinations of species, and how artificial the classificatory groups which we distinguish in nature. Strictly speaking, there are in nature only individuals, this is certain, that among her products nature has in reality formed neither classes, nor orders, nor families, nor genera, nor constant species, but only individuals which succeed one another and resemble those that produced them. Now, these individuals belong to infinitely diversified races, which shade into one another under all the forms and in all the degrees of organization, and each of which maintains itself without change, so long as no cause of change acts upon it. P. 41. But there is a natural order in the animal kingdom, a progression from the simpler to the more complex organizations, a natural échelle d'êtres. This order is shown by the relation to one another of the large classificatory groups, for they can be arranged in series from the simplest to the most complex, somewhat as follows: 1. Infusoria. 6 arachnids. 11 fishes. 2 polyps. 7 crustacea. 12 reptiles. 3 radiates. 8 annelids. 13 birds. 4 worms. 9 cirripedes. 14 mammals. 5 insects. 10 mollusks. But the order of nature is essentially continuous, and the limits of even the best defined of these classes are in reality artificial. If the order of nature were perfectly known in a kingdom, the classes which we should be forced to establish in it would always constitute entirely artificial sections. P. 45. In the same way, the lesser classificatory groups represent smaller sections of the one unique order of nature. Note that Lamarck's échelle is in no way a morphological one, and was not intended to be such. It is a scale of increasing physiological differentiation, and the stages of it are marked by the acquirement of this or that new organ, cf. Oken. Observation of their state convinces one that in order to produce them successively nature has proceeded gradually from the simpler to the more complex. Now nature, having had in mind the realization of a plan of organization which would permit of the greatest perfecting, that of the vertebrates, a plan very different from those which she has been obliged to form as a preliminary to reaching it, one understands that, among the multitude of animals, one must necessarily come across not a single system of organization which has become progressively perfected, but diverse very distinct systems, each of which has come into existence at the moment when each primary organ first put in its appearance. P. 171. For Lamarck, this order of nature was not merely ideal. Nature had actually formed the classes successively, proceeding from the simpler to the more complex. She had brought about this evolution by transforming the primitive species of animals, raising them to higher degrees of organization, and modifying them in relation to the environment in which they found themselves. Lamarck's theory of evolution is worked out in great detail in his Philosophie zoologique, but the exposition is diffuse and disconnected. It is better in giving an account of it to follow the more concise, mature, and general exposition which he gives in the introduction to his Histoire naturelle des animaux sans vertébrés 341. Near the beginning of the introduction, Lamarck gives us in a few short fundamental principles the main lines of his general philosophy. He is a confirmed materialist. Every fact and phenomenon is essentially physical and owes its existence or production entirely to material bodies or to relations between them. All change and all movement is in the last resort due to mechanical causes. Every fact or phenomenon observed in a living body is at once a physical fact or phenomenon and a product of organization. P. 19. Life, thought and sensation are not properties of matter, but result from particular material combinations. His thoroughgoing materialism is most clearly shown in its relation to living things in the first three of the zoological principles and axioms, which are developed further on in the book. These are as follows: 1. No kind or particle of matter can have in itself the power of moving, living, feeling, thinking, nor of having ideas, and if, outside of man, we observe bodies endowed with all or one of these faculties, we ought to consider these faculties as physical phenomena which nature has been able to produce, not by employing some particular kind of matter which itself possesses one or other of these faculties, but by the order and state of things which she has constituted in each organization and in each particular system of organs. To every animal faculty, of whatever nature it may be, is an organic phenomenon, and results from a system of organs or an organ apparatus which gives rise to it and upon which it is necessarily dependent. 3. The more highly a faculty is developed, the more complex is the system of organs which produces it, and the higher the general organization, the more difficult also does it become to grasp its mechanism. But the faculty is none the less a phenomenon of organization, and for that reason purely physical, p. 104. According to these axioms, function is a direct and mechanical effect of structure. The curious thing is that in spite of his avowed materialism, Lamarck's conception of life and evolution is profoundly psychological, and from the conflict of his materialism and his vitalism, of which he was himself hardly conscious, arise most of the obscurities and the irreducible self-contradiction of his theory. Lamarck divided animals, psychologically, into three great groups: apathetic or insensitive animals, animals endowed with sensation, and intelligent animals. The first group, which comprise all the lower invertebrates, are distinguished from other animals by the fact that their actions are directly and mechanically due to the excitations of the environment. They have no principle of reaction to external influences, but passively prolong into action the excitations they receive from without. They are irritable merely. The second group are distinguished from the first by their possessing, in addition to irritability, a power which Lamarck calls the sentiment intérieur. He has some difficulty in defining exactly what he means by it. I have no term to express this internal power possessed not only by intelligent animals but also by those that are endowed merely with the faculty of sensation. It is a power which, when set in action by the feeling of a need, causes the individual to act at once, i.e., in the very moment of the sensation it experiences, and if the individual is of those that are endowed with intelligence, it nevertheless acts in such a case entirely without premeditation and before any mental operation has brought its will into play, p. 24. It is the power we call instinct in animals, p. 25, and it implies neither consciousness nor will. It acts by transforming external into internal excitations. To this second group of animals, possessing the sentiment intérieur, belong the higher invertebrates, notably insects and mollusks. Only animals possessed of a more or less centralized nervous system can manifest this sentiment, or principle of unconscious reaction to external stimuli. The higher animals, or the four vertebrate classes, form the group of intelligent animals. In virtue of their more complex organization, they possess, in addition to the sentiment intérieur, the faculties of intelligence and will. Now, broadly put, Lamarck's theory of evolution is that new organs are formed in direct reaction to needs, besoins, experienced by the sentiment intérieur. The sentiment intérieur is therefore the cause not only of instinctive action but also of all morphogenetic processes. Will and intelligence, which are confined to a relatively small number of animals, have little or nothing to do directly with evolution. To understand the working out of Lamarck's evolution theory, we must revert to his conception of the échelle des êtres. What he wrote in the Philosophie zoologique is here repeated in the work of 1816 with little modification. There is a real progression from the simpler to the more complex organizations. Nature has gradually complicated her creatures by giving them new organs and therefore new faculties. It is interesting to note that Lamarck expressly refers to Bonnet, p. 110, but refuses to accept his view of an échelle extending down into the inorganic. Like Bonnet, however, and like the German transcendentalists, Lamarck makes man the goal of evolution, p. 116. He makes it quite clear that his shell is a functional one, for he links vertebrates to mollusks even while expressly admitting that they are not connected by any structural intermediates, p. 123. He does not fall into the error of the transcendentalists and assume that vertebrates and invertebrates alike are formed upon one common plan of structure. The progression of organization shown by the animal kingdom has not been altogether regular and uninterrupted. The progression in complexity of organization shows here and there, in the general animal series, anomalies induced by the influence of environment and by the influence of the habits contracted. Philosophy Zoology, I, p. 145. There are thus really two causes at work to produce the variety of organization as it appears to us, one which tends to produce a regular increase in complexity, and one which disturbs and diversifies this regular advance. The first cause Lamarck calls the vital power, pouvoir de la vie, the other may be called the influence of circumstance, anim svert, p. 134. To the latter cause are due the lacunae, the blind alleys, and the complications which the otherwise simple scale of perfection shows. To explain both these aspects of evolution, Lamarck propounded in his volume of 1816 four laws, which read as follows. First law: life, by its own forces, tends continually to increase the volume of every body possessing it, and to extend the dimensions of its parts, up to a limit which it brings about itself. Second law: the production of a new organ in an animal body results from the arisal and continuance of a new need, and from the new movement which this need brings into being and sustains. Third law: the degree of development of organs and their force of action are always proportionate to the use made of these organs. Fourth law: all that has been acquired, imprinted, or changed in the organization of the individual during the course of its life is preserved by generation and transmitted to the new individuals that descend from the individual so modified, pages 151-2. It is mainly but not entirely by reason of the first of these laws that organization tends to progress, and mainly by reason of the second and third that difference of environment brings about diversity of organization. In virtue of the fourth law, the acquirements of the individual become the property of the race. Lamarck's exposition of his first law, that life tends by its own powers to enlarge and extend its bodily instrument, is vague and difficult to understand. He has already explained some pages back how the first organisms arose by spontaneous generation in the form of minute gelatinous utricles, cf. Oken. He conceives that it is in the movements of the fluids proper to the organism that the power resides to enlarge and extend the body. Nutrition alone is not sufficient to bring about extension, a special force is required, acting from within outwards, p. 153. In the most primitive organisms the movements of the vital fluids are weak and slow, but in the course of evolution they gradually accelerate, and, becoming more rapid, trace out canals in the delicate tissue which contains them, and finally form organs. Subtle fluids play a great part in Lamarck's biology. They take the place of the soul or entelechiae which the vitalists would postulate to explain organic happenings. Lamarck seems in this to follow certain of the old materialists, who conceived the soul to be formed of a matter more subtle than the ordinary. 342. In his second law, Lamarck's essentially vitalistic attitude comes out very clearly, for it states that a psychological moment enters into all new production of form, that the ultimate cause of the development of new form is the need felt by the organism. This need is of course not a conscious one, it is a need perceived by the sentiment interior. In the large group of apathetic or insensitive animals, which do not possess this faculty, needs cannot be experienced. Accordingly new organs are here formed directly and mechanically, by the movements of the vital fluids set in action by excitations from without. The evolution, like the behavior, of these animals is due to the direct and physical action of the environment. But this is not the case with the more highly organized animals which possess feeling. They experience needs, and each need felt, acting upon their inner feeling, immediately directs the fluids and the forces to the part of the body where action can satisfy the need. Now, if there exists at this point an organ capable of performing the required action, it is quickly stimulated to act, and if the organ does not exist and the need is pressing and sustained, bit by bit the organ is produced and developed in proportion to the continuity and the energy of its use. P 155. In intelligent animals the sentiment interior may be moved by thought or will. As an example of the way in which the law works, Lamarck takes the hypothetical case of a gastropod mollusk, which as it creeps along experiences dimly the need to feel the objects in front of it. It makes an effort, unconscious, be it noted, to touch these objects with the anterior portions of its head, and sends forward continually to these parts a great volume of nervous and other fluids. From these efforts and the repeated afflux of fluids there must result a development of the nerves supplying these parts. And as, along with the nervous fluids, nutritive juices constantly flow to the parts, there must result the formation of 2 or 4 tentacles in the places to which these fluids are directed. A curious mixture of mechanistic explanations and vitalistic hypothesis. In his third law, that use and disuse are powerful to modify organs, Lamarck is upon more solid ground, and can point to many instances of the visible effect of these factors of change. It is of course rather closely bound up with his second law and may even be regarded as an extension of it. The law has reference to one of the most powerful means employed by nature to diversify species, a means which comes into play whenever the environment changes. The cause of the great diversity shown by animal species is indeed ultimately to be sought in the environment. As the imperfect and earliest forms developed, they spread over the earth and invaded the utmost corners of it. One can imagine what an enormous variety of habitats, stations, climates, available foods, environing media, etc., animals and plants have had to endure, as the existing species were forced to change their place of abode. And although these changes have taken place with extreme slowness, their reality, necessitated by various causes, has nonetheless induced the species affected by them slowly to change their manner of life and their habitual actions. Through the effects of the second and third of the laws cited above, these induced activity changes must have brought into being new organs, and must have been able to develop them further if more frequent use was made of them. They must in the same way have been capable of bringing about the degeneration and finally the complete disappearance of existing organs which had become useless. P 161. On the other hand, if the environment does not change, species remain constant. It is to be noted that change in environment is rather the occasion than the cause of modification. The environment induces the organism to change its habitual way of life. It sets up new needs, to satisfy which the organism must modify its structure. It is the organism that takes the active part in all this. The action of the environment is indirect. Of Lamarck's fourth law, which asserts the transmission of acquired characters, little need here be said in the way of exposition. Upon the truth of it depends of course Lamarck's whole theory. He himself never dreamed that anyone would ever dispute it. Lamarck sums up as follows: by the 4 laws which I have just enunciated, all the facts of organization seem to me to be easily explained. The progression in the complexity of organization of animals, and in their faculties, seems to me easy to conceive. So, too, the means which nature has employed to diversify animals, and bring them to the state in which we now see them, become easily determinable. P 168. It is never made quite clear, we may note in passing, how far his second and third laws tend to bring about an increase in complexity. In addition to diversifying animals, 343, the function creates the organ. This would seem to be the kernel of Lamarck's doctrine. But how does he reconcile this essentially vitalistic conception with his strictly materialistic philosophy? We have seen that irritability, the sentiment interior, and intelligence itself, are the effects of organization. We are told farther on that both the sentiment and intelligence are caused by nervous fluids. A great part of both the Philosophy Zoologique and the introduction to the Animaux Sans Vertebrates is given up to the exposition of a materialistic psychology of animals and man, based entirely upon this hypothesis of nervous fluids. Thus habits are due to the fluids hollowing out definite paths for themselves. The sentiment interacts by directing the movements of the subtle fluids of the body, which are themselves modifications of the nervous fluids, upon the parts where a new organ is needed. But if it is itself only a result of the movement of nervous fluids, again, how can a need be felt by a nervous fluid? This is an entirely psychological notion and cannot be applied to a purely material system. Whence arises the power of the sentiment interer to canalize the energies of the organism, so to direct and coordinate them that they build up purposive structures, or effect purposive actions, as in all instinctive behavior. Either the sentiment interer is a psychological faculty, or it is nothing. There is no doubt that, as expressed by Lamarck, the conception conceals a radical confusion of thought. It is not possible to be a thoroughgoing materialist, and at the same time to believe that new organs are formed in direct response to needs felt by the organism. Lamarck could never resolve this antinomy, and his speculations were thrown into confusion by it. To this cause is due the frequent obscurity of his writings. Should we be right in laying stress upon the psychological side of Lamarck's theory, and disregarding the materialistic dress in which, perhaps under the influence of the materialism current in his youth, he clothed his essentially vitalistic thought? Everything goes to prove it: his constant preoccupation with psychological questions, his tacit assimilation of organ formation to instinctive behavior, his constant insistence on the importance of besoin and habitude. Let us not forget the profundity of his main idea, that, exception made for the lower forms, the animal is essentially active, that it always reacts to the external world, is never passively acted upon. Let us not forget that he pointed out the essentially psychological moment implied in all processes of individual adaptation. With keen insight he realized that conscious intelligence counts for little in evolution, and focused attention upon the unconscious but obscurely psychical processes of instinct and morphogenesis. Not without reason have the later schools of evolutionary thought, who developed the psychological and vitalistic side of his doctrine, called themselves Neo-Lamarckians. We shall say then that Lamarck, in spite of his materialism, was the founder of the psychological theory of evolution. Lamarck stood curiously aloof and apart from the scientific thought of his day. 344 He took no interest in the morphological problems that filled the minds of Cuvier and Geoffroy. He had indeed no feeling at all for morphology. He did not realize, like Cuvier, the convenance de parties, the marvelous coordination of parts to form a whole. He had little conception of what is really implied in the word organism. He was not, like Geoffroy, imbued with a lively sense of the unity of plan and composition, and of the significance of vestigial organs as witnesses to that unity. He seems not to have known of the recapitulation theory, of which he might have made such good use as powerful evidence for evolution. Even with the German transcendentalists, with whom in the looseness of his generalizations he shows some affinity, he seems not to have been specially acquainted. He was interested more in the problems suggested to him by his daily work in the museum. He wanted to know why species graded so annoyingly into one another. He wanted to examine critically his haunting suspicion that species were really not distinct, and that classification was purely conventional. The question, too, of the adaptation of species to their environment, the problem of ecological adaptation, in distinction to that of functional adaptation which interested Cuvier so greatly, came vividly before him as he worked through the vast collections of the museum. He was the first systematist to occupy himself in a philosophical manner with the problems of general biology. he introduced new problems and a new way of looking at old. With Lamarck, the problem of species and the problem of ecological adaptation enter into general biology. The one point in which he does definitely carry on the thought of his predecessors is his conception of the animal kingdom as forming a scale of functional perfection. He did not go to the same extreme as Bonnet. He did not even consider that the animal series was a continuation of the vegetable series. In his opinion, they form two diverging scales. He recognized, too, that among animals there was no simple and regular gradation from the lowest to the highest, but that the orderly progression was disturbed and diverted by the necessity of adaptation to different environments. It is interesting to note that in developing this idea he arrived at a roughly accurate distinction between homologous and analogous structures. More importance, he thought, was to be attributed in classifying animals to characters which appeared due to the plan of nature than to such as were produced by an external modifying cause, p. 299. But he did not formulate the distinction in any strictly morphological way. As his ideas developed, he laid less stress upon the simplicity and continuity of the scale. In his supplementary remarks to the introduction of 1816, he admits that the series is really very much branched, and even that there may be two distinct series among animals instead of one. His last schema of the course of evolution shows no little analogy with the genealogical trees of Darwinian speculation. It is headed "The Presumed Order of the Formation of Animals," showing two separate partly branching series, and it reads as follows. It is interesting to note that vertebrates are placed between the two series, and are now not linked on directly to any invertebrate group. Lamarck's theory had little success. There is evidence, however, that both Meckel and Geoffroy owed a good many of their evolutionary ideas to Lamarck, and Cuvier paid him at least the compliment of criticizing his theory 345, not distinguishing it, however, very clearly from the evolutionary theories of the transcendentalists. But, speaking generally, Lamarck's theory of evolution exercised very little influence upon his contemporaries. This was probably due partly to the obscurity and confusion of his thought, partly to his lack of sympathy with the biological thought of his day, which was preponderatingly morphological. It was not that men's minds were not ripe for evolution, for in the early decades of the 19th century evolution was in the air. There were few of von Bayer's contemporaries who had not read Lamarck 346. Erasmus Darwin's Zoonomie ran through 3 editions, and was translated into German, French, and Italian. 347. German philosophy was full of the idea of evolution. There was no unreadiness to accept the derivation of present-day species from a primordial form if only some solid evidence for such derivation were forthcoming. Cuvier and von Baer, as we have seen, combated the current evolution theories on the ground that the evidence was insufficient, but von Baer at least had no rooted objection to evolution. In an essay of 1834, entitled The Most General Law of Nature in All Development 348, von Baer expressed belief in a limited amount of evolution. In this paper he did not admit that all animals have developed from one parent form, and he refused to believe that man has descended from an ape, but, basing his supposition upon the facts of variability and upon the evidence of paleontology, he went so far as to maintain that many species have evolved from parent stocks. In the absence of conclusive proofs he did not commit himself to a belief in any extended or comprehensive process of evolution. Imbued as he was with the idea of development, von Baer saw in evolution a process essentially of the same nature as the development of the individual. Evolution, like development, was due to a Bildungskraft or formative force. The ultimate law of all becoming was that the history of nature is nothing but the history of the ever-advancing victory of spirit over matter, p. 71. In a later essay, 1835, in the same volume he says that all natural science is nothing but a long commentary on the single phrase es verdi. p. 86. As we shall see, von Baer adopted in later years the same attitude to Darwinism as he did to the evolution theories in vogue in his youth. Although in the 20 or 30 years before the publication of The Origin of Species, 1859, no evolution theory of any importance was published, and although the great majority of biologists believed in the constancy of species, there were not wanting some who, like von Baer, had an open mind on the subject, or even believed in the occurrence of evolutionary processes of small scope. Isidore Geoffroy Saint-Hilaire, the son of the great Étienne Geoffroy Saint-Hilaire, seems to have held that species might be formed from varieties. The law which L. Agassiz thought he could establish 349 of the parallelism between paleontological succession, systematic rank, and embryological development, tended to help the progress of evolutionary ideas. J. V. Karras, who afterwards became a supporter of Darwin, seems already, in 1853, to have inferred from Agassiz's law the probability of evolution 350, but no evolution theory was taken very seriously before 1859, when The Origin of Species was published. Like Lamarck, Charles Darwin was, neither by inclination nor by training, a morphologist. In his youth he was a collector, a sportsman, and a field geologist. His voyage round the world on the Beagle aroused in him keen interest in the problem of species, their variety, their variation according to place and time, their adaptedness to environment. The conviction gradually took possession of his mind that the puzzling facts of geographical range and geological succession which he observed wherever he went were explicable only on the hypothesis that species change. He was not satisfied with the theories of evolution that had been proposed by his grandfather, by Lamarck, and by E. Geoffroy Saint-Hilaire. He did not indeed understand these theories any too well. He resolved to work out the problem in his own way, for his own satisfaction. He tells us all this very clearly in his autobiography. During the voyage of the Beagle I had been deeply impressed by discovering in the Pampeian Formation great fossil animals covered with armor like that on the existing armadillos, secondly, by the manner in which closely allied animals replace one another in proceeding southwards over the continent, and thirdly, by the South American character of most of the productions of the Galapagos archipelago, and more especially by the manner in which they differ slightly on each island of the group. Some of the islands appearing to be very ancient in a geological sense. It was evident that such facts as these, as well as many others, could only be explained on the supposition that species gradually become modified, and the subject haunted me. But it was equally evident that neither the action of the surrounding conditions, nor the will of the organisms, especially in the case of plants, could account for the innumerable cases in which organisms of every kind are beautifully adapted to their habits of life, for instance, a woodpecker or a tree frog to climb trees, or a seed for dispersal by hooks or plumes. I had always been much struck by such adaptations, and until these could be explained it seemed to me almost useless to endeavor to prove by indirect evidence that species have been modified. 351 All Darwin's varied subsequent work revolved round these, for him, essential problems: how do species change, and how do they become adapted to their environment? He never ceased to be essentially a field naturalist, and his theory of natural selection would have been an empty and abstract thing if his vast knowledge and understanding of the web of life had not given it color and form. He never lost touch with the living thing in its living, breathing reality. Even plants he rightly regarded as active things, full of tricks and contrivances for making their way in the world. No one ever realized more vividly than he the delicacy and complexity of the adaptations to environment which are the necessary condition of success in the struggle for existence. Almost his greatest service to biology was that he made biologists realize as they never did before the vast importance of environment. He took biology into the open air, away from the museum and the dissecting room. Naturally, this attitude was not without its drawbacks. It led him to take only a lukewarm interest in the problems of morphology. It is true he used the facts of morphology with great effect as powerful arguments for evolution, but it was not from such facts that he deduced his theory to account for evolution. It is questionable indeed whether the theory of natural selection is properly applicable to the problems of form. It was invented to account for the evolution of specific differences and of ecological adaptations. It was not primarily intended as an explanation of the more wonderful and more mysterious facts of the convenance de parties and the interaction of structure and function. Perhaps Darwin did not realize this inner aspect of adaptation quite so vividly as he did the more superficial adaptation of organisms to their environment. It was, perhaps, his lack of morphological training and experience that led him to disregard the problems of form, or at least to realize very insufficiently their difficulty. It is in any case very significant that only a small part of his Origin of Species is devoted to the discussion of morphological questions, only one chapter out of the 14 contained in the first edition. Though the theory of natural selection took little account of the problems of form, Darwin's masterly vindication of the theory of evolution was of immense service to morphology, and Darwin himself was the first to point out what a great light evolution threw upon all morphological problems. In a few pages of the Origin he laid the foundations of evolutionary morphology. We have here to consider his interpretation of morphological facts and its relation to the current morphology of his time. The sketch of his theory, written in 1842-352, shows a very significant division into two parts, the first dealing with the positive facts of variability and the theory of natural selection, the second with the general evidence for evolution. It is in the second part that the paragraphs on morphological matters occur. In paragraph 7, on affinities and classification, Darwin points out that on the theory of evolution homological relationship would be real relationship, and the natural system would really be genealogical. In the next paragraph he notes that evolution would account for the unity of type in the great classes, for the metamorphosis of organs, and for the close resemblance which early embryos show to one another. It is of special interest to note that he definitely rejects the Meckel-Serres theory of recapitulation. It is not true, he writes, that one passes through the form of a lower group, though no doubt fish more nearly related to fetal state, p. 42. The greater divergence which adults show seems to him to be due to the fact that selection acts more on the later than on the embryonic stages. He realizes very clearly how illuminative the theory of evolution is when applied to the puzzling facts of embryonic development. The less differences of foetus, this has obvious meaning on this view, otherwise how strange that a horse, a man, a bat should at one time of life have arteries, running in a manner which is only intelligibly useful in a fish. The natural system being on theory genealogical, we can at once see why foetus, retaining traces of the ancestral form, is of the highest value in classification, p. 45. Abortive organs, too, gain significance on the evolutionary hypothesis. The affinity of different groups, the unity of types of structure, the representative forms through which foetus passes, the metamorphosis of organs, the abortion of others, cease to be metaphorical expressions and become intelligible facts, p. 50. In general, organisms can be understood only if we take into account the cardinal fact that they are historical beings. We must look at every complicated mechanism and instinct as the summary of a long history of useful contrivances, much like a work of art, p. 51. 353. Already in 1842 Darwin had seized upon the main principles of evolutionary morphology. The indications then given are elaborated in the 13th chapter of The Origin of Species, 1st ed., 1859. A good part of this chapter is given up to a discussion of the principles of classification, only a few pages dealing with morphology proper. But, As Darwin rightly saw, the two things are inseparable. We note first that there is no hint of the scale of beings. Darwin conceives the genealogical tree as many-branched. Animals can be classed in groups under groups, and cannot be arranged in one single series. He discusses first what kind of characters have the greatest classificatory value. Certain empirical rules have been recognized, more or less consciously, by systematists that analogical characters are less valuable than homological, that characters of great physiological importance are not always valuable for classificatory purposes, that rudimentary organs are often very useful, and so on. He finds that as a general rule the less any part of the organization is concerned with special habits, the more important it becomes for classification, p. 414, and adduces in support Owen's remark that the generative organs afford very clear indications of affinities, since they are unlikely to be modified by special habits. These rules of classification can be explained on the view that the natural system is founded on descent with modification, that the characters which naturalists consider as showing true affinity, are those which have been inherited from a common parent, and, in so far, all true classification is genealogical, that community of descent is the hidden bond which naturalists have been unconsciously seeking, and not some unknown plan of creation, or the enunciation of general propositions, and the mere putting together and separating objects more or less alike, p. 420. In general, then, homological characters are more valuable for classificatory purposes because they have a longer pedigree than analogical characters, which represent recent acquirements of the race. Coming to morphology proper, Darwin takes up the question of the unity of type, and the homology of parts, for which the unity of type is but a general expression. He treats this on the same lines as E. Geoffroy Saint-Hilaire, and Owen, referring indeed specifically to Geoffroy's law of connections. What can be more curious, he asks, than that the hand of a man, formed for grasping, that of a mole for digging, the leg of a horse, the paddle of the porpoise, and the wing of the bat, should all be constructed on the same pattern, and should include similar bones, in the same relative positions. Geoffroy Saint-Hilaire has strongly insisted on the high importance of relative position or connection in homologous parts. They may differ to almost any extent in form and size, and yet remain connected together in the same invariable order, p. 434. The unity of plan cannot be explained on teleological grounds, as Owen has admitted in his Nature of Limbs, nor is it explicable on the hypothesis of special creation, p. 435. It can be understood only on the theory that animals are descended from one another and retain for innumerable generations the essential organization of their ancestors. The explanation is to a large extent simple on the theory of the selection of successive slight modifications, each modification being profitable in some way to the modified form, but often affecting by correlation other parts of the organization. In changes of this nature, there will be little or no tendency to alter the original pattern or to transpose the parts. If we suppose that the ancient progenitor, the archetype as it may be called, of all animals, had its limbs constructed on the existing general pattern, for whatever purpose they served, we can at once perceive the plain significance of the homologous construction of the limbs throughout the whole class, p. 435. We may note three important points in this passage. First, the identification of the archetype with the common progenitor; second, the view that progressive evolution is essentially adaptive, and dominated by natural selection, and third, the petitio principii involved in the assumption that adaptive modification brings inevitably in its train the necessary correlative changes. In his section on morphology, Darwin shows clearly the influence of Owen, and through him of the transcendental anatomists. He refers to the transcendental idea of metamorphosis, as exemplified in the vertebral theory of the skull and the theory of the plant appendage, and shows how, on the hypothesis of descent with modification, metamorphosis may now be interpreted literally, and no longer figuratively merely, p. 439. Very great interest attaches to Darwin's treatment of development, for post-Darwinian morphology was based to a very large extent on the presumed relation between the development of the individual and the evolution of the race. Just as he kept clear of the notion of the scale of beings, so he avoided the snare of the Meckel-Serres theory of recapitulation, according to which the embryo of the highest animal, man, during its development climbs the ladder upon the rungs of which the whole animal series is distributed, in its gradual progression from simplicity to complexity. The law of development which he adopts is that of von Baer, which states that development is essentially differentiation, and that as a result embryos belonging to the same group resemble one another the more the less advanced they are in development. There can be little doubt that he was indebted to von Baer for the idea, and in the later editions of The Origin he acknowledges this by quoting the well-known passage in which von Baer tells how he had two embryos in spirit which he was unable to refer definitely to their proper class among vertebrates. 354. Not only are embryos more alike than adults, because less differentiated, but it is in points not directly connected with the conditions of existence, not strictly adaptive, that their resemblance is strongest. P. 440, think, for instance, of the arrangement of aortic arches common to all vertebrate embryos. Larval forms are to some extent exceptions to this rule, for they are often specially adapted to their particular mode of life, and convergence of structure may accordingly result. All these facts require an explanation. How, then, can we explain these several facts in embryology, namely, the very general, but not universal, difference in structure between the embryo and the adult of parts in the same individual embryo, which ultimately become very unlike and serve for different purposes, being at this early period of growth alike of embryos of different species within the same class, generally but not universally, resembling each other, of the structure of the embryo not being closely related to its conditions of existence, except when the embryo becomes at any period of life active and has to provide for itself, of the embryo apparently having sometimes a higher organization than the mature animal, into which it is developed, pages 442-3. Obviously all these facts are formally explained by the doctrine of descent. But Darwin goes further. He tries to show exactly how it is that the embryos resemble one another more than the adults. He thinks that the phenomenon results from two principles. First, that modifications usually supervene late in the life of the individual, and second, that such modifications tend to be inherited by the offspring at a corresponding, not early, age, p. 444. Thus, applying these principles to a hypothetical case of the origin of new species of birds from a common stock, he writes, from the many slight successive steps of variation having supervened at a rather late age and having been inherited at a corresponding age, the young of the new species of our supposed genus will manifestly tend to resemble each other much more closely than do the adults, just as we have seen in the case of pigeons. 355, pages 446-7. Since the embryo shows the generalist type, the structure of the embryo is useful for classificatory purposes. For the embryo is the animal in its less modified state, and in so far it reveals the structure of its progenitor, p. 449, the embryological archetype reveals the ancestral form. Embryology rises greatly in interest, when we thus look at the embryo as a picture, more or less complete, of the parent form of each great class of animals, p. 450, a prophetic remark, in view of the enormous subsequent development of phylogenetic speculation. We may sum up by saying that Darwin interpreted von Baer's law phylogenetically. The rest of the chapter is devoted to a discussion of abortive and vestigial organs, whose existence Darwin naturally turns to great advantage in his argument for evolution. Throughout the whole chapter, Darwin's preoccupation with the problems of classification is clearly manifest. On the question as to whether descent was monophyletic or polyphyletic, Darwin expressed no dogmatic opinion. I believe that animals have descended from at most only 4 or 5 progenitors, and plants from an equal or lesser number. I should infer from analogy that probably all the organic beings which have ever lived on this earth have descended from one primordial form, into which life was first breathed, p. 484. Darwin rightly laid much stress upon the morphological evidence for evolution 356, which he considered to be weighty. It probably contributed greatly to the success of his theory. Though he himself did little or no work in pure morphology, he was alive to the importance of such work 357 and followed with interest the progress of evolutionary morphology, incorporating some of its results in later editions of The Origin, and in his Descent of Man, 1871. In his morphology, Darwin was hardly up to date. He does not seem to have known at first hand the splendid work of the German morphologists, such as Rathke and Reichert. He pays no attention to the cell theory, nor to the germ layer theory. His sources are, in the main, Geoffroy Saint Hilaire, Owen, von Baer, Agassiz, Milne Edwards, and Huxley. Perhaps his greatest omission was that he did not give any adequate treatment of the problem of functional adaptation and the correlation of parts. It is not too much to say that Darwin not only disregarded these problems almost entirely, but by his insistence upon ecological adaptation and upon certain superficial aspects of correlation, succeeded in giving to the words adaptation and correlation a new signification, whereby they lost to a large extent their true and original functional meaning. It is true that Darwin himself, as well as his successors, believed that natural selection was all-powerful to account for the evolution of the most complicated organs, but it may be questioned whether he realized all the conditions of the problem of which he thus easily disposed. He says, rightly, in an important passage, that it is generally acknowledged that all organic beings have been formed on 2 great laws: unity of type, and the conditions of existence. By unity of type is meant that fundamental agreement in structure which we see in organic beings of the same class, and which is quite independent of their habits of life. On my theory, unity of type is explained by unity of descent. The expression of conditions of existence, so often insisted upon by the illustrious Cuvier, is fully embraced by the principle of natural selection. For natural selection acts by either now adapting the varying parts of each being to its organic and inorganic conditions of life 358, or by having adapted them during past periods of time, the adaptations being aided in many cases by the increased use or disuse of parts, being affected by the direct action of the external conditions of life, and subjected in all cases to the several laws of growth and variation. Hence, in fact, the law of the conditions of existence is the higher law, as it includes, through the inheritance of former variations and adaptations, that of unity of type. Origin, 6th ed., Pop Impression, pages 260-1. It is clear that Darwin took the phrase conditions of existence to mean the environmental conditions, and the law of the conditions of existence to mean the law of adaptation to environment. But that is not what Cuvier meant by the phrase. He understood by it the principle of the coordination of the parts to form the whole, the essential condition for the existence of any organism whatsoever. See above, Chap 3, p. 34. Of this thought there is in Darwin little trace, and that is why he did not sufficiently appreciate the weight of the argument brought against his theory that it did not account for the correlation of variations. Darwin's conception of correlation was singularly incomplete. As examples of correlation he advanced such trivial cases as the relation between albinism, deafness, and blue eyes in cats, or between the tortoise shell color and the female sex. He used the word only in connection with what he called correlated variation, meaning by this expression that the whole organization is so tied together during its growth and development, that when slight variations in any one part occur, and are accumulated through natural selection, other parts become modified. 6th ed. p. 177. He took it for granted that the correlated variations would be adapted to the original variation which was acted upon by natural selection, and he saw no difficulty in the gradual evolution of a complicated organ like the eye if only the steps were small enough. It has been objected, he writes, that in order to modify the eye and still preserve it as a perfect instrument, many changes would have to be effected simultaneously, which, it is assumed, could not be done through natural selection, but as I have attempted to show in my work on the variation of domestic animals, it is not necessary to suppose that the modifications were all simultaneous, if they were extremely slight and gradual. 6th ed. p. 226. In post-Darwinian speculation, the difficulty of explaining correlated variation by natural selection alone became more acutely realized, and it was chiefly this difficulty that led Weismann to formulate his hypothesis of germinal selection as a necessary supplement to the general selection theory. The change in the conception of correlation which Darwin's influence brought about has been very clearly stated by E. von Hartmann 359, from whom the following is taken: while the correlation of parts in the organism was before Darwin regarded exclusively from the standpoint of morphological systematics, Darwin tried to look at it from the standpoint of physiological and genealogical development, and in so doing he put the standpoint of morphological systematics in the shade. But the more we are now beginning to realize that systematic relationship does not necessarily imply genetic affinity, the more must the correlation of parts come back into favor as a systematic principle. While Darwin only, as it were, against his will, relied on the law of correlation as a last resort when all other help failed, this law must be regarded, from the standpoint of the orderly inner determination of all organic form change, as having the rank of the highest principle of all, a principle which rules parallel, divergent, and convergent evolution, pages 47-8. Further on, following Radl, he characterizes Darwin's attitude to the law of correlation in these terms: Darwin's interest is entirely focused on the variation, the function, the causes of form production, in short, upon evolution. Accordingly, he regards correlation essentially as correlative variation in the sense of a departure from the given type. With morphological correlation in different types Darwin troubles himself not at all, nor with correlation in the normal development of a type, p. 49. Cuvier's conception of the convenance de parties, essential to all biology, remained on the whole foreign to Darwin's thought, and to the thought of his successors. It was indeed one of their boasts that they had finally eliminated all teleology from nature. The great and immediate success which Darwinism had among the younger generation of biologists and among scientific men in general was due in large part to the fact that it fitted in well with the prevailing materialism of the day, and gave solid ground for the hope that in time a complete mechanistic explanation of life would be forthcoming. Darwinismus became the battle cry of the militant spirits of that time. It was precisely this element in Darwinism that was repugnant to most of Darwin's opponents, in whose ranks were found the majority of the morphologists of the old school. They found it impossible to believe that evolution could have come about by fortuitous variation and fortuitous selection. They objected to Darwin that he had enunciated no real Entwicklungsgesetz, or law governing evolution. They were not unwilling to believe that evolution was a real process, though many drew the line at the derivation of man from apes, but they felt that if evolution had really taken place, it must have been under the guidance of some principle of development, that there must have been manifested in evolution some definite and orderly tendency towards perfection. 360. No one expressed this objection with greater force than did von Baer, in a series of masterly essays 361 which the Darwinians, through sheer inability to grasp his point of view, dismissed as the maunderings of old age. In these essays von Baer pointed out the necessity for the teleological point of view, at least as complementary to the mechanistic. His general position is that of the statical teleology, to use Dreyer's term of Kant and Cuvier. His attitude to Darwinism is determined by his teleology. He admits, just as in 1834, a limited amount of evolution. He criticizes the evolution theory of Darwin on the same lines exactly as 40 or 50 years previously he had criticized the recapitulation and evolution theories of the transcendentalists, principally on the ground that their deductions far outrun the positive facts at their disposal. He rejects the theory of natural selection entirely, on the ground that evolution, like development, must have an end or purpose. Zeal, a becoming without a purpose, is in general unthinkable. p. 231, he points out, too, the difficulty of explaining the correlation of parts upon the Darwinian hypothesis. His own conception of the evolutionary process is that it is essentially Zielstrebig or guided by final causes, that it is a true evolutio or differentiation, just as individual development is an orderly progress from the general to the special. He believed in saltatory evolution, in polyphyletic descent, and in the greater plasticity of the organism in earlier times. The idea of saltatory evolution he took from Kleiker, who shortly after the publication of The Origin promulgated in a critical note on Darwinism a sketch of his theory of heterogeneous generation. 362 Kleiker's attitude is typical of that taken up by many of the morphologists of the day. 363 He accepts evolution completely, but rejects Darwinism because it recognizes no Entwicklungsgesetz, or principle of evolution. For the Darwinian theory of evolution through the selection of small fortuitous variations, he would substitute the theory of evolution through sudden, large variations, brought about by the influence of a general law of evolution. This is his theory of heterogeneous generation. The fundamental idea of this hypothesis is that under the influence of a general law of evolution creatures produce from their germs others which differ from them. p. 181. It is to be noticed that Kleiker laid more stress upon the Entwicklungsgesetz than upon the saltatory nature of variation, for he says a few pages further on, the notion at the base of my theory is that a great evolutionary plan underlies the development of the whole organized world, and urges on the simpler forms towards ever higher stages of complexity. p. 184. Saltatory evolution was not the essential point of the theory. Another difference between the Darwinian hypothesis and mine is that I postulate many saltatory changes, but I will not and indeed cannot lay the chief stress upon this point, for I have not intended to maintain that the general law of evolution, which I hold to be the cause of the creation of organisms, and which alone manifests itself in the activity of generation, cannot also so act that from one form others quite gradually arise. p. 185. He put forward the hypothesis of saltatory variation because it seemed to him to lighten many of the difficulties of Darwinism: the lack of transition forms, the enormous time required for evolution, and so on. It should be noted that Kleiker regarded his principle of evolution as mechanical. It would take too long to show in detail how a belief in innate laws of evolution was held by the majority of Darwin's critics. A few further examples must suffice. Richard Owen, who in 1868-364 admitted the possibility of evolution, held that a purposive root of development and change, of correlation and interdependence, manifesting intelligent will, is as determinable in the succession of races as in the development and organization of the individual. Generations do not vary accidentally, in any and every direction, but in preordained, definite, and correlated courses. p. 808. He conceived change to have taken place by abrupt variation, independent of environment and habit. by departures from parental type, probably sudden and seemingly monstrous, but adapting the progeny inheriting such modifications to higher purposes, p. 797. He believed spontaneous generation to be a phenomenon constantly taking place, and constantly giving the possibility of new lines of evolution. Ivan Hartmann in his Philosophie des Unbewussten, 1868, and in his valuable essay on Wahrheit und Irrtum im Darwinismus, 1874, criticized Darwinism in a most suggestive manner from the vitalistic standpoint. He drew attention to the importance of active adaptation, the necessity for assuming definite and correlated variability, and to the evidence for the existence of an immanent, purposive, but unconscious principle of evolution, active as well in phylogenetic as in individual development. In France, H. Milne Edwards 365 stated the problem thus: in the present state of science, ought we to attribute to modifications dependent on the action of known external agents the differences in the organic types manifested by the animals distributed over the surface of the globe either at the present day, or in past geological ages? Or must the origin of types transmissible by heredity be attributed to causes of another order, to forces whose effects are not apparent in the present state of things, to a creative power independent of the general properties of organizable matter such as we know them today? p. 426, he concluded that the action of environment, direct or indirect, was insufficient to account for the diversity of organic forms, and rejected Darwin's theory completely. He thought it likely that the successive faunas which paleontology discloses have originated from one another by descent. But he thought that the process by which they evolved should rightly be called creation. The word was of course not to be taken in a crude sense. When the zoologist speaks of the creation of a new species, he in no way means that the latter has arisen from the dust, rather than from a pre-existing animal whose mode of organization was different. He merely means that the known properties of matter, whether inert or organic, are insufficient to bring about such a result, and that the intervention of a hidden cause, of a power of some higher order, seems to him necessary, p. 429. The criticism of Darwinism exercised by the older currents of thought remained on the whole without influence. It was under the direct inspiration of the Darwinian theory that morphology developed during the next quarter of a century. 333 Radl, LOCCIT, I, p. 71. 334 Kritik der Earthelskraft, 1790. 335 ENG Transaction by J. H. Bernard, p. 337, London, 1892. 336 H. F. Osborne, From the Greeks to Darwin, p. 145, New York and London, 1894. 337 C. Meckel, Supra, p. 93, C.F. Tiedemann, Zoology, p. 65, 1808. Even as each individual organism transforms itself, so the whole animal kingdom is to be thought of as an organism in course of metamorphosis. Also p. 73 of the same book. 338 Chapters 7 and 9. 339 On Early Evolution Theories. C. In addition to Osborne and Radl, J. Arthur Thomson, The Science of Life, 1899, and the opening essay in Darwin and Modern Science, Cambridge, 1909. 340 Philosophy Zoology, ed. C. H. Martins, Volume I, p. 75, 1873. 341 quotations in the text are from the second edit. Dessays and Milne Edwards, I, Paris, 1835. 342 For instance, Lucretius is tibi nunc animus quali sit corpore et unde constituerit pergam rationem rhetori dictus. Principio seaio per subtilumet minutus perquam corporibus factum constare. De rerum natura, 3, verses 177 to 80. 343 Contrast Trevoranus. In every living being there exists a capability of an endless variety of form assumption, each possesses the power to adapt its organization to the changes of the outer world, and it is this power, put into action by the change of the universe, that has raised the simple zoophytes of the primitive world to continually higher stages of organization, and has introduced a countless variety of species into animate nature. Quoted by Haeckel in History of Creation, I. p. 93, 1876. 344 There is no evidence that he was influenced by Erasmus Darwin, who forestalled his evolution theory, and was indeed more aware of its vitalistic implications. C. S. Butler, Evolution, Old and New, London, 1879, for an excellent account of Erasmus Darwin. 345 As did also Lyell in his Principles of Geology, 1830. 346 K. E. von Baer, Rieden, I. p. 37, Petrograd, 1864. 347 Radl, Loccit, I. p. 296. 348 Reprinted in his Rieden, I. 1864. 349 See Huxley's criticism of it in a Royal Institution lecture of 1851, republished in Sci Mem, I. pages 300-4. On its relation to Haeckel's biogenetic law, see below, p. 255. 350 System der theoretischen Morphologie, p. 5, 1853. 351 Life and Letters of Charles Darwin, ed. F. Darwin, I. p. 82, 3rd ed., 1887. 352 The Foundations of the Origin of Species, a sketch written in 1842. Ed. F. Darwin, Cambridge, 1909. 353 Cf. A Parallel Passage in the Origin, 1st ed., pages 485-6. 354 In the 1st ed. p. 439, Darwin makes the curious mistake of attributing this story to Agassiz. 355 In which nestlings of the different varieties are much more alike than adults. Darwin attached much importance to this idea, see Life and Letters, I. p. 88, and 2, p. 338. 356 See his letters, Passim. 357 Writing to Huxley on the subject of the latter's work on the morphology of the mollusca, 1853, he says the discovery of the type or idea, in your sense, for I detest the word as used by Owen, Agassiz and co., of each great class, I cannot doubt, is one of the very highest ends of natural history. More Letters, ed. F. Darwin and A. C. Seward, 1903, I. p. 73. 358 Italics mine. 359 Das Problem des Lebens. Biologisk Studien. Bad Sascha, 1906. See also E. Radl, Bile Centralblatt, XXI, 1901. 360 See the excellent treatment of the difference between the realism of Darwin and the rationalism of his critics, in Radl, 2, particularly pages 109, 135. The most elaborate criticism of Darwinism from the older standpoint was that given by A. Wigand in der Darwinismus und die Natur Newtons und Cuvier's, 3 volumes, Braunschweig, 1872. 361 in Volume 2. Of his Reden, St. Petersburg, Petrograd, 1876 über den Zweck in den Vorgängen der Natur, über Zielstrebigkeit in den organischen Körpern insbesondere, and über Darwins Lehre. 362 über die Darwinische Schöpfungstheorie, Zeitz. F. Wyss. Zoll, 14, pages 74 to 86, 1864. Elaborated in Anat UsYst Beschreibung die Alcyonerien, 1872. 363 cf. For instance, Nageli's theory of a perfecting principle, first developed in his Entstehung Begriff der Naturhistorischer Art, München, 1865. 364 Anatomy of Vertebrates, 3, 1868. 365 Rapport sur les progrès récents des sciences zoologiques en France. Paris, 1867. Chapter 14 Ernst Haeckel and Carl Gegenbohr. At the time when Darwin's work appeared, there already existed, as we have seen, a fully formed morphology with set and definite principles. The aim of this pre-evolutionary morphology had been to discover and work out in detail the unity of plan underlying the diversity of forms, to disentangle the constant in animal form and distinguish from it the accessory and adaptive. The main principle upon which this work was based was the principle of connections, so clearly stated by Geoffroy. The principle of connections served as a guide in the search for the archetype, and this search was prosecuted in two directions: first, by the comparison of adult structure, and second, by the comparative study of developing embryos. It was found that the archetype was shown most clearly by the early embryo, and this embryological archetype came to be preferred before the archetype of comparative anatomy. It became apparent also that the parts first formed, germ layers, were of primary importance for the establishing of homologies. While practically all morphologists were agreed as to the main principles of their science, they yet showed, as regards their general attitude to the problems of form, a fairly definite division into two groups, of which one laid stress upon the intimate relation existing between form and function, while the other disregarded function completely, and sought to build up a pure or abstract morphology. In opposition to both groups, in opposition really to morphology altogether, a movement had gained strength which tended towards the analysis and disintegration of the organism. This movement took its origin in the current materialism of the day, and found expression particularly in the cell theory and in materialistic physiology. The separation between morphology as the science of form and physiology as the science of the physics and chemistry of the living body had by Darwin's day become well nigh absolute. The morphology of the 50s lent itself readily to evolutionary interpretation. Darwin found it easy to give a formal solution of all the main problems which pre-evolutionary morphology had set. He was able to interpret the natural system of classification as being in reality genealogical, systematic relationship as being really blood relationship. He was able to interpret homology and analogy in terms of heredity and adaptation. He was able to explain the unity of plan by descent from a common ancestor, and for the concept of archetype to substitute that of ancestral form. The current morphology, Darwin found, could be taken over, lock, stock and barrel, to the evolutionary camp. In what follows we shall see that the coming of evolution made surprisingly little difference to morphology, that the same methods were consciously or unconsciously followed, the same mental attitudes taken up, after as before the publication of The Origin of Species. Darwin himself was not a professional morphologist. The conversion of morphology to evolutionary ideas was carried out principally by his followers, Ernst Haeckel and Carl Gegenbohr in Germany, Huxley, Lancaster, and F. M. Balfour in England. It was in 1866 that Haeckel's chief work appeared, A General Morphology of Organisms 366, which was intended by its author to bring all morphology under the sway and domination of evolution. It was a curious production, this first book of Haeckel's, and representative not so much of Darwinian as of pre-Darwinian thought. It was a medley of dogmatic materialism, idealistic morphology, and evolution theory. Its sources were, approximately, Buchner, Theodor Schwann, Virchow, H. G. Braun, and, of course, Charles Darwin. It was scarcely modern even on its first appearance, and many regarded it, not without reason, as a belated offshoot of nature philosophy. Its materialism is of the most intransigent character. The form and activities of living things are held to be merely the mechanical result of the physical and chemical composition of their bodies. The simplest living things, the Monera, are nothing more than homogeneous masses of protein substance. They live, but without organs of life. All the phenomena of their life, nutrition and reproduction, movement and irritability, appear here as merely the immediate outcome of formless organic matter, itself an albumin compound, p. 63, 1906. Teleology, the Achilles heel of Kant's, otherwise sound, philosophy, is to be regarded as a totally refuted and antiquated doctrine, definitely put out of court by Darwinism. Haeckel works out his materialistic philosophy of living things very much after the fashion of Schwann. There is the same talk of cells as organic crystals, of crystal trees, of the analogy between assimilation by the cell and the growth of crystals in a mother liquid. Heredity and adaptation are shown equally as well by crystals as by organisms, for heredity, or the internal Bildungstrieb, is the mechanical effect of the material structure of the crystal or the germ, and adaptation, or the external Bildungstrieb, is a name for the modifications induced by the environment. Adaptation so defined comes to be synonymous with the fortuitous variation which plays so great a part in Darwin's theory of natural selection. It goes without saying that Haeckel allowed to the organism no other nor higher individuality than belongs to the crystal, and took no account at all of that harmonious interaction of the organs which Cuvier called the principle of the conditions of existence. The concept of correlation had simply no meaning for Haeckel. The analysis and disintegration of the organism was pushed by him to its logical extreme, and in this also he was a child of his time. A no less important influence clearly visible in the general morphology is the idealistic morphology of men like K. G. Karras and H. G. Braun. In previous chapters we have seen how K. G. Karras attempted to work out a geometry of the organism, and how Braun tried in a modest way to found a stereometrical morphology, but had the grace not to push his stereometry à l'outrance, recognizing very wisely that the greater part of organic form is functionally determined. Haeckel took over this idea 367 and pushed it to wild extremes, founding a new science of promorphology of which he was the greatest and only exponent. 368 The science dealt with axes and planes, poles and angles, in a veritable orgy of barbarous technical terms. It was intended to be a crystallography of the organic, and to lay the foundations of a mechanistic morphology, or morphography at least. How it was to be linked up with the physics and chemistry of living matter on the one hand and with the ordinary morphology of real animals on the other, was never made quite clear. The science of promorphology has no historical significance. It is interesting only because it illustrates Haeckel's close affinity with the idealistic morphologists. Another abortive science of Haeckel